Hi, welcome back to a new lecture from the Transformers for Vision series. In the last lecture, we discussed why transformers are needed to capture long-range dependencies within images, which CNNs struggle to do. And this is the first time in this lecture where we will be diving deep into the actual architecture of a transformer. We will be discussing from the context of large language model rather than vision transformers in the current lecture. However, whatever we learn today will also be translated directly to when we discuss about vision transformers in the future lecture. So the way I have arranged today's lecture is completely beginner friendly. You don't have to know anything about transformers yet. And we'll be tracking, or we'll be trying to understand how a transformer works from the perspective of an individual token. I will define what is a token, and we will look at this token's journey to see how the transformer operates. I'm pretty sure all of you are familiar with this paper, Attention is All You Need, which came out in 2017, and this is the paper that revolutionized the field of artificial intelligence as we see the hype today. This paper has 200,000 plus citations from Google, and in this paper they propose for the first time the idea of self-attention, which we will discuss in this course. And this changed the way people implemented natural language processing. So transformer was the main part of this paper with self-attention introduced in it, and then later various other variants came. There was flash attention, and there are many other modifications that happened to transformers later, but the base model remains the one that is proposed in the Attention is All You Need paper. So let's see what is a transformer architecture and how exactly it works. Be prepared to dive in. Feel free to take notes. If you want to pause the video and rewatch some sections, feel free to do that. But, stay very focused, because we'll be actually discussing how exactly each individual module in the transformer works. This is probably the most famous figure of transformer architecture that currently exists on the internet. I have overlaid two things on top of the image. This slight red color box with some text annotation. So I added it myself. But what you see inside is the transformer architecture diagram, which was there in the Attention is All You Need paper. So in today's lecture, we will not be looking at this entire architecture, because this architecture consists of two parts. One is encoder and another one is decoder. So encoders are found in models like BERT. So BERT is basically an encoder only architecture. Decoders are found in models like GPT. So GPT is a decoder only architecture. So if you understand how decoder works, you can basically understand how GPT or Chat GPT works. So our focus in today's lecture will be on a decoder only architecture. So this part we won't be having a look at. However, don't worry, if you understand how exactly this works, you understand how the entire transformer architecture works. The rest of the things are very simple. So this is where we start. Now the problem is this diagram, right? Although it captures everything, it is the most famous diagram. For beginners, it's not very friendly, because there are so many things going on. There are so many terminologies, so many arrows that connect different modules. So unless you have a very specific perspective, or unless you have some prior experience, it's difficult to read what's going on in this diagram, which is why I will show you different version of the same diagram which I have constructed, and I will walk you through the same decoder architecture as I walk you through the different modules of the decoder only model. So what happens in a large language model? A large language model simply makes predictions of the next word. So you can open ChatGPT and ask, is BERT decoder only model, or rather encoder only model? Then you see the way it answers. It prints one word at a time. So basic task that a large language model performs is called next word prediction. And once you have the next word, this you can add to the already existing words, and now you have another input, the cat sat on the mat, and then you can try to predict the next word and then add it to the existing sequence and do this iteratively to produce a long, big response. So the input or the prompt is the sentence or sequence which you give. Model is the large language model. It could be GPT, it could be any other model. And output at one time is the next word that is predicted. And this process is repeated to produce entire paragraphs. So if we can understand how this next word prediction happens inside a transformer architecture, we can basically understand how a chat GPT model or how GPT model works. So now let's see how this entire simplified diagram works in reality. So here, what I am showing you is a simplified or modified diagram that shows decoder only architecture. So when I say decoder only, what I mean is the right hand side of the above figure. So this figure, this right hand side has a bunch of things. Same thing I have drawn in a slightly different way. Now, I know that here also there are a bunch of things going on, which is probably not very beginner friendly, which is why I won't be asking you to look at this whole thing at once. We will look at this entire architecture in chunks. So focus on three main parts. We can divide this entire architecture into three parts. The first part is this part where input is taken care of. Basically, input is transformed into some format. And what is the input? Input is the sequence, the cat sat on the. Then the second part or the second block is called the transformer block. And then the third block is where output is produced, where the next word prediction happens. So we will be looking at only one of these blocks at a time. So first we will keep our focus on the input section. Then once we understand it fully, what happens to the input, we will move on to transformer block. And then once we understand fully what happens here, we will move to the output section. So we will attack this architecture in a very sequential manner. So ignore everything on the right hand side, ignore this and this for now. Don't think about 2 and 3. Let's just think about what happens to the input once you feed it. What happens in this input part of the transformer. So now we are focusing just on this part, right? And you can see that three things are written. First is the input sentence. Second is the tokenized text. Then I have written something like token embedding and positional embedding. What are these things? What is a token? What do we mean by token embedding? What do we mean by positional embedding? Right? This part you might probably know. This is something called as like a prompt or input. The cat sat on the. Now, if we understand each of these things which I labeled as A, B, C separately, we can understand what this input section of the transformer architecture is doing. So let's consider an input. First, what happens to this sentence is it is split into words. So you can think of each word as a token. That is a simplified way to say in actual transformer architecture, you will not be splitting a sentence into words. Like there are words, there are subwords, and there are other characters also that can form a token. But here, for the purpose of simplicity, you can say that this sentence is split into 5 tokens. The cat sat on the. So these are the 5 tokens. And we will just focus on one token so that we can track what happens to that token as it goes through the transformer architecture. So we will focus on the cat token, which is the second token in this sequence. If you are interested to know how exactly this tokenization happens, so this splitting of this input into tokens is called tokenization. The tokenization, one of the ways in which you can tokenize is called byte pair encoding. People did not come up with byte pair encoding randomly. There were other options too. You could tokenize based on just words, as I just showed you. The cat sat on the. So you could have simply 5 tokens. Logic is very simple. Wherever you identify a word, convert that word as a token. The problem with this is if some new words are introduced into the vocabulary, let's say this is the name of a like a drug, Ozempic. If a new word is coming into the vocabulary or new word is coming into the language, it may not be part of the vocabulary of the transformer model. So these are called out of vocabulary words, OOV. This can happen. Another is there are words with similar meaning. The root word remains the same. So cat and cats, they both refer to the idea about cat. So the root word remains the same, but they are now becoming two different tokens, right? Which is not necessarily good. And think about a dictionary that we have to construct that consists of all the words. English language apparently has 200,000 words. We can ask ChatGPT how many words are there. Roughly, how many words are there in English language? So 600,000 entry. Some of them say Merriam-Webster 470,000. Then modern usage 20,000 to 35,000. Core modern English 170,000. So it depends on what you look at. All words ever recorded 600,000. So there are different words that you can consider. So you can say it's on the order of 100,000. So you have to create a dictionary that has that many words in it or that many tokens in it to identify, hey, the token number 1 in this particular input is that word in the dictionary, right? So it's a very difficult thing to do. The easy thing about this word-based tokenization is that the tokenized sequence is small. If you are converting, the sentence into words, where words are the tokens, if a sentence has 5 words, basically you are converting that sentence into 5 tokens, which is a good thing. There is the other extreme which you can do, which is character-based. So in character-based, you could split the entire sequence into individual characters. So for example, the cat sat on the mat will become something like so 3 tokens for the, then space will have a token, then cat, something like this. The great thing about this is, if you look at the alphabets, there are only 26 alphabets. Then you can consider small letter alphabets, capital letter alphabets, and maybe some other numbers. So there are, the vocabulary size will be very small because you are considering the basic element of language, right? You are not now considering words. You're considering the character level, tokens at a character level. What this means is you don't have to construct a vocabulary or a dictionary of 200,000 items. You maybe have to construct something on the order of 200 or 250 items, considering all the small letter and capital letter characters, spaces, other maybe special symbols, etc. So your dictionary remains a small dictionary. Then out of the vocabulary words won't exist. Why? Because you are anyway splitting. So if Ozempic word comes, this is anyway split into O, Z, E, M, P, I, and C. And those are actually tokens that are existing in the dictionary if you are using character-based splitting. But the problem is, when you do this, the meaning associated with the word is entirely lost. If you split a word into a bunch of characters, you are looking at the word as just individual at an individual character level. So the meaning associated with putting those characters together is now lost. And another worst problem is each sentence you are now splitting into a very long sequence. For example, the cat sat on the, right? So let's say this is the input sentence. If we were splitting this into just words, we just have 5 words. So it's the sequence length is 5. But if it was characters, we will have 3 plus, let's say, space plus 3 plus space plus 3 plus space plus 2 for on plus space plus the 3. So 3 plus 1, 4, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. The sequence length is 18. And here if we consider to this 5, if we add the spaces, we have 1, 2, 3, 4. So maximum this will become 9. So see the sequence length, if we are splitting the sentence into just characters, is much higher. So that is the disadvantage of character-based tokenization. So what is done is something in between. So something in between called byte pair encoding. So in byte pair encoding, what is done is, here is an example. Let's say you have a sequence in which the sequence looks like this: CCC, AK, CCC, ACM. In byte pair encoding, you look at two characters at a time, and you check how many such pairs exist. So in this case, we can see that CC is a pair. There is another CC here. This CC is another pair. This CC is another pair. Then what else do we have? CA. We have here also we have CA. Yeah, I guess that's it, right? You can see a bunch of 1, 2, 3, 4, 5, 6 pairs of tokens. Now, what we do is we replace the most frequently occurring pair, in this case that is CC, with a new character which is not present in the current input sequence, or which is not present in the input data set. So let's say that is this capital Q. So CC you replace by capital Q. Then what will happen? Then this sequence will become QCA. So the first CC, whenever you encounter the first CC, it is replaced by capital Q, which means this CC is not counted anymore, the second CC. So then it will become QCA K, QCA CM. Now we look at, okay, now are there any more pairs? Yes, there is. QC is a pair, QC is a pair, CA is there, CA is there. That's it, right? QC and CA. The first occurring pair is QC. And what would that mean is we can replace now QC with another character which is not occurring in the input, which let's say is P. So then they will become PAK, PACM, because QC will now become P. Now what we can do is, again, we can identify a pair, right? PA is a pair now. So PA is one, PA, another one is there. So most frequently occurring pair here is PA. Now we can again replace PA by Z, and this sequence will now become ZK, ZCM. Now there are no more pairs existing, which means the byte pair encoding will stop at this point. So what we have done is, by encoding pairs that occur frequently, and by replacing that with another character which is not there in the input, we convert this into a smaller sequence representation. So now this is the byte pair encoding technique. Byte pair encoding, however, is not an idea that was introduced in the Attention is All You Need paper. It was introduced much earlier. Paper, I think this was in 1994 or something like that. Original. Pretty old paper. In the original paper, so this is that original paper from 1994 that introduced the concept of byte pair encoding. And it's amazing how this concept is now actually became useful after many years in the context of large language models. And byte pair encoding based tokenization has now become very famous and very frequently used. So this was a small digression, but let's come back to where we left. We were discussing about tokenization. So let's forget about byte pair encoding for a moment, because it's not going to affect the way we understand how a transformer architecture works. Let's imagine the sentence is still split into words, and we have 5 words, and the word that we are looking at with our focus is the word cat. Let's see what happens to this token. The first thing that is done is to check where this token exists in our dictionary. So the dictionary we can think of as something like it consists of many predefined tokens. And as I said, it can be characters, it can be subwords, it will have, things like this end character to denote the end of a paragraph or things like that. And this dictionary has a mapping where an ID, so this is a number which denotes the ID, is mapped with the corresponding token. In GPT-3, the dictionary size was 50,257, meaning that many tokens were existing in the dictionary of GPT-3. And in GPT-3, the tokens were not necessarily words. They were created using byte pair encoding, which means it will have other characters also. Now, what we will do is we will look at this cat token and see where it exists in the dictionary, and we will see that it is this 3428th token in the dictionary. Right? So we know that now this is the token. Now, the way these tokens are stored is by doing something called token embedding. So token embedding is where you convert the token into a vector format. And in GPT-2, the small GPT-2 version had a vector of 768 dimensions. So what that means is the word cat, all right, the word cat is converted into a vector with 768 dimensions, and each dimension you can think of as something like you are asking a question to this token, something like, is this a noun? Is this token about a gender? Is this token about a verb? Is this about an animal? So since cat is an animal, maybe this number is high relatively. Now, of course, this is not the actual meaning of the individual dimensions. Nobody knows what exactly these individual dimensions mean, but you can imagine those dimensions to be features that are used for representing the token. And how is this tokenization done? How are these words converted to vectors? There are pre-trained neural networks which can perform this tokenization. So cat will be converted into a vector of 768 dimensions, and there will be some meaning associated with where this vector is pointing in that 768 dimensional space. Now, every word in the dictionary, every 50,000 plus words in this dictionary will be converted into this vector format, and it will be already stored. Now, how does this vector look like? Let's see how this vector representation looks like. So let's say I am representing the 768 dimensional space in just 2 dimensions. I'm only plotting the first dimension and 768 dimension, but of course I can't plot more. But just imagine vectors pointing in certain directions in this space. The different regions in this multi-dimensional space has meaning. So there might be one hyperspace in this 768 dimensional space where the semantic meaning of that space is related to animals. So maybe the vectors of cat, dog, and other animals will be generally pointing in that direction. So these vectors will be lying close to each other if you calculate the angle between them. And likewise, if you look at some other vectors, if you convert the word apple into its corresponding vector and the word orange into its corresponding vector, along certain axes, they will be lying close to each other because maybe they are pointing to the semantic space which represents fruits. But in maybe along some other directions, perhaps these two vectors, maybe apple and dog, might remain closer to each other. Maybe a vector that or a direction or dimension that represents color. Maybe dog is, let's say there is a brownish color dog, apple is red, whereas orange is orange and cat is black. So on a dimension that is representative of color, maybe the way these vectors are arranged are different. So it depends on which dimensions we are considering. However, please understand that the numbers that are associated with the 768 dimensions are not random. They carry meaning. Now, there is one more thing that we have to consider, right? So first, let's take a step back. This is token embedding, and this is the step that we see here. So first, the text is tokenized. In our example, we are saying that the tokenization is based on words. Although in reality, it may be based on byte pair encoding, but for simplicity, we'll assume words. And now those words are tokenized. What do we mean by that? We look at the ID of those words in our dictionary, and from there we can get the vector associated with that word. So if the current word that we are looking at cat, we will get a 768 dimensional vector. which is meant for cat. So these two parts are fine. So how many such vectors we will have? Since we have 5 tokens, we will have 5 such vectors. 1, 2, 3, 4, 5. So we will have 5 vectors of each 768 dimensions. Then there is one more step in the input block, which is called positional embedding. Positional embedding is very important and very interesting. So consider this sentence. The dog chased another dog. So here, if we were to consider just the vector embedding of the token, there are these many tokens, right? The dog chased another dog. There are 5 tokens in this sentence. And these 2 tokens are the same. This is dog and this is also dog. However, they are 2 different dogs. The one is the chasing dog, the other one is actually being chased. So there should be some difference in the vector associated with dog in the token number 2 and dog in the token number 5. So something about this position has to be encoded, or it has to be added into the vectorized token. So what is done is another vector of same dimension of 768 dimension is created, and this vector now carries information about the position of the token. So you can think of each dimension to carry some features or some meaning, although it's not necessarily like this. Maybe one dimension is about, is this token at the beginning of the sentence? Another token is about, is this, another feature is about, is this token at the middle of the sentence? Is this token requiring long range dependency? Because there could be sentences where, for example, the teacher who was explaining a difficult concept to the students smiled. Now here, look at who smiled here. It's the teacher who smiled, right? But the teacher word is at the beginning of the sentence. The smiled word is at the end of the sentence. So this is called long range dependency. The smile is highly dependent on, or it has to, it carries significant association with the word teacher in this particular context. So maybe some dimension or some feature in this 768 dimensional vector is about long-term, the existence of long-term dependency or long-range dependency. Another could be about, is there, is this a normal position for this words to occur? So there are many different meanings one can associate with the different dimensions of the position embedding. However, nobody knows what is the exact meaning, but we can think of it in that way. Now what is done? The position embeddings are added to the token embedding. So how do we visualize that? Let's say the token embedding without considering the position, the normal dog token is having a certain vector. You can consider position embedding as an additional vector added to it, so that now the position embedded dog vector is pointing in slightly some other direction. So for this obvious reason, since the dog in the position 2 here and the dog in the position 5 here will have different position embeddings, those 2 vectors, the red color dog vector and blue color dog vector, should point in 2 different directions. And it should also be pointing in different direction from the original dog vector without the position embedding. So this is the original dog vector, this black vector. They are both pointing in the same direction. But then to get the dog vector for character, this second token, versus to get the dog vector for the third token, sorry, not third, fifth token, you are adding different position embedding vectors. So this is the position embedding vector for this dog, corresponding to position 2, and this could be the position embedding vector for the fifth token, which is another dog. And the final output, which is this vector and this vector, are now pointing in different directions. because now that position information is also added. So this is the idea of position embedding, and in vector terms, it will look like this. The original token embedding was the 768 vector, which had some semantic meaning. On top of it, you add the position embedding vector. So these two vectors are added element wise. So 0.1 plus 2.1, 0.21 will be 0.31, 0.23 plus 0.13, 0.36, like that. So now you have input embedding. Once you consider token embedding and once you add position embedding to it, when you add these two vectors element wise, the resulting output is the input embedding. Input embedding of what? Input embedding of the current token that we are looking at. The example that I mentioned second was about that of a dog, just to give you the idea about position embedding, but we are following the token called cat. So same thing applies for the cat token. The cat token is in the second position of the sequence, and that embedding, that position embedding, is added onto the cat vector. So this is what is happening in the input block of the transformer. The input text is tokenized, meaning divided into words or tokens. Then those tokens are embedded. And this embedding, for this embedding, we already have a pre-trained neural network. We don't have to go into the details of that. Words are converted into vectors. Just understand that. It's already converted. It's already there in the dictionary. The vector corresponding to the word cat will already be there in the dictionary. And then on top of it, depending on the position of the token, we add the positional embedding to get the input embedding. So what comes out of this is the input embedding. And this will, of course, be a 768 dimensional vector. There are other GPTs. So this is the case of GPT-2. In GPT-3, it was 12,288 dimensions instead of 768 dimensions. This exact number does not matter. It varies from models to model. Now let's get back to the architecture. So we entirely covered the input part of the transformer architecture. Now let's come back to the architecture, right? So in the input section, let me just zoom out. In the input section, these were the three things going on. You have the input text, which is tokenized. So you split the text into the, cat, sat, on, the, right? So here cat is the token. Then that token is embedded, meaning it is converted into a 768 dimensional vector. And then you add position embedding to that token. This is done for all the tokens in the input. But we are currently focusing on only one token, the token called cat. So whatever is the position embedding vector corresponding to that, basically corresponding to position number 2, that is added. And finally, the output that comes out of this is input embedding. Now let's get back to the transformer, the entire architecture of the large language model. This part is done. Of course, we have simplified bunch of things, but we'll be moving into more complex aspects about these architectures in the later lectures. This lecture's purpose is to give you a proper overview. Now let's move on to the transformer block, which is the block number 2 in our schematic. So let's just isolate that block number 2 and let's just look at it. What are the things that you see here? You can see there is a layer normalization. I'm not expecting you to know any of this, but I'm just calling it out so that you can just pay attention to those words, and then I'll explain what those words mean. So there are two parts where you see layer normalization. There are two parts where you see dropout. There is a multi-head attention. There is a feed-forward neural network. And you see this plus, it signifies skip connections, where you have connections that helps you prevent vanishing gradients while training the neural network, which I will explain. So we have to go through each of these individually to understand what exactly is happening in a transformer block. Now, out of this, the most difficult concept is obviously multi-head attention. So what I'm going to do today in this lecture is to just briefly touch upon multi-head attention without going into the details of it. And I have 2 to 3 lectures planned just to discuss about multi-head attention. attention mechanism, self-attention, causal attention, and multi-head attention. So all of these we'll be discussing in the upcoming lectures. For now, let's focus on the overall architecture, and I'll take you by hand holding. So don't worry about whether you will understand something or not, just because we are not diving deep into the multi-head attention currently. So let's move on. So this is another way in which you can draw the same transformer block. Okay, so there are 1, 2, 3, 4, 5, 6 items and then skip connections. I just had a different redrawn version of the transformer block. So the input, so this is the entire transformer block. So input embedding is coming here. It goes here, right? Input embedding of the token. Then it undergoes layer normalization. Then it goes through multi-head attention, and there is a skip connection here. So right after layer normalization, you have a skip connection, then multi-head attention and dropout. Then same thing repeats. You have layer normalization. After layer normalization, you have a skip connection going here. Basically, what skip connection means, whatever output comes out of this is directly passed here. And this plus sign means whatever output comes out of here and whatever comes through here, you are adding those two and sending it here. I'll explain why we need this. So now, because I have drawn it in this way, I hope it feels slightly better, right? So there is a little bit of symmetry. So you have layer normalization followed by multi-head attention and dropout. Here you have layer normalization followed by feed-forward neural network and dropout. So there is some symmetry, not entirely symmetric, but some symmetry is there. Now let's focus on this transformer block. Firstly, what is layer normalization? Layer normalization is something that is applied to each token. So let's say my token is a 5-dimensional token. We are discussing so far 768 dimensions, but let's say my token has only 5 dimensions, x equal to 2, minus 1, 3, 4 dimensions, 3, 0, as shown in this example. What is done to this token is you first calculate the mean. So mu equal to 2 plus 5, 4 divided by 4, which will be 1, right? So mean is 1. And standard deviation, I have already done the calculation, is 2 minus 1 the whole square plus minus 1 minus 1 the whole square plus 3 minus 1 the whole square, then 0 minus 1 the whole square, and then you add that, divide by 4, you get the variance, and then you take the square root, you get standard deviation. And standard deviation turns out to be 1.58. Then what is done is, this x is converted to 2 minus mu by sigma, minus 1 minus mu by sigma, then 3 minus mu by sigma, and then 0 minus mu by sigma. By doing this, what happens is this input token, it's in the distribution of its values in each dimension. What happens is the mean of this distribution will become 0, because you are subtracting the mean from the distribution. So mean becomes 0 for this distribution. And then the standard, you're dividing each of the terms by the standard deviation, which means the standard deviation will become 1. So basically, the purpose of layer normalization applied to each token is to bring the mean close to 0 and bring the standard deviation close to 1. So this is what is done, x minus mean of x. So in simple terms, x minus mu of x divided by sigma of x. X is the entire variable. This is what is done. In addition to this, there is one more thing that is done in layer normalization, which is scaling and adding a bias. So this, whatever you get here, will be multiplied by a term beta I plus gamma I. So this is called scaling and this is called adding a bias. And these two are trainable parameters, which is done so that after layer normalization, if you want to kind of scale up the numbers and if you want to offset the numbers a little bit with some learned parameters, you can do that. But let's not go into the details of what is beta and what is gamma. Just understand the purpose of layer normalization. It kind of standardizes your data. So that is done in both of these layers, in layer norm 1 as well as layer norm 2. The next part, the skip connection part, is done so that you can prevent something called as vanishing gradients. So Think of a neural network with a lot of layers. Okay, ignore about it. Don't think about the transformer architecture. Just think about a neural network with bunch of layers. What happens is the magnitude of the gradient, and when I say gradient, I mean gradient of loss with respect to weights in, let's say, layer number 1, and or gradient of loss with respect to weights in layer number n. N is the last layer. In general, we can say that the magnitude of loss, change in loss when you change some weights in layer 1 compared to magnitude of loss when you change the weights in layer number n, this will be greater. In fact, much, much greater. What this means is, if you slightly change something in this layer, that will have more influence on the output and consequently on the loss than when you make changes over here. And that is because if you plot the gradient magnitude as a function of the layer, the outer layers, the nth layer will have higher magnitude and earlier layers will have lower magnitudes. And what does this mean? What is the consequence of this? The consequence of this is that in backpropagation, what we are trying to do is we are trying to modify the weights. So let's say weight number 1 will get modified such that the earlier weight minus learning rate multiplied by dou loss by dou weight 1. Now what will happen if this magnitude of this is small? It means this number will be close to 0, which means the weight number 1 will not get updated. On the other hand, weight in the nth layer will be changing such that wn minus eta times dou loss by dou wn. And because the magnitude of gradient in the nth layer is much higher, as you can see here, there will be a lot of significant change happening to the weights in the nth layer. So what that means is, if you want to modify the earlier layers, because that is important, right? Because earlier layers, unless you modify, you won't have a fully trained neural network. It will take a lot of iterations. So this problem is called the problem of vanishing gradients. And this was solved in a very ingenious way by the idea of skip connections, which was famously introduced in the paper of ResNet, residual neural network, you might have heard of. ResNet also has around 170,000 or something citations, very, very famous paper. So what they did is they introduced something called as skip connections, where earlier layers are directly, whatever numbers are there are directly passed here, and then they are added here. Then they are passed here like this. I mean, this is an oversimplified version of skip connections, but the goal here is that the influence of the earlier layers at the output should be bigger, so that even if you change the weight over here slightly, there should be some influence on the output, which means there should be some influence on the loss. What does that mean? It means during backpropagation, the influence of earlier weights on the loss is significant, and that means those weights can get modified by a significant factor rather than just minuscule modification. So your training process will become much more efficient. So these skip connections kind of solve the problem of vanishing gradient by increasing or making the magnitude of gradient in the earlier layers also relatively higher. And this is exactly what you see in the transformer block also in the form of skip connections. So this is a skip connection. This is also a skip connection. Okay. Now you see something called dropout. Dropout is something that is done to prevent the model from sort of overfitting. So it's like a regularization technique, where if you have a neural network with bunch of neurons, in certain backward passes or in certain training loops, you prevent some, on a probabilistic basis, you prevent some nodes from participating in that training loop. So what happens is these nodes are not available anymore, which means now the rest of the nodes are forced to learn the patterns in the data. In the earlier case, maybe these are the nodes that are doing a lot of heavy work. Maybe these are like lazy nodes, which are not contributing much to the final output. But now, because in the current training loop, these nodes are switched off, meaning they are not participating in forward propagation and backward propagation anymore, the other nodes will significantly change its weights. And you do this randomly. you say I have to switch off 50% of the nodes randomly. So in each layer, so in the current layer, if I say 33% of the nodes should be switched off, then in the current loop, maybe this node will be off. In the next loop, maybe this will be off. When I say off, simply nothing passes through that. That's all. And to prevent the output from scaling down, because since only 1/3 of the nodes are now available in this layer, whatever output comes out of this might be scaled down on an average by a factor of 1/3. To prevent that, the output from the other nodes are increased by that much factor. So output from the other two nodes will be scaled up by a factor to compensate for the loss in the output magnitude due to the absence of these dropped out nodes. So dropout will force some lazy neurons to learn from the data, which they otherwise may not, because there are other neurons that are doing a lot more heavy lifting. And this dropout is also there at two places. This is one place where you have dropout, and this is another place where you have dropout in the transformer block. Now you have two more things to discuss. One is multi-head attention and another is a feed-forward neural network. Now, all the amazing things about the transformer architecture happened in the multi-head attention part. I will briefly explain in one sentence, and remaining things in detail we can discuss in the upcoming lecture where we actually dive deep into multi-head attention. But the idea is this. The earlier sentence which I wrote, the teacher who was explaining a difficult concept to the students smiled. Now let's say this is my input and I have to predict the next word based on this input in transformer. What is done is something called as attention score is created, where I say if the word that I'm looking at was the, how much attention should this, or how much connection should this word should have with teacher? How much should this word have a connection with this word? How much should the connection between these two should be? Because this matters, right? So if you look at the word smiled, this word smile should attend a lot to the word teacher, because teacher is the one who is smiling, not students. But if you are just looking at this as a sequence, you will see that in the sequence, these two words are actually close to each other. Students and smiled are close to each other. So how can you teach the large language model, or how can you teach a neural network that actually these two words are not the ones that should attend each other that much? In fact, it should be teacher and smiled, these two. So what is constructed is something called as attention score, which I will discuss in detail in the next lecture, because if I keep it in this lecture, the length of this lecture will go few hours. To prevent that, I am simplifying it and I will conveniently skip the part of the multi-head attention so that you can focus on the rest of the architecture. Then in the next lecture, I'll exactly explain how the multi-head attentions, self-attention, causal attention, multi-head attention works. And then we can come back and look at the entire architecture of the transformer once more. But the basic idea here is that you create something like an attention matrix. So if we have words like the, cat, sat, on, the, we create something called as attention score, which will look something like this: cat, sat, on, the. So there are 5 tokens, and you will have attention scores for each token corresponding to every other token in the sequence. Not just every other token, it's also looking at itself. Now the attention scores will depend on the dependency between two words. So the word sat might depend heavily on cat. So this attention score might be high, this guy. But the word sat is not really paying attention to the word the. So maybe this might be small. The word sat is maybe paying a lot of attention to the word sat itself. So maybe this might be something like this. And so on. this the and this the are not necessary for paying it, not really required to pay attention to each other. Maybe this is small. So like this, you can construct, and these will be numbers inside this 5 by 5 matrix, which are called as attention scores, which you can modify to create something called as attention weights. But we'll discuss this in detail in the next lecture. For the moment, just understand that what this multi-head attention does is it tells the neural network how closely each tokens in a sequence are attending to each other. And then you have a feed forward neural network. So what happens to this input embedding is by the time it passes through here, it passes through multi-head attention, it passes through dropout. By the time it reaches, layer normalization, and by the time it reaches the feed forward neural network, the numbers inside the original input embedding would have definitely changed. However, the dimensionality will still remain the same. It will still be a 768 dimensional vector. Now, something happens to this vector inside the feed forward neural network, and that something is really fascinating. So what is done in the feed forward neural network is you simply project this 768 dimensional vector into a space that is 4 times as big. In GPT-3, it is actually projected from 12,288 dimensional space into a space of size 12,288 times 4. So 4x bigger space. And then you project it back into 12,288 dimensional space. In this case, you project from 768 dimensions to 768 times 4. Then you project it back into a 768 dimensional space. And these projections are interesting. These are simple mathematical operations. So if you have a vector of, let's say, dimension 768 times 1, and or you can, in the way I have written it, it should be ideally written as 1 by 768 because I have written it like a row. So 1 by 768 is the dimension. I want to convert this into something of the dimension 1 by what is 768 multiplied by 4. 768 times 4 equal to 3072. So 1 times 3072. And then I want to bring it back to 1 times 768. So the way this can be done is through this neural network. This is the feed forward neural network. And what is happening in this neural network? Simple matrix multiplication. So this is multiplied by a matrix of dimension 768 by 3072. And what are those matrix? The numbers inside that matrix? The numbers inside that matrix are these weights in these connections. So the 1 by 768 matrix is multiplied by this matrix. So what will be the output dimension? If you multiply two matrices, my dimension of first matrix is this, second is this. The output dimension will be this multiplied by this, right? 1 times 3072, meaning 1 row and 3072 columns. And what is this 3072? It is the number of nodes in the intermediate hidden layer. So the reason why this is done is because if you have a vector representation of data in a very high dimensional space, it means you can capture more abstractions or more feature rich. Higher dimensional spaces are more feature rich because each dimension can act like a feature. So by projecting the 768 dimensional vector into a space of 4x the size, you are hoping to make the vector look at directions in that bigger space so that you can recognize more relevant features. So you are this is not encoding. If you were encoding, you might be projecting into a lower dimensional space, but it's almost like that. It looks like it's not exactly like an auto encoder, but something like that. You are projecting it into a higher dimensional space, and then you are projecting it back into its original dimension. So by the time this transformation happens, the features inside these vectors, meaning numbers inside each of this dimension, would have become something more richer in context. And if you actually think about the number of parameters in your neural network, actually GPT-3 has 175 billion parameters. I will talk about this in another lecture, but you will see that roughly 2/3 of the parameters, you might think that most of the parameters are coming from multi-head attention because that is a great innovation in GPT. But if you will be surprised to know that roughly 2/3 of those parameters are attributed to this simple feed-forward neural network. Only 1/3 of the parameters, roughly 1/3 of the parameters are only attributed to the multi-head attention. It's fascinating. So we can do the exact calculation, which we will be doing in one of the future lectures. But this is the purpose of the feed-forward neural network. You make the features inside the 768 dimensional vector, which represents the transformed embedding. You make those features a bit more richer. So now let's take a step back and look at the entire architecture once more. But before going into that, I want to talk about one more thing. We know that in multi-head attention, there are multiple attention heads stacked in parallel. But in addition to that, these transformer blocks themselves. So this is one transformer block, right? And the original in this original diagram, I just had one transformer block I had drawn. But like this, there are 12 transformer blocks in series if you are looking at GPT-2 small model. If you are looking at GPT-3 model, you had 96 such transformer blocks in series. In GPT-3, you also had in each transformer block, you had 96 attention heads in parallel. We are not yet discussing the multi-head attention heads yet, but just know that there are two numbers. One is the number of layers associated with the multi-head attention. So those layers are parallel. You can think of it like a stack here itself, and it is within an individual transformer block, but there are these transformer blocks repeating. So let's say this is transformer block 1. This whole thing, okay, this whole thing in this gray box is the transformer block 1. Then you have transformer block 2. Like this, in GPT-2, there are 12 blocks. In GPT-3, there are 96 blocks. So that is what I have drawn here. The token, by the time it exits one transformer block, it is time for it to go through 11 more such blocks. So it's like huge processing. A lot of things are going on. And when I mentioned earlier that 2/3 of the parameters are belonging to this feed-forward neural network, I mean to say 2/3 of them are belonging to all feed-forward neural network of every single transformer block combined. So if there are 12 transformer block, the feed-forward neural network in one transformer block will attribute to roughly 2/3 divided by 12. That many parameters, roughly. Similarly, the multi-head attention in one transformer block will attribute to roughly 1/3 of the parameters divided by 12. If you have 12, if you are looking at GPT-2. If you are looking at GPT-3, each transformer block will attribute to roughly not transformer block. Each feed-forward neural network will attribute to roughly 2/3 of the parameters divided by 96, because you have 96 transformer blocks in parallel. 2/3 of the parameters divided by 96 of what? Of 175 billion. These many parameters will be present in the feed-forward neural networks. And if you are looking at the multi-head attentions in 96 transformer blocks, they will attribute roughly to 1/3 of 1/3 divided by 96, because in each block you are having that much parameters multiplied by 175 billion. So it's fascinating to understand that this feed-forward neural network plays a big role in the entire transformer architecture. Now let's zoom out on the transformer block and see the individual items. So you have two places where you have layer normalization, where you are normalizing the inputs so that the mean is 0 and standard deviation is close to 1. And then, of course, you are scaling it and adding a bias, which are trainable parameters. You have dropout at two places to prevent overfitting and to also encourage lazy neurons to learn useful things from the data. And you have skip connections, which I haven't drawn here, but it is understood. It looks something like this. You have skip connections to reduce the issue of vanishing gradients. And then you have feed-forward neural network to enrich the features by projecting into a higher dimensional space and projecting it back into its original dimension. These many things happen inside one transformer block. And like this, there are 12 transformer blocks in GPT-2, 96 in GPT-3. Now let's come back to our architecture. We discussed about the input part. We discussed about the transformer block part. And now the last and final thing is the output part, the third block. Let's see what happens now. So what comes out of here is still the transform token. So the token corresponding to cat, which we were looking at, it has now transformed to something here, right? But it is still of the dimension 768. So it's still a 768 dimensional vector. And there are two things to discuss in the output. One is a layer normalization, which is exactly same as the layer normalization that you saw earlier. And another is the output layer. So layer normalization simply does this, x minus mu by sigma, and then it would be multiplied by some trainable parameters, beta plus gamma. But this you forget for a moment. Basically understand that by default, what the layer normalization is doing is you reduce the mean to close to 0, reduce the standard deviation to 1. So this part is already discussed, so I don't think we need to go into details more. Now output layer is interesting. What is happening in the output layer? We have a 768 dimensional thing coming out of this final layer normalization. But at the output, whatever we get, we should be able to predict what is the next word. And where are we going to predict the next word from? We are going to predict from the dictionary, right? Because in our vocabulary, we have 50,257 words. And we are going to predict the next word from that only. So at the output, something should tell me, hey, with 80% probability, the next word carries an ID of 7,468 from your dictionary. So check for that item. Something like this, I should know. So what that means is whatever we get out of the output should have a dimension of 50,257. Correct? Because then in that, I can, whatever I get out of this, I can pass through Softmax and create a probability distribution. So let's say this is 50,257 dimension. Then I can look at whichever item has the highest Softmax probability. So let's say this number is 0.8. I can say that, and if this is 7,847, I can say that this item has the highest probability. Which one? 7,847th item. It has 80% probability to be the next word. And what is that item? Go back in the dictionary and check. And if you look at the dictionary, maybe it will turn out to be the word, the ID might match with the word mat. This is how next word prediction is made. So what happens here when you go through the output layer? What exactly happens there? You already know what happens there because you saw something very similar in the feed forward neural network. So what happens is you have a projection layer where the 768 dimensions are projected to 50,257 dimensions. So this is 768, 50,257. Now again, what kind of matrix can do this? If you are going from 1 by 768, if you are going from this dimension to 1 by 50 to 57, the kind of matrix that can do this will have a dimension of 768 by 50 to 57. Because when you multiply this with this matrix, your resulting dimension will be 1 times 50 to 57. And what is this matrix? This matrix is nothing but the weights in this neural network. It's simply a projection layer. You are projecting from a 768 dimensional space into 50,257 dimensional space. Now you might be wondering, what are these numbers? These weights, what are those? They are trainable parameters which will be trained during the process of pre-training the transformer. So in GPT, which stands for Generative Pre-trained Transformer, these weights are already predefined for you because OpenAI has spent millions of dollars in doing that. So in the projection layer now, the final output may look something like this. Something like this item. The next word should be this item in the 50,257. And whatever is the ID of this item, you go back to your dictionary and check. So how exactly are we doing the next word prediction? We can do this for every token, right? We can have a next word prediction for we can have a next word prediction for cat. SAT can have a next word prediction, because we did not discriminate on tokens. We just said currently we are looking at the token cat. We did not look at the final token the. But there can be a next word prediction for the. And the ground truth for the token called the is something that we already know. If in this particular context, if the if the input is the, ground truth should be cat. Why? Because it is the actual next word coming in the sequence. This I'm talking about training. I'm not talking about inferencing right now. I'm talking about while training the neural network. If you have one sentence called the cat sat on the, it's not just like you are trying to predict this one mat. It's not like you have one input sequence and one output. You have multiple inputs. You can consider this to be an input and this to be an output. You can consider these two to be the input and this to be the output. You can consider these three to be the input and this to be the expected output, and these all to be the input, or all of these to be the input and this to be the output. And similarly, all of these to be the input and this to be the output. So it's called self-supervised learning. You don't have explicitly labeled data set, but just by the fact that you have a sequence like this, the next word, which can be cat or sat or on or the, mat, etc., they themselves form the supervised learning data set. So what will happen in neural network training is that initially, although the next word that you are supposed to predict in this sequence is cat, the neural network may predict boy. And because of this, there is loss, right? Because the predicted sequence, predicted token and actual ground truth token are two different things. Vectors, they are two different vectors of 768 dimensions. And now you can construct a like a loss function. And based on that loss, you can perform backpropagation and modify all the weights, all the 175 billion parameters. Not all of them, but you can modify all the trainable weights in your neural network, right? And if it is a properly trained neural network, it may predict something like mat as the next token. It can predict chair also, which is why you will see hallucinations. Neural network next word predictions are not always the same. The same sentence, if you input and if I input, we'll get two different output, because there is a probabilistic nature with respect to selecting whether I should always select the highest probability token or not, right? Here, the token with 80% probability is this, but there are still tokens. Maybe this guy has 10% probability, and this might be the token corresponding to chair instead of that corresponding to mat. So maybe there is also a chance that the next word in this sequence could be the cat sat on the chair instead of the cat sat on the mat. So this is how the next word prediction in the transformer architecture happens. Basically, next word prediction in large language models. So let's now take a step back and let's look at the output part alone. So in the output part, we have layer normalization for changing the mean close to 0, standard deviation close to 1. Output layer is a projection layer where 768 dimensions are projected up into 50,257 dimensions. And those numbers are logits which can be converted into softmax. And the final probability, final word selection will depend on the probability distribution of the next word. And maybe the next word that is picked is mat. It could become chair depending on whether you are actually picking the highest probability next word or second highest probability next word, etc. So this is how the next word prediction task works in large language models. Now let's take one step back to see the entire architecture. This is the entire architecture of a large language model, where the only thing where we did not spend too much time is the multi-head attention, and it is indeed probably the most complicated and most important part, which we will come into in the subsequent lecture. But other than that, we looked at the transformer architecture pretty much in detail, and we decided to look at it in 3 blocks. We looked at it in input block, then transformer block, and output block. In the input block, we saw that you can convert the input sequence into tokens, and then you convert the token into embedding, and then you add the positional embedding to the input to the token embedding to produce the input embedding. Whatever comes out of here is the input embedding. And it had 768 dimensions if you are considering GPT-2. Now that goes into a transformer block where a bunch of things happen. You first have layer normalization, then you have multi-head attention, which produces the attention scores and then finally attention weights. Then you have dropout to prevent overfitting. This happens 2 times. And then there are skip connections to reduce vanishing gradient. And this also happens 2 times, these skip connections. And you have feed forward neural network, which is actually very important and crucial. In fact, as I mentioned, 2/3 of the parameters are attributed to these feed forward neural networks. And then you have an output. We also discussed that there are 96 such transformer blocks in series in GPT-3, and there are 96 attention heads in the multi-head attention of every single transformer block in GPT-3. In GPT-2, there are 12 such in series, and we can also ask how many attention heads in GPT-2 multi-head attention. Okay, so 12 attention heads per layer, and like that there are 12 in series. So this is the GPT-2 small model, okay, 117 million parameters. On the other hand, and for GPT-3 large model, it will be 96 and 96. So not the small, this one, GPT-3, yeah, this one. 175 billion, there are 96 attention heads in every single transformer block, and like that there are 96 transformer blocks, or 96, it's called layers also. Then in the output, what happens is you have the final embedding called context vector coming here of 768 dimensions that undergoes layer normalization. Then after layer normalization, it undergoes a projection into 50,257 dimensional space. And then you can calculate softmax probability distribution and pick the next word prediction. And next word prediction is picked based on if let's say the output says the word of this ID, let's say ID number 37568 has the highest probability with 0.7 percentage, 70% probability, then you look at, which one is this word? You go to your dictionary and check which one is the word. You see that word corresponds to mat. That ID corresponds to the input embedding of, token embedding of mat. Then you say next word is mat. So this is what happens in the entire transformer architecture. So I hope you got a good overview about what happens to a token, individual token, as it passes through the transformer architecture. I'm pretty sure that since the information or content is so dense in this, you might require to watch and go through this multiple times. I highly encourage you to do so. If you are listening to these concepts for the very first time, you will definitely require to spend, you'll be definitely required to spend more time. So I highly recommend you do that. Take notes, and in one of the upcoming lectures, I will discuss exactly how these 175 parameters are distributed in the model architecture. That way you will exactly understand how the transformer architecture works in a little bit more close, numerical fashion. But before going into that, we will also spend significant amount of time on multi-head attention, which we did not spend too much time on in the current lecture. But I want to spend time on the attention mechanism itself, called the original attention mechanism was badano attention. Badano attention in 2014. Then I want to discuss about self attention mechanism, which was introduced in the Attention is All You Need paper in 2017. And in the same paper, there were ideas like causal attention. These words may make it sound like it's a big deal, but once you understand what's going on, it's easier. And then, of course, multi-head attention. Then there were other concepts like latent multi-head attention, multi-head latent attention, flash attention. There are many, many concepts. If you ask ChatGPT the number of attention types existing, there are 50 plus. Like, we can just ask, how many types of attentions are there? Give me a list of names. There is no official list, but yeah, additive attention. Yeah, this is the badano attention which I mentioned, but there are many types of attentions. You will see that some of them are very famous. All right, so I think we can wrap up the lecture today. But you will have a fairly good understanding about multi-head attention in the upcoming lectures. But I hope this diagram serves as a very good overview for you to think about the LLM architecture. It looks complex, but the more time you spend on it, you will understand more and more how exactly it works. And ultimately, the reason why I'm teaching you all of this is so that this will come handy when you are trying to understand the structure of vision transformer, right? Here we did nothing with respect to vision, although we are in the transformers for vision course. But whatever you learn today, a lot of things will carry forward when we discuss about vision transformer architecture. So please try to understand this lecture material very deeply, and I will see you again in the next lecture. Take care. Until then, bye. Hi, welcome to a new lecture from Transformers for Vision. Today we will discuss about the evolution of attention mechanism, how we went from encoder-decoder mechanism in recurrent neural networks to badano attention, which was introduced in 2014, and then from there in 2017 self-attention mechanism was introduced in the paper Attention is All You Need. And attention mechanism has revolutionized not just natural language processing but also computer vision. In the previous lecture, we discussed how long-range dependency can be captured very well by using attention mechanism in big sentences or big paragraphs, where the first word in the sentence and the last word in the sentence could be highly correlated, although they are far apart. Same phenomenon can happen in images where a patch of pixels, let's say at the top left corner, and a patch of pixels at the bottom right corner can be highly correlated, and you want to capture that long-range dependency. And attention mechanism is the mechanism which can do that for you. So this lecture has a very important context in the current course. So let's get into the lecture. So you might have heard of this term sequence to sequence models, where you can input any kind of sequence. It can be words from sentences. It can be just letters, or it can be features in an image, and a sequence to sequence model can convert this into another sequence. So this was primarily, at least in the beginning, used for language translation, because translation is simply converting one sequence into another. So this is a sentence, this is a car, it's a sequence of words converted into the French version. So this sequence to sequence model for neural machine translation was very popular, and it indeed worked very well for small sentences. It of course had some issues when you had large, long sentences, which we will discuss why in a moment. But let's first try to understand how did this sequence to sequence model work? What was underneath inside this sequence to sequence model part? So this neural machine translator was basically an encoder-decoder architecture. You will come across these two terms also in the context of transformer. The transformer architecture mentioned in the Attention is All You Need paper had an encoder-decoder architecture. So if you open the paper, Attention is All You Need, and if you look at this figure, the left-hand side is encoder-only architecture like what you see in BERT models. The right-hand side is decoder-only architecture, which you will see in models like GPT. So here also you can see the encoder-decoder architecture. You will see something like this also in the model called UNet. So UNet was a semantic segmentation model. And in UNet also you will see similar encoder-decoder architecture where you are converting an input image, or you are encoding an input image into smaller spatial dimension and more number of channels. And at the decoder, so this is the UNet. It's named so because its shape is like a U, and the left arm of the unit is encoder, the bottom part is the bottleneck, and this right arm is the decoder. So the idea of encoder-decoder architecture you will come across this idea in many different contexts. And the input to the encoder is this English sentence, this is a car. Output from the decoder is the French translation of that. I don't know how to pronounce this really well, so I'll not attempt it. So now let's see what is there in the encoder and what is there in the decoder, and how does encoder communicate to the decoder, because something has to go from encoder to the decoder for decoder to provide you the final translated output. So let's see how this works. And once we understand how this works, we will also understand what was the shortcoming of this kind of a model and how attention mechanism evolved as a natural consequence. So let's focus on just the encoder part. So here I am isolating only the encoder. Let's forget about decoder for a moment. What the encoder does is, given an input sequence, and why do I call this as a sequence? Because you can consider a sentence as a sequence of words or a sequence of tokens, however you want to split it. But let's say for simplicity, you are splitting a sentence into words. So this is a car will be this is a car. So a sequence of 4 words. So these words are input into the encoder sequentially. And at the end of this sequence, what the encoder outputs is something called as context vector. So this context vector is one single output vector. And why do I call this as a vector? Because it has n number of dimensions. So let's say it has 768 dimensions. This number is not exact. I'm just giving an example. Then basically what this vector is doing is, whatever information is contained in this input English sequence, this one single vector is trying to capture the entire context of that sentence or the entire meaning that is there in that sentence in just one vector. So this context vector came out as the output from the encoder. And then what you will do is you will feed this context vector into the decoder. All right. So the input sentence does not go directly into the decoder. It is encoded into the context vector format. And then the decoder will try to convert this context vector into the final target language. If it is French, it will be looking like this, 3 words in French. These output words are also produced sequentially, just like how input was coming in sequentially into the encoder. So if there are 3 words, it will be produced one after the other. But to produce these 3 words, your input into the decoder is just this one single context vector. So now you can imagine what is probably happening here. You have an input sequence in one language. You are converting it into an abstract representation in the form of context vector. Then that abstract representation, you hope to capture some meaning in the input sentence. But this abstract representation is not in any language. It's in the language of mathematics. It's just numbers. And then from that abstract representation, which is the context vector, you try to convert it into the other human language, which is French. So this is what decoder does. So you can think of encoder converting your input into another space, another vector space, and then decoder converting it back from that vector space into your French language. So this is a simplified version of how encoder and decoder works. Now we have to go into detail one more level. Okay, what exactly does encoder do to produce this context vector? So this is the next question. How do you go from this input sequence in English to this context vector, which is a mathematical abstract concept? How do you go to this? So what is done is, first, your words are converted into vectors. So words, this is a car. So these individual words are converted into 4 input vectors. Now these are again mathematical representations of these words. This is a car will have 4 different vectors, and usually these vectors carry meaning. So we can draw something like the feature space. So let's say there are 768 dimensions for this vector. So meaning this is the first element, second element, like that 768th element. 768 is a number just that was used in GPT-2. That's the only reason I'm mentioning that number here. It can be anything, right? Depends on the word to vec conversion. But let's say the idea is that this is dimension 1 of the vector. This is dimension n. The value of n can be anything. And then you will have a vector pointing in this direction. Maybe this is apple. You will have a vector pointing here. This could be orange. So now these 2 vectors are pointing into kind of similar regions in space that carry same semantic meaning. So this is the semantic space for, let's say, fruits. So these vectors, when you are encoding the English word into a mathematical vector, those directions, the vector directions will carry certain meaning. On the other hand, if you have two vectors, let's say one for dog and one for cat, now these two vectors are pointing into another direction of space whose semantic meaning, or this semantic space, may be for animals, right? So if you generally look at the vectors for cat, dog, or other animals, it will, along certain dimensions, it will point to some region of the space, whereas some other vectors for fruits may point to some other direction of space along some dimensions. So this is the idea of converting words to vectors. So words carry meaning, right? For humans, words carry meaning, but just like that, these vectors also carry meaning. It encodes the semantic meaning of those words. They are not random numbers. Now, once you have these four vectors, you have input vector 1, input vector 2, 3, 4, right? Now you have a sequence of 4 vectors. Now, these sequence of 4 vectors are fed into the recurrent neural network. So encoder is basically a recurrent neural network. You call that as a neural network, but it recurs, so it has time steps. So what I have drawn here is the 4 time steps that this recurrent neural network goes through, because there are 4 words in the sequence. So it may look like as if there are 4 RNNs, but there are no 4 RNNs. There is only one recurrent neural network. But I have just drawn the 4 different time steps as 4 repeating RNNs. So let's just focus on this part for now. Just focus on inside this rectangle. Okay. So a recurrent neural network has an initial hidden state. Hidden state is also a random vector. So we can call this as vector number 0 as the initial hidden state before it gets any input. Then this hidden state, along with the first input vector corresponding to the word this, is fed into the RNN. So this is the RNN, this red color circle. Of course, it's a neural network, so this is not the representation of RNN. It's just a block which I have created to say that it's an RNN. So in the first time step, you have the word this, its corresponding input vector, and then the hidden state vector, you can call it as vector number 0 or hidden state vector 0, and entering into the RNN. And what the RNN outputs is the next hidden state. So this hidden state is not the final output from the RNN. It is the context vector. So you are still in the time step number 1. You just got the first hidden state. Now what happens is this first hidden state vector is fed into the RNN in time step 2, along with the second word in the input sequence in the form of a vector. So vector number 2 is the vector corresponding to is. Now this hidden state vector 1 and input vector 2 will go into the same RNN, but I just copy pasted the same image here to show that it's time step 2, but actually it's the same RNN, okay? Don't think that there are multiple RNNs. It's only one RNN, but it's taking this this output as the input in this step again. You can draw it something like this, but then it will look ugly. So that's why I chose to draw it like this. Then this will output the next hidden state vector number 2. And then you will have input as the third word, the input vector number 3. And then this will output the hidden state vector number 3. And then you might guess what will happen in the next step, which is the most important step probably. You have hidden state vector 3 and the last word in the sequence in the form of vector entering into the same RNN in the last time step. And then the vector will output the final context vector. The RNN will output the final context vector. So this final context vector would have been a next hidden state if there was one more word in the sequence. But because there is no more words in the sequence, this final context vector is now the vector that encodes the information in this entire sequence, right? So the vectors before that, the hidden vectors before that, the hidden vector 0, 1, 2, and 3 do not come out of the RNN. What comes out of is the last sort of hidden state, but it's called as the context vector. Now, decoder, what it does is it takes this particular output from the RNN in the encoder as the input. And decoder has only one input, right? At any given point of time, you are not giving an input sequence to decoder. You are giving the context vector to the decoder. So from the context vector, Decoder produces two output at a given time step. Decoder is also an RNN, but instead of having two inputs and one output, this will have two outputs and one input. The first input is the context vector. From the context vector, it will produce the first word, which is the output, in the form of output vector. And this output vector you can map to the word. So you will have a dictionary. In this dictionary, you will have all the possible words with the corresponding IDs of the vector. So let's say this vector maps to one particular word. Then all you can do is, you can just check. So if this vector is like in a certain format, so whatever vector this RNN outputs should be a vector that corresponds to one particular word, right? And then it will, in the dictionary, this vector will map to one particular word in the English language. So that will be the French translation. If the RNN is properly trained, it will be the French translation of the input sequence. And then it also outputs one more thing, which is the next hidden state vector. So this is the input context vector. This is the first output, but then the second output is hidden state vector. And this hidden state vector itself will be the input to the next time step. So effectively, if I want to draw this as a recursion, this I can just draw back here. So this guy will come back here as the input, and then it will produce the next word in the sequence as the output. So this is the output vector number 2 converted into French equivalent. And then it will produce one more hidden state vector. And then this hidden state vector will be the input to RNN once again. And then it will produce the final word in the sequence. And then you don't have any more hidden states, because this is the last word in the sequence. Now, please note again, these are different time steps, but it's only one RNN. So if we were to draw this, something like this can be drawn. So you have initial input coming to the RNN. It's producing the output sequence, first word from the output sequence. Second output is the next hidden state, but then this is going back as the input, something like this. So this diagram is not that intuitive, which is why I prefer different time steps drawn as different RNNs, although it's the same RNN. So this is the detailed encoder-decoder architecture in the RNN. So English sentence will go here. English sentence will be converted to, if there are 4 words, it will be converted to 4 vectors. All right. Then the first vector will go here as the input along with the hidden state. Then it will produce the next hidden state. Then the second vector will go here along with the first hidden state to produce the next hidden state, and so on. So this is how the neural machine translation in encoder-decoder architecture of RNN was working. But this has one problem. Just think about what is the main problem here. The main problem here is you are forcing this context vector to somehow magically capture the entire context in your sequence. The entire meaning in your sequence is now expected to be captured by just this one context vector. You are putting too much pressure on this vector. And what if your sentence was very long? The dimensionality of this vector remains the same, but then this very extra long sentence with, let's say, 15 words, you are somehow expecting this last context vector to capture everything in that sentence. But that's too much pressure on just one single vector. And that was one major problem with respect to RNN. We are relying entirely on this one vector to encode the whole information in the input sequence. So this was okay as long as the sentences you are translating are small. Because, for example, see the sentence example that we used. This is a car. It's a small sentence. So for these kinds of sentences, it's okay. But consider if your sentence was something like this. The teacher who was teaching a difficult concept smiled. Okay, this is a much longer sentence compared to the earlier example. Now look at these 3 words. Okay, sorry, there is one more word I have to write here. This difficult concept to the students smiled. Okay. Now consider these 3 words: teacher, students, and smiled. So usually in small sentences, if you look at this example, the cat sat on the mat. In this sentence, you have cat the cat is performing an action, and this action is performed on the mat. So all these three words are related, and it's a small sentence. So RNN probably won't struggle to capture the meaning from this sentence that cat is the one who sat on the mat, not somebody else. Here, on the other hand, just check this. You have students, you have smiling, and you have teacher. But actually, who smiled? Did the student smile or did the teacher smile? Actually, teacher is the one who smiled. Teacher who was teaching the concept to students smiled. But from the structure of this sentence, it's very confusing. I mean, for humans, it's fine. But for a computer who is relying on these or who is looking at these words as sequence, in the sequence, you can see that the word students and the word smiled are very close to each other. So it's very difficult to teach a neural network that actually in this particular case, in this context, students did not smile. It's actually teacher who is smiled. And this is called long range dependency. So here the dependency is short term. Cat and sat are next to each other. Sat and mat are also not too far away. But here smiled is at the far end of the sentence. Teacher is on the other end of the sentence. So smiled is on the rightmost end. Teacher is almost on the leftmost end. So these are called long range dependencies, and this is a problem. So long range dependency capture was a problem with the encoder-decoder architecture in RNNs. And this problem exists primarily because in the decoder, it has only access to the last context vector. Decoder cannot look back and look at the hidden states, the previous hidden states of the encoder. Decoder is not allowed to see that. Decoder is only allowed to look at the last hidden state or the context vector. But what if the decoder also had access to the previous hidden states, all the previous hidden states? Then maybe you can somehow teach the decoder to pay more attention to, once you encounter the last context vector, you can ask the decoder to pay more attention to this word teacher, the word students, and the word smiled, instead of just paying attention to the more recent words in the sequence, right? Because you have access to the encoder, the hidden states from the encoder before the final context vector. So this was an idea which was for the first time introduced in the paper, which was the first attention paper, which later came to be known as badano attention due to the name of the first author. This paper is super famous. It has 40,000 plus citations. This paper came out in 2014. So what this paper said is, we can assign an attention score to different words in the input sequence. So for example, if the next word that is to be predicted in the output sequence of this is a car. Now let's say this sequence is converted through encoder into hidden states and then to context vector, and then you are entering the decoder. And when you are producing the first output word in the output sequence, how much should this output word depend on this word in the input sequence? How much should it depend on this? How much should it depend on this and this? So instead of the next word in the output sequence depending just on the context vector, you are also making it dependent on all the previous hidden states in the encoder. So this was the basic idea behind the attention mechanism. And this had far-reaching consequences. So for example, if you look at the translation of the word European Economic Zone, right? If you translate this to French, you will see that zone is coming last in English, but in French, it's coming first. And European is coming first in English. In French, it's coming last. Economic, that word has the same location. So there are issues with respect to different languages where the actual physical position of words in one language and the physical position of the corresponding word in the other language may be completely opposite. So this, for capturing this, so now if you are trying to predict the word European, right, the third word in the output sequence, it should probably spend most attention to not the last word in the sequence, but the first word in the input sequence. This European should ideally pay most attention to, or it should attend mostly to the European word in the input, which is the first word in the input sequence. But this European in French is the last word in the output sequence. So this is a classic example why you need some sort of an attention mechanism. So the Badano attention paper shows a very nice figure like this. So see the arrangement on the European Economic Area. So here this matrix represents the attention between the output sequence and input sequence. So let's say the input sequence is French and output sequence is English. So this is, let's say, input. And this is output. So input is, you can read it from here, and this is the end, which means you have ended the input. This is the end for output, which means you reach the last part of the output. And you see this area, European Economic Area, these three words. And here, Zone Economic European. So this zone pays most attention to actually this area. So which is why this cell has the brightest color. Economic attends mostly to economic, this one, and European attends mostly to European. So here the order in which European Economic and Area appears is 1, 2, 3. Here on the other hand, it's 3, 2, 1. And which is why here it's as if you have a transpose. So if language number 2 had all the words in the reverse order, this matrix would look like a transpose matrix with all the other diagonal elements to be white in color. But rest of the words are kind of following similar sequence as that of English, as that of French, which is why the bright color cells are all along this main diagonal. However, there are words in the French language which flips with respect to words in the English language, like this European Economic Area, which is why this other diagonal, the second diagonal of this square, is having brighter color. So this was the figure introduced in Badano attention, which very nicely captures the concept of attention. How much should each word pay attention to other words in the sequence? So you can also see how much this word's zone pays attention to the word called economic, or how much it is paying attention to the word the. It's not paying any attention to that, which is why it's dark in color. So this word, zone is not paying any attention to agreement or any attention to on, the. With European also very little attention. Most of its attention is paid to these two words, economic and area. Similarly, the word economic is paying most attention to European and economic. Similarly, European is paying most attention to European itself, not any other words. But there are some words which are paying slight attention to multiple words. So this dot, which is the period character, is paying most attention to period in English, which is this, but you can see that there is some attention paid to some of the other words also, was, signed, in. So you can see many different interesting characteristics of two languages, how they correlate with each other from just this one visual. Now you might see same image or similar like looking image in the context of self-attention mechanism, which we won't be discussing in detail in this lecture, but I have reserved lectures in the upcoming future lectures of this series, where you will see something very similar, but this time you won't be looking at separate input and output sequences. You will be looking at same sequence, and you will be asking question like, how much attention does this word area pay to all the words in the same sequence? How much attention does this word signed pay attention to all the words in the same sequence? So this Badano attention, this attention matrix need not be a square matrix, because the number of words in the French language and the number of words in the English language can be different. So this can be a non-square matrix. But in self-attention, the sequence is paying attention to itself, which means the number of words in sequence number 1 and sequence number 2 are the same. So it will look like a square matrix. Now, did this come all at once? So what was the timeline of evolution of these models? So RNNs was introduced in 1980. So it's good to have this picture in mind. And LSTM is long short-term memory, which was, I would say, a much more complex version compared to RNN in 1997. And then in 2014 is when the attention mechanism or Badano attention came, and then came the self-attention mechanism in 2017. Now, in the context of this course, since we are interested in vision, the next part of this timeline would be 2020. Which is when the transformer architecture introduced in this paper was also used for vision. So this was the vision transformer. So this is a timeline which you should definitely have in your mind if you want to know how the field of AI evolved with respect to attention. Now, I won't be going into the details of badano attention, how exactly it is calculated in today's lecture, but I will wrap up the lecture by just mentioning a couple of differences between badano attention and self-attention. So in badano attention, it was introduced so that the decoder in the RNN of the neural machine translation can actually get access to not just the final context vector coming from encoder, but also the other hidden states from the encoder. So basically, badano attention is a much stronger link between decoder and encoder. And if you look at the sequence, it will be in two different languages, or it need not be the same sequence paying attention to itself. So it's not self-attention. It is attention between input sequence and output sequence. Now, you might be wondering, is the neural machine translation or is the encoder-decoder kind of architecture with badano attention only used in translation? Not necessarily. It can be used for paraphrasing. It can be used for chat. So the applications of recurrent neural networks was, there were a vast variety of applications. However, we are just talking about translation mainly because it's a natural consequence, right? Translation is like basically you are having an input sequence, you are converting it into another language. So naturally it follows one sequence converted to another sequence idea. That's the only reason why we are talking about translation right now. But badano attention links two different sequences. The input sequence is linked to output sequence to know how much attention should each word in the input sequence pay to the other words in the output sequence. And here you see this is the classic example. See how the color here is distributed. It's not along the main diagonal, it's along the other diagonal of this matrix to show that actually the words are reversed in this context. The input words in French and the output words coming out in English are exact opposite, if you look at it meaning wise. On the other hand, in self-attention, you see the words in the input sequence and the other sequence are both the same. And in self-attention, you are not converting one sequence to another necessarily, but rather you are generalizing the principle of badano attention to say that actually within the same sentence itself, you can produce attention score. For example, if the words are Americans speak English, maybe the word English pays highest attention to Americans, maybe, right? The word speak does not carry too much attention with respect to itself or with respect to the other words. As long as Americans word is there, it will pay more attention to English, and English can pay more attention to American. So most of the context is probably embedded in those two words. And if we go back to the example of the teacher teaching students smiled, where is our sentence? Yeah. So in this sentence, if we were to discuss about self-attention, the word smiled might pay the highest attention to the word teacher. The word students may not pay that much attention to smiled because they are not correlated that much. Teacher may pay very high attention to teaching, but teacher may not pay too much attention to, I guess teacher in this context is paying attention to most of the words. Difficult word may pay most attention to the word concept because concept is being difficult. Students are not being difficult. Smiling is not difficult. Teacher is not difficult. Concept is difficult. Now, this we can also represent the idea of badano attention in the context of encoder-decoder and self-attention. We can represent in this form. So here, let's look at the encoder-decoder format once more. You have the hidden state H0. Okay, so this part is the encoder. This red color blocks, these are the encoder. Green color blocks are decoder. Hidden state is coming and first input vector is coming. Then H1 is produced. But H1 is made accessible to decoder, not just the final context vector. Then you have H2 produced using H1 and using the next input, which is the vector corresponding to the word economic. Then you have H3, which is the third hidden state produced using H2 as the input and the third vector corresponding to zone as the input. And please note, these are different time steps. These are not three different recurrent neural networks. Now, because we have now badano attention, you can create attention score. So alpha 1 1 means how much does the first hidden state pay attention to the first state here in the decoder. How much does the second hidden state pay attention to the first word in the decoder? And how much should the third hidden state in the encoder pay attention to the first state in decoder? So this state in the decoder is having access to every single state hidden state in the encoder, and there are corresponding attention scores. So these are alpha attention scores. Or you can also call it as relative importance. How much importance should the first hidden state in the decoder pay attention to the previous hidden states in the encoder, not just the context vector. Of course, context vector is coming as the input here. This is the final context vector, but there is also access to the previous hidden states. And this applies to state 1, state 2, state 3 of decoder to produce the final output. Now, mathematically, how does this play out? We will discuss in the upcoming lecture, but I just want to give you a conceptual clarity right now. And similarly, in self-attention, it is, so tomorrow it will rain. So let's say this is the sentence. Okay. And now you are looking at the word rain itself to see how much attention it pays to all the 4 words in the sequence. You have tomorrow it will rain. So here we are not talking about badano attention anymore. We are talking about self-attention. So now the word rain may pay the highest attention to this word tomorrow, because tomorrow is when it is going to rain. So I have drawn this black dot to signify the attention score itself, but it may be paying, the rain word may be paying very little attention to the word it and the word will, and it may pay very high attention to rain also, right? So these black dots show how much attention does each words in the sequence pay to the word rain. So here rain, because you are looking at rain and you are looking at the rest of the words and how much attention is there between them, rain is called as the query. Rest of the words are called as the key. Now, using these attention scores, you can produce a more context rich vector, which will take these, or which will factor these attention scores into account. We will see how mathematically it turns out in the next lecture. But basically, the goal of this attention mechanism is to produce a vector, context vector, that is much richer in information, right? So this is how the self-attention and badano attention came into picture. But we have to discuss a little bit more about how do you go from these input vectors and from these attention scores to a context richer or richer context vector. So let's discuss that in the upcoming lecture. So I hope you understand now the significance of attention mechanism, not just in the context of neural machine translation, which of course it was very important because of introduction of badano attention, but also the importance of self-attention because it generalizes the principle of badano attention. You are not looking at 2 different sequences. You are looking at the same sequence and how much importance does each word in that sequence play to its own words. So with that, let's wind up today's lecture. We'll meet again in the next lecture where we will go into the details of how do you create the context vector given you have attention scores and given you have the input vectors. So thank you so much. Take care until then, and bye. Hi, welcome back to a new lecture from Transformers for Vision series. Today, for the first time in this series, we will dive deeper into the concept of self-attention. To simplify our understanding, we will be considering self-attention mechanism without any trainable weights, and I will explain what this means. So first, we will be trying to understand what exactly is self-attention and how do you calculate this attention scores so that you can get a context vector. This is what we discussed in the RNN lecture earlier. And we will also be implementing the same in code so that you can have a better numerical understanding. So let's get into the lecture. In the earlier lecture, we discussed about neural machine translation, which was using an encoder-decoder architecture. So we discussed about this short sentence translation example. So if you have an English sentence which says this is a car, it's a small sentence which has only 4 words. And this sentence as a sequence will be the input into the encoder. Encoder will simply output the context vector, and this context vector is expected to carry the entire meaning or the entire context in the input sequence. So it is carrying a lot of pressure. And then this context vector goes into the decoder as an input, and both encoder and decoder are RNNs, recurrent neural networks. And then decoder will output the output sequence. So if you are converting an English sentence into French, it will output the corresponding French equivalent. We discussed about the details of the architecture of encoder and decoder, but we also discussed one thing, that this kind of model struggles with long-range dependency. What is a long-range dependency? Consider this bigger sentence. The teacher who was teaching a difficult concept to the students smiled. So you have teacher here, you have students here, and you have this action of smiling. So looking at the sentence, how will you teach a neural network that it is actually the teacher who has smiled, not the students? Because here, the big sentence, in this big sentence, the word teacher is at the beginning and the word smiled is at the end. So there is definitely a long range dependency between the word smiled and the word teacher. And smiled has to pay a lot more attention to teacher than to students, because students did not smile, although these are two words that are really close to each other. So this was a problem in RNNs, because this whole long range dependency and this attention that each word has to pay to the words in the same sequence, this was difficult to teach to a recurrent neural network in the absence of attention mechanism, because you simply had one context vector as the output. Although there are hidden states, multiple hidden states in the encoder architecture, those hidden states were not accessible to the decoder. And then we discussed in the last lecture that in 2014, the concept of badano attention was introduced, where every hidden state in the output or at the decoder can get access to every single hidden state in the encoder. So H1, H2, H3 are hidden states in the encoder, S1, S2, S3 are states in decoder. So whenever you are considering one particular hidden state in the decoder, it is having access, especially the first decoder hidden state is not just having access to the context vector. So context vector is of course here, but context vector is not the only thing that the decoder gets access to. It also gets access to all the previous hidden states. And because of this, you can say that the word European, which ended up creating the hidden state H1, you can pay alpha 1, 1, that much weightage to that word. And alpha 2, 1. So 1, 1 means you're looking at the first hidden state of the encoder and first hidden state of the decoder. Alpha 2, 1 means, or you don't want to call this as hidden state necessarily. You can say the first sequence output coming out from the decoder. Alpha 2, 1 means you are looking at the first hidden state from encoder and the first item from decoder and so on. So to produce this output called zone, this mechanism can pay attention on a weighted basis to each hidden state in the encoder. So this is what badano attention enabled recurrent neural network to do. It could assign relative importance to every word in the sequence, not just looking at the final context vector. Although we discussed this and although we compared badano attention to self-attention, so it's very similar. Badano attention is about you have two different sequences, one at the encoder and one at the decoder. And badano attention creates attention scores or attention weights between words in the input sequence at encoder and words in the output sequence at decoder. So this matrix need not necessarily be like a square matrix, because there is no guarantee that the number of words in French is same as number of words in English, right? So this matrix can be like a non-square matrix. But in self-attention, it generalizes the concept of badano attention, where it says, okay, I don't have to compare between input and output sequence. Just given a sequence, within that sequence is that itself, the words are paying different levels of attention to each other. So smiled, this word attends to the word teacher. Logically, it should attend to the word teacher more than it attends to the word students. And when I say attends, it's a fancy way of saying it should pay more, I would say it should pay more importance to. So this was the concept of self-attention, and self-attention matrix looks like a square matrix. So if it is these three words, Americans speak English, then you can figure out through self-attention mechanism how much importance should this word English pay to the rest of the words in the same sequence. So you're looking at one sequence, and self-attention is attention matrix or attention scores or attention weights. I will explain the difference between score and weight. Self-attention will create those numbers, and it will help you identify how much importance each word is paying to the other words in the same sequence. Now, we stopped at this point in the earlier lecture, but we did not dive deep into how this attention or self-attention scores and weights can be calculated in the first place. And that is what we are going to do right now. So just to recap on the attention mechanism types that we'll be covering, badano attention is something that we have discussed Simplified self-attention is something that we are going to discuss right now, and that will make you understand how fundamentally attention mechanism works. And then the actual self-attention mechanism, which is implemented in GPT, involves trainable weights. In today's lecture, we are assuming there are no weights to be trained. So we will assume a much more simplified version of the self-attention mechanism without losing any understanding. But self-attention lecture, which will be the next one, will cover the actual trainable self-attention mechanism in detail. And GPT actually has two more concepts called masked self-attention and multi-head attention. So both of these concepts are very important to understand, and we'll be covering those as well. And they are derivatives of the original self-attention idea. And once you understand self-attention, it'll be much more easier to understand masked self-attention and multi-head attention. So in today's lecture, our focus will be entirely on a simplified self-attention mechanism. So now let's go back to the idea of self-attention. Let's say we have a sentence like dream big and work for it. Now the question is, if you are considering one word among this sequence, let's say the word big, the question that we are asking in self-attention mechanism is how much attention or how much weightage should this word big pay to every words in the same sequence? It will include itself. So big will be looking at itself, big will be looking at dream and work for it. Now in the RNN lecture, which was before, we also had a brief discussion about how words are converted into vector embeddings. So words are represented in a vector space, in an n-dimensional space. So it is represented using numbers, which is an abstract mathematical representation. It's not in a language of English or French. It's in the language of mathematics. Now the question is, the word big will have a certain vector embedding. The word dream will have another vector embedding, and work for it. Each of these words have their own vector embedding. And if you remember what we discussed in the last lecture, these vectors that corresponds to the word are not random. Those vectors carry meaning. So let's say these two are the vectors for apple and orange. Not from this sentence, but I'm just showing you an example. Then these could be the words for dog and cat. And in general, you can say that the words that carry similar semantic meaning may point to the similar semantic space in the n-dimensional space. So this could be a space or semantic space for fruits. And where these two vectors are pointing in general could be towards a semantic space for animals. Now these are the original embedding of the words without any extra context. So here word is converted into a vector, and it does not involve the knowledge of what words exist before this, what words exist after this, right? So there is no context here. It's just pure word to vector conversion. But this is not very useful because here the word big is in a context. It's in the context of the whole sentence, which means our goal is not to just get the vector embedding. This part is easy. Our goal is to get a context vector considering this word called big as the current word that is under consideration. So we want to get a context vector out of this word called big, which carries much more meaning and it's much more enriched compared to the embedding vector. And we can then do the same for all the words. So at the end of the day, unlike recurrent neural networks in encoder-decoder architecture in neural machine translation, we have multiple context vectors corresponding to each of the input word. So each input word has one context vector. So overall, we have multiple context vectors. However, in RNN, in the encoder and RNN and decoder, you could see that the encoder will simply output one context vector. Then that goes into the decoder. So our goal here is to create enriched context vector for each word in the sequence by taking into consideration not just that word, also the words right next to it. So each word should know how much importance it has to attribute to itself and to the rest of the words in the sequence. So this is the idea of how the attention scores are calculated, or how the self-attention scores are calculated. Now, I know that this diagram has bunch of numbers, but please please don't get worried. This is very simple. Now, let's say the word that I am considering for a moment is this word, the second word in the sequence, big. Now, as I mentioned, every single word in the sequence in a given sentence is converted into initially the input embedding, right? So let's say we are looking at an input embedding space of only 3 dimensions, not like 768 dimensions or something, only 3 dimensions. So this is the first dimension, second dimension, and third dimension of the input embedding for the word dream. And like that, first, second, third, like that, each vector has 3 dimensions. And there is one unique vector corresponding to each unique word. So dream, which is the first number in the sequence, input sequence is called as X here. And we are saying X of 1 is the first item in the input sequence, which is the word dream. And that dream has a corresponding embedding, vector embedding, and that is this. Similarly, the word big has a corresponding vector embedding, which is this. This is the vector embedding for and, work, for, it. Now, what we are trying to do is to construct something called as attention weights. And these attention weights are how much weightage should the word number 2 pay to word number 1? How much weightage should the word number 2 pay to itself? How much weightage should the word number 2 pay to word number 3? So word 2 to 1, word 2 to itself, word 2 to 3, 2 to 4, 2 to 5, and then 2 to 6. So these, if we can know how much attention this word big is paying to all the other words, that is called as attention weights. And let's represent the attention weights using alpha. So alpha 2, 1 means how much attention does big pay to dream. Alpha 2, 2 is how much attention does big pay to itself. 2, 3 is how much does it pay to and so on. Then if we had these attention weights, somehow we could construct a context vector. So this is the context vector corresponding to just one word. Which word? The word big. So if we had the attention weights of the word big with respect to every word in the sequence, using those attention weights, we can construct a context vector, maybe by taking a weighted average. So we could probably do alpha 2, 1 multiplied by this vector, plus alpha 2, 2 multiplied by this vector, alpha 2, 3 multiplied by this vector, and then that will give us a new vector whose dimension will still be 3 dimensions, because you are doing a weighted sum of each of these vectors. So dimensionality will not change. And then this vector will be called as the context vector for which one? For this input, for the input embedding called big. Like this, if we could repeat the process for every single word in this sequence, we can say we have now the context vector for all words in the sequence. All right. So this is what we are trying to do. Now let's see how this can be done. So firstly, let me show you a code snippet where I have my words, dream. Let me pick a new color. Dream, big, and work for it. So you have 6 words, which means you have 6 3-dimensional vectors. Now I am storing this vector in a tensor, in a PyTorch tensor. So now I have, this is first dimension of the first vector, this is second dimension of the first vector, third dimension of the first vector. Like that, I have 6 vectors, 1, 2, 3, 4, 5, 6. So basically, I am defining 6 vectors, each of them being 3 dimensions. And just assume for a moment that these are the input embeddings. Usually these input embeddings are created by using the word. So you input the word itself into maybe like a word to vec converter. So it will be a neural network which will help you convert the input word into a vector. But here, to simplify things, we are assuming that we already somehow know the input embedding. We only know the input embedding, by the way. We don't know the context vector. That is the more important thing here. But we know the input embedding for the word dream. All right. Now these are the words: dream, big, and work for it. Okay, so just keep this thing in mind. You have 6 vectors, each of them are 3 dimensions. Now you can plot this in 3 dimensions as a 3D plot in Python. So I will run the code and show you in a moment, but let me just show you the output first. You can run the code and you can get a plot that looks kind of like this. So if I copy paste this plot over here, then I can annotate. So now this is the 3D plot showing each of these 6 vectors: dream, dream, then where is big, and work for it. Now these are the 6 vectors. You might notice some specialities about these vectors. If you generally look at the vectors dream, big, and work, they are kind of pointing in similar direction. The words like and for are kind of pointing in some other direction, and it is pointing in even farther away. So if you really compare these 3 vectors against the vector it, they are literally, it's not exactly orthogonal, but they are pointing in general in away directions. And this makes sense, maybe because semantically, it is not really directly related with any of these words. Similarly, and for are like words, filler words, which even if you remove it, you can still kind of make out the meaning of the sentence. Work, big, and dream are maybe words kind of that appear in similar contexts. So kind of makes sense that they could be pointing in similar directions or in the direction of similar semantics, same semantic space. So this is how the vectors are looking at right now. Now let's see what to do with calculation of attention scores. So here we are not talking about attention weights anymore. We are talking about attention scores. And there is a difference between attention score and attention weight. Earlier, the alpha that we discussed over here are attention weights. So there is huge importance. Please pay very close attention here. These are attention weights. What we are discussing right now are attention scores. Now we can calculate a metric called as attention score, and that attention score can be a proxy for how much importance each word has relative to rest of the words in the same sequence. Now what could be a logical thing here? How can you construct attention scores by knowing the fact that these are the vectors that you have? So you have these 6 vectors and you have to somehow construct an importance score, right? One way to think about that is you look at in which direction these vectors are pointing. If the vectors are pointing far apart, like if the angle between these vectors are very big, so see this, the vector it and the rest of these vectors are literally, it's not exactly orthogonal, but kind of orthogonal. So maybe, the vector it and these vectors are not really paying too much attention to each other because they are anyway not pointing in similar semantic space direction. But maybe these vectors, work, big, and dream, they have so much importance to each other because they are all pointing in kind of similar direction. So these 3 words, so if you look at the word big, it should pay good attention to work, it should pay good attention to dream because these 3 words are pointing in similar directions. So they could mean similar things. But the word big need not pay that much attention to the word it, as you see from this vector diagram. But how do you quantify this mathematically? How do you come up with an attention score which can mathematically quantify this amount of importance each vector has for the other vector? One way to do that is by taking the dot product of these vectors. So if you have 2 vectors, let's say v1 and v2, the dot product will be a scalar. So let's say alpha is a dot product. Alpha is equal to v1, or let me call this as omega for consistency. So omega is a scalar which will be v1 dot v2. And if the angle between those vectors are 90 degree, then they are orthogonal vectors and omega will be equal to 0. If the angle between v1 and v2 are 0 degree, then the omega will be maximum. It will simply be magnitude of v1 multiplied by magnitude of v2. So the dot product between 2 vectors is like a very nice proxy, or it's like a very good metric for capturing the attention between those two vectors or the importance of those two vectors in that context. So in the context of the current sentence, you can say that big is, it should pay more attention to work and dream than these words in the current context. Maybe in some other context, the word big might pay more attention to for, because the rest of the words in the sentence might be pointing in entirely different direction. But in the current context, big should ideally pay more attention to work and dream based on this vector 3D vector diagram. So that is exactly what we are doing here. We calculate the dot product, something like this. So if the dot product between two vectors, the magnitude of the dot product between two vectors are bigger, you can say that these two vectors in the current context should pay more attention to each other, or they should attend to each other more than with some other vector with which the dot product value is very small. So here a dot c is lower in magnitude compared to a dot b. So here when I say dot, I mean the dot product, right? So dot product you can think of as a mathematical measure for vector similarity. Now, one thing you should note is, in general, higher the dot product value, better the alignment. Lower the dot product value, lesser the alignment between those vectors. Now, if we come back to this diagram, I hope you will have a better picture of what's going on here. So here, consider the words in your input sequence, dream big and work for it. And there are 6 words, and consider that currently you are looking at the word big. So now the word that you are looking at, to see how that word, how much attention that word should pay to the rest of the words, including itself, is called query. So query in this case is the second token. Okay. And these words will come back again. This word called query will come back again when we are learning about the masked self-attention and multi-head attention, etc. So now query being this word big, and rest of the words now, including itself, are called keys. And we will also discuss in subsequent lectures why does it make sense to call this as query, this as key, etc. But I'm just introducing this terminology to you so that it will be familiar to you when we discuss it in detail later. So query being big and dream being this, what we can do is we can simply take the dot product of this with this. So it will be 0.75 multiplied by 0.42 plus 0.2 multiplied by 0.65 plus 0.55 multiplied by 0.31. So element wise dot product, this times this plus this times this plus this times this, and that will be one number because dot product results in a scalar which is one number, and that number will be the attention score, not attention weight. It will be the attention score between big and dream. Similarly, if you take the dot product of big with itself, it's basically the magnitude of that vector, and you will get that number, and that will be the attention score between big and itself. Similarly, you can calculate the rest of the attention scores, and these attention scores we denote by omega. So omega 21 means attention score that is paid by the second word in the sequence to the first word. Omega 22 means second word to itself. 23 means second words to the third word, second to the fourth, and so on. Now, this attention score is calculated between one query and every single words in the input vector, which we can call as keys. So it's between query and keys. Alright, so this much so far is good. Now, one thing might be confusing here for you, if you have a certain thought process, is that, so the word big is aligning perfectly with itself. Isn't that correct? Because the word big is having 0 degree with itself. So shouldn't the attention score of the word big be highest? Why is this number not the highest? So this is 0.91. But here you can see there is another word, work. So big is having so much more attention with work. So this is 1.04. Why is that the case? Why is the attention between big and work bigger? So there are two things to note here. First one is that the magnitude of these vectors, right? These 3D vectors, the magnitude of every single one of them is not the same. They are different. So here, if I plot the magnitude, or if I just note down the magnitude is simply square root of x square plus y square plus z square. And for the word dream, it is 0.90. This is 0.95, 0.94, 1.09, etc. So not only these words have vector representation that points in different directions, but also the magnitude of those vectors are different, and that also carries meaning. So the semantic meaning is carried in the fact that the vector is pointing in a certain direction, and also in the fact that it has a certain magnitude. So please don't misunderstand that all these vectors are unit vectors. That's not the case. And because of this, it is likely that the word big or the vector big can have a bigger dot product with some other vector which is almost pointing in that direction. So here you see big and work are pointing in almost the same directions. And because of that, the dot product between big and work is higher than the dot product between big and itself. So please note this. This is a very important thing to understand, because otherwise you might think later when we construct the attention matrix that, so let's say dream, big, and work for it. When we construct an attention matrix like this, you might think that dream is highly correlated with dream because they are literally the same vectors. And because of this diagonal element should always be the highest in this attention matrix. You might think like that, but that is not the case. And the reason for that is because the words are having, these vectors are having different magnitudes. So when you take the dot product with some other vector can actually be bigger than dot product with itself. All right. So please note this. Now we can get the attention score for the current query with every vector, every word in the sequence. All right. So that much is fine. Now, just having attention scores are not enough, because attention scores are just numbers which do not tell us something very useful. What is more useful is if somehow these numbers can tell me, hey, the word big or the query big should pay 10% attention to dream. It should pay 20% attention to big. It should pay 25% attention to and, like that. If I can get some numbers in percentages, that will be more useful to me. So that then I can say sum total of these attention scores, somehow if I can bring it to 100% or 1, that will be better for me because it's meaningful. Then I can say in a sense of a fraction, big is paying 0.5 fraction of attention to itself. It's paying 0.3 fraction of attention to and so on, something like that. But one thing you have to note here is that if you sum up the attention scores of big with respect to all the words in the sequence, so omega 21 plus 22 plus 23 plus etc., the sum will not be equal to 1. So here itself, if you go up, if you sum up these numbers which we have, these are the attention scores of the query big with respect to all the words in the sequence. You simply sum this up, it won't come out to be 1. It's greater than 1. It could be less than 1 also depending on the vectors, but it's not equal to 1. This is not good because it's better if they are normalized, the sum is normalized to 1, so that then I can calculate a score, attention score, which is like a fraction or like a percentage, which is more useful and interpretable for me. So that is why normalizing the attention scores to create what we call as attention weights is important. So attention weights sum up to 1, but attention scores do not sum up to 1. That's the main difference between those two. But there is one more important thing in constructing attention weights, which is when you are training the large language model, it's better if the numbers in the attention are in the range of less than 1 or 0 to 1, because the training will be much more stable in that way. So if the weights sum up to 1, we know that every single weight is less than 1. So there is a specific range in which the weights are expected. So this will result in two things. One is interpretability, because now I can say this much percentage attention is paid to another word, and also in LLM training stability. Right? So now let's see, how do we construct a normalized attention score? Meaning, how do we construct this how do we change this attention score such that it sums up to 1? So what I want is all the attention scores corresponding to dream, all the attention scores of dream with respect to all the words in the sequence should sum up to 1. So sum of all these things should be 1. Currently it is not 1. Then similarly for big, if these are the attention scores, these 6 attention scores are there, they should sum up to 1. Currently it is not. Similarly for every query, so dream, big, and work for it. So those are queries. when we construct attention scores of those queries with respect to every single word in the sequence, I want the sum of those attention scores to be 1. This is what my requirement is. Now let's see how we can do that. Maybe what we can do is we can simply do a summation, which is called simple normalization. Simple normalization is you take the sum of these numbers. So convert this number to be omega 21 divided by sum of omega 2i, where I runs from 1 to 6. So omega 21 divided by, in the denominator, it will be omega 21, 22, 23, etc. And you do this for every row separately. So here you find the sum of all these 6 numbers. All right. And then you find the sum of omega. And then every single omega you divide by. So you do omega 1i divided by sum of omega. Omega 2i or 1i divided by omega. I mean 1 divided by sum of omega. Omega 1 2 divided by sum of omega. Omega 1 3 divided by sum of omega, etc. So that will ensure that when you sum up all these, you will get back 1 because you are normalizing by the sum. And you could do that for all the individual rows here separately. And that is valid. In that case, you have a normalized attention score, which we can call as attention weight. They will sum up to be 1 very nicely. And you will have interpretability, you will have stability. But the thing is, there are other normalization techniques. The most famous normalization techniques is Softmax. In Softmax, what we do is, the formula is this: we take the exponent of those elements, and then we take the sum of exponents, and then you normalize using the sum of exponents. So this is the simple normalization, and this is the Softmax normalization. In both cases, you can see that the sum total of the elements will be 1, because in simple normalization, you will have sigma xi divided by sigma xi, right? And this we can rewrite as this sigma will go into the numerator, because sigma xi is like just a number. So then sigma xi divided by sigma xi, this is equal to 1. Similarly, in Softmax, we'll have summation of e raised to xi divided by sigma e raised to xi. Sigma e raised to xi is a number. So then this sigma will apply to numerator. Then we'll have sigma e raised to xi divided by sigma e raised to xi, which is equal to 1. So both of them are equally fine. But there is a huge difference between simple normalization and Softmax normalization. Consider these attention scores. So let's say this is omega 11, omega 12, omega 13, and omega 14. These are attention scores, not weights, because clearly they don't sum up to 1. Sum is 6 plus 8 plus 9, 10, 11, 12, right? 12 is the sum. In simple normalization, the first number will become what? 1 by 12. Second number will become, so 1 by 12 is slightly less than 0.1. So this is the simple attention. Second number will become 2 by 12, which is 1 by 6, 0.166 or something, right? Third number will become 3 by 12, which is 1 by 4, 0.25. That is this. Fourth number will be 6 by 12, which is half. So here, if you look at the attention scores converted to weights, they will sum up to be 1. And the differences between them are proportional to their actual attention score value. So this attention score is double that of this attention score. And because of that reason, this attention weight, which is 0.25, and you have to multiply that by 2 to get this attention weight, which is 0.5. So this is the simple normalization. In machine learning, however, what we like is, we would like to say with more certainty, or we would like to make a bit more bold decisions, saying that the attention score of this is highest, which means I should give more weightage to this, and these should be slightly suppressed. And that is exactly what happens in Softmax. In Softmax, when you convert these numbers, when you put it through the Softmax formula, this is the resulting graph. So whichever is the highest, it will be given significantly higher weightage, whichever is low, they will be completely suppressed. Now your model can make much more clear decisions, because clearly this number is dominating. I have made an Excel sheet where you can plug in these numbers to see the effect of Softmax on the input. So let's just open this quickly and let's play with these numbers a little bit. All right. So now see these numbers. My inputs are 1, 2, 3, 6. And when I convert those numbers to exponents, these are the numbers. So this is the sum of the numbers. and this is the sum of the exponents. So simple normalization will result in these numbers, softmax will result in these numbers. So I'm plotting it here. So just no need to focus on these numbers, just focus on the graph. So if it is 1, 2, 3, 6, it will be like this. If it is 1, 2, 3, 10, see how much more the emphasis is on the largest number in softmax. So softmax makes the decision of the model much more clearer. So let's say this is 1, 2, 3, 4, right? Then simple normalization does not give us something very useful here. These numbers are like steps. After simple normalization also, they are like exact same steps of exact same proportion. But here you see it's more like an exponent, which is better. If this is 5, the difference is better. See, here the difference is very little. It's very hard to say which one is clearly dominating. I mean, of course, we can say that 5 is dominating, but it's not good enough. But here in softmax, it converts the dominating number into even higher dominating status. The rest of the numbers it will suppress. So softmax is a better way to construct probability distribution. So even if these numbers are negative numbers, it's not an issue for softmax. But it's an issue for simple normalization. In softmax, however, that number is entirely suppressed very close to 0. So softmax has this benefit that it's kind of agnostic to input numbers sign to produce the final probability distribution. Whereas in simple normalization, this negative number, although the sum of these numbers will be 1, negative number is not the right probability, right? So negative number is not a probability value. So that's the advantage of using softmax over simple normalization. So what we do is we get the attention weights, right? Sorry, attention scores, right? So this omegas are the attention scores. We convert those attention scores into softmax probability distribution. So now these alphas are the softmax probability distribution, which will sum to 1. So how do we get alpha? We get alpha by taking softmax of omega. So what would be it be like? So alpha 1, 1 equal to omega 1, 1 divided by, or in this case, there is no 1, 1. It's all 2, 1, 2, 2, etc. So let's rewrite that way. So alpha 2, 1 equal to e raised to omega 2, 1 divided by sum of e raised to omega 2i, where I runs from 1 to 6. So this is alpha 2, 1. Like that, you can construct alpha 2, 2, alpha 2, 3, etc. So now this is the attention weights. Why? Because these weights sum up to 1 and it's like a nice probability distribution. Now what we can do is, now we are fully ready to calculate the context vector. Context vector for what? Context vector for this input embedding, because context vector is there for every single input embedding. Unlike the recurrent neural network encoder-decoder architecture where there was only one context vector out of the entire sequence, here we have context vector associated with each input embedding. So now we are fully ready to calculate the context vector corresponding to the embedding for the word big. So if we go back to the earlier figure, this figure, here, what did we discuss? Here we discussed somehow if we had these attention weights, we can probably do a weighted average of the input embeddings to get the context vector. So alpha 2, 1 multiplied by this plus alpha 2, 2 multiplied by this plus alpha 2, 3 multiplied by this. We could do that, which will result in a 3-dimensional vector. So it will be like a weighted average, right? Weighted summation. That is exactly what we'll be doing now. So now that we have the softmax distribution, which is the attention weights, all we have to do is we simply say the context vector corresponding to x of 2, which we will call as z of 2. So now z or z is the context vector for input embedding number 2, will be alpha 2, 1 multiplied by x of 1. So what is that? Alpha 2, 1 multiplied by x of 1 plus alpha 2, 2 multiplied by x of 2, alpha 2, 3 multiplied by x of 3, alpha 2, 4 multiplied by x of 4, and sum up all of that. And that will give you the context vector for the query big. So here, essentially what we are doing is we are taking the input embedding for all the words in the sequence, and then we are calculating how much relative importance should these input embeddings have to each other in the current context, and then create an attention weight, and using that attention weight, take a weighted score of these all input embeddings to construct the context vector. Currently, this example is for the context vector for the word big, but this exact same procedure can be replicated for the rest of the words or for the rest of the queries. So this is the idea behind constructing context vector. Now this context vector is rich in information because it has information not just about itself, So the input embedding of the vector of the word big only had information about itself. So this vector did not have any other information. It has no idea what is there next to it. But now this context vector, which is again a three-dimensional vector, will have information about what other words exist around this word big, right? So it's much more context rich. You can also visualize this creation of the context vector from a bit of graphical perspective. So let's say, consider the 6 vectors in your text input sequence: dream big and work for it. So 6 words. Now these 6 words have 6 corresponding input embeddings. So these are those input embeddings, let's say, these vectors. Now it's pointing in different directions, but I have just put it on one plane just to visualize. Now what the attention weights tell us is that 20% weightage. So if big is our query, so this is now our query vector, which means we are trying to calculate how much should this vector pay attention to itself and also the rest of the vectors, right? And what will tell us the amount of attention that it has to pay? It will be from the attention weights between query and all the vectors. So now attention weights we can visualize as a percentage. So these percentages should add up to 100. 30 plus 30 plus 20, which is 80. 80 plus 10 is 90, plus 5 plus 5, 100, right? So now we should consider 30% of the vector dream. So now the dream vector is reduced from its original size to 1/3. We should pay 30% to big itself. So big is also reduced to 30%. And you just need to pay 5%. Work, you pay 20%. So 20, because this 1/5 of the length, approximately, these are just graphicals. These are not exact lengths. And 4, 10%, and 8, 5%. Now these are the weighted vectors. So these were the original input embedding vectors. Which ones? These gray ones. And this was the query vector, this black color vector. But these red color vectors are now attention weighted vectors. So the input embeddings are multiplied by the attention weights, corresponding attention weights. And now what do? You simply do a vector sum of all these 6 weighted vectors. And when you do that, you will get a resulting vector. And that resulting vector will be the context vector. So here I have shown it in green color. It's not the exact vector summation of these red color vectors, but approximately if you add up these red color vectors, you will get a resulting vector, and that resulting vector is the context vector. Context vector for what? Context vector for the query vector. So here the query vector is big. So this is the corresponding context vector for big. So see what has happened. The vector big, which was the input embedding, which did not carry any context, has now transformed to this vector in the same dimension. So if it's a three-dimensional space, it simply transformed. Transformed through what? Transformed through attention weights. So attention weights were multiplied with the rest of the input embeddings, and all of them were added up to create this context vector. And this is done for every other vectors also. This, just like how we did this for the big vector, which is done for dream and work for it. And this is how we construct 6 context vectors from 6 input embeddings, right? This was not there in the RNN, but in the original RNN before attention mechanism. And now what we have is we constructed this self-attention mechanism to create the attention weights, and these weights allowed it to create the context vectors. All right. So now these attention weights, as I mentioned, alphas, not omegas, they should sum up to 1. So all the attention weights of the dream query should sum up to 1. All the attention weights of the big query should sum up to 1. Same for and, same for work, for, and it. All right. So please pay attention to this. Attention weights are different from attention scores. Okay. Now let's look at the whole picture. We have input embedding. In the input embedding, we have 6 words. And the input embedding space is 3-dimensional. It's an assumption that we made. Of course, in reality, in GPT-2, GPT-3, etc., the space is much bigger. But we had 6 input vectors with 3-dimensionality. So it will be like a matrix of dimension 6 by 3. 6 denoting the number of vectors, 3 denoting the dimension of each vector, right? Now this input embedding, somehow we want to convert to what? We want to convert into context vectors. And what should be the dimension of these context vectors and how many context vectors we should have? Think about it. Every single input embedding we are converting into a context vector. And context vector is simply a transformation of the input embedding in the same dimensional space, which means each context vector should be it should have 3 dimensions. So like that, you should have 6 context vectors because you have 6 input embeddings, right? So the dimension of your final context vector matrix should be 6 by 3. So somehow you have to convert the input 6 by 3, input embedding 6 by 3 into context vector, a matrix that consists of all the context vectors, which should have 6 by 3 as a dimension. And what is used for making this conversion? Attention weights is used for making this conversion. So there are how many attention weights? For every query, you have 6 attention weights. And like that, you have 6 queries. So it's a 6 by 6 matrix. So attention weights is 6 by 6. Let's just write this down. Input embedding is 6 by 3 because you have 6 vectors and 3 dimensions. Attention is 6 by 6. We have 6 queries, and for every query, there are 6 attention weights. And then the expected output, which is context vector matrix, should be what? Same dimension as the input embedding. It should be 6 by 3. So how do you go from you are multiplying with the attention weights, the input embedding, and somehow you're getting the final output. So in what fashion can you multiply these two to get this? Is it input embedding multiplied by attention, or is it attention multiplied by input embedding? In the current dimensionality, it should be attention multiplied by input embedding because the second dimension of the first matrix and first dimension of the second matrix should match. So attention weights, which is 6 by 6, multiplied by input embedding, which is 6 by 3, will give you context vector matrix, which will be 6 multiplied by 3 because this dimension is common in in matrix multiplication. So this will result in 6 by 3. So that is what I have drawn here. You multiply attention weights, and this is 6 by 6 with input embedding. This is 6 by 3 to get context vectors, which are 6 by 3. So this is the 6 by 3 dimensional matrix, which will handle the 6 context vectors of each 3 dimensions. Now, I think we are now in a good place to go ahead and execute all of this in code, because we have now the 6 vectors as input embedding. We know how to calculate attention scores. We know how to convert the attention scores into attention weights using Softmax. And then we know how to go from attention weights to context vectors by multiplying attention weights with input embedding. So let's now open the code. All right. So the first block of code, we are importing PyTorch, and we are defining a tensor. So in this tensor, we have 6 items, each belonging to one word, and there are 3 dimensions. So let's just run this to define the tensors. In this block, I'm just simply printing the magnitude of each vectors. So magnitude along dimension 1. So magnitude along dimension 1 means this magnitude of this vector, magnitude of this vector, of this, like that, 6 magnitudes will be there. And then I'm just printing it one by one. So magnitude of dream is 0.903. This I already showed you to just show the fact that they are not unit vectors pointing in different direction. They are different vectors, vectors of different magnitude pointing in different direction, right? Magnitude and direction are different. So these are the magnitudes of my current vectors, dream big and work for it. Now we can simply plot this. For plotting, I'm using matplotlib. So I'm not going to the details of these libraries because these are fairly straightforward. So we extract the x coordinate, y coordinate, and z coordinates from our input matrix. So inputs is the input matrix. From that, the items in the first column, or rather 0th column, are the x coordinates. In the first column, number 1 is the y coordinates. Column number 2 is the z coordinates. Indexing starts with 0 in Python. Then we add a figure using matplotlib plt.figure, and then it's a 3D projection. We define the color for our 6 vectors. We have 6 vectors because we have 6 words, 6 unique colors. And then we simply add the labels, X label, we set the limits for the axis to be between 0 to 1 and simply run the code to plot it. So these are now 6 vectors. And as I mentioned earlier, the vector work, big and dream, those vectors are generally pointing in the same direction. The vector it is almost, it's not exactly orthogonal, but kind of in the 90-degree direction. This is how our initial input embeddings look like. Now, how to convert this into context vectors? So first, we can randomly take the second input token as a sample. What is the second input token? This word, big. Now let's see how much attention should this word big pay to all the words in the sequence, right? So we can say the current query that I'm looking at is the first element number 1 in the inputs, which is the second row, right? First row is the word dream, second row is the word big, but the second row is denoted by index 1. So this is the first query. Now for this query, we can calculate attention score. So first we define an empty attention score array. So the number of elements in this empty attention scores array should be same as the number of rows. So row is the 0th dimension of the matrix inputs. So inputs dot shape of 0. And then we simply do a dot product between the query and the rest of the vectors. So query is this, rest of the vectors are each individual vector in our inputs. So inputs has basically 6 rows, and each row will be considered as the key, and that is denoted by x underscore I. And then we store the corresponding attention score in the ith index item in the attention underscore score under 2. So this underscore 2 means you are looking at the token number 2 as the query, or word number 2 as the query. And then we can simply run this to see the attention scores. So see, now it's dream big and work for it, right? So we are looking at big as the query, and big is paying 0.90 attention to itself. Big is paying 0.80 attention to dream, and big is paying most attention to, I think this is work, right? This is 4 and this is it. Basically big is paying least attention to it. That is what this means. So these are the attention scores for the query equal to big with respect to all the 6 inputs in the input embedding. Now we can perform normalization. So this is the simple normalization or vanilla normalization, not softmax, where every attention score is divided by the sum of those attention scores. So we can get the attention scores to be normalized such that they sum up to 1. But we also already discussed why this is not the best thing to do, why softmax is the better thing to do. So what we can do is we can convert these, not these attention scores. These are useless ones. So we can even comment this entire thing out so that we don't have it. But these scores, 0.80, 0.905, this we can convert to softmax. So here we can utilize the TensorFlow softmax function. So we are calling TensorFlow.nn.softmax, and we are passing the attention scores there in a TensorFlow format. And then we can get the softmax probability distribution. So basically now what this says is 16% attention should be paid to the dream, 18% to big itself, dream big, and then work, right? 13% to work, 20% to dream big and work for it. So this 13 is and, work is 20, 4 is 17, it is 14. So this is how the softmax probability distribution looks like, and sum total is 1. This is slightly showing 1.0001 because of a round off errors. So when the softmax is being calculated, numbers are being rounded off. Now the attention scores are calculated for every single query and for every single input sequence. So how many queries do we have? We have 6 queries. 6 queries, and how is that? We have 6 sentences, and each of them are of length 3. So but there are 6 rows and 3 columns, right? And what we said was, if I want to calculate the attention score between this query and let's say now I have this was my input embeddings, which was also 6 by 3, 6, This is 6. So I'm just drawing 6 lines. What I said is we could take the dot product between, first I take the dot product between, so let's say this is my query. Now, second item is the query. I take the dot product between this and this. Then I take the dot product between this and this. Then I take between this and this. Then I take between this and this. So if you look at what's happening here, the same row is getting multiplied by different rows in the next matrix. So the easiest way to perform this is, and at the end of the day, I need to get something of dimension 6 by 6 because I have 6 queries and I have 6 embeddings. And for every query, I want 6 attention scores or attention weights rather. And like that, I have 6, which means the output should be 6 by 6. So what I can do is this matrix, I can multiply with the transpose of this matrix. So it will be a multiplication of 6 by 3 matrix with a 3 by 6 matrix resulting in 6 by 6 matrix. So whatever is my input matrix, right, you can multiply it by transpose of the input matrix, input transpose. So that is what is done here. So I have the inputs matrix, which is this at the input, inputs equal to this tensor. And then I multiply that with the transpose. So dot t means transport, at means it will perform, Python will perform a very efficient matrix multiplication. Now we get the attention scores matrix, not the attention score for just one query, for all queries. So these are the attention scores for the first query. These are the attention scores for the query in big. And just look at these numbers, 0.8005, 0.9050. These are the same numbers that we had over here. 0.8005, 0.9050. These are the attention scores corresponding to the query big. Now we have to convert this into softmax such that we are normalizing along each row. So each row should sum up to 1. So here in Python, if we mention dimension equal to -1, it means perform the normalization along whichever is the last dimension. And here that means you will be performing normalization along every row such that every row will sum up to be 1. So now here these are the attention weights and these numbers will sum up to 1. We can do a quick calculation. 17 plus 17 is 34. This is roughly 34 plus 135. Plus 15 is 50. Plus 20 is 70. Plus 15 is 85. Plus 13 is 98. And there are a few residuals here which I did not include, which is why some of these are 1. And we can randomly take it, right? So row 2 sum equal to sum of, this is not the correct one. Row 2 sum is sum of, let's say, these numbers. So sum of these numbers are the row 2 sum. And we can get it to be, okay, so I need an extra. Yeah, see, sum of the second row is 0.999. Sum of the last row is also, I'm pretty sure it's 0.999 or close to 1. Yeah, it's 1.0. And here I just print all the rows, sum of all the rows along, again, dimension equal to -1 means the last axis of this tensor or last dimension of this tensor. So then I can see that every row, I have 6 rows, every row sum is 1. So this 1.00 is the sum of this row. Similarly, the next 1.000 is the sum of this row. Okay, please notice, not the other way, not column wise, row wise. Now, what we can do is we can simply calculate the context vector. So how do we calculate context vector from attention weights? We said all we need to do is simply multiply attention weight with the input embedding, right? Attention weight is a 6 by 6 matrix, input embedding is 6 by 3, and using that we can get context vector. So let's see. So here I'm multiplying attention weights with input vector. So same thing here, input embedding, attention weights multiplied by input embedding. So attention weights at means matrix multiplication in the language of Python, inputs, and then you can print all the context vectors. So now these are the 6 context vectors of each being 3 dimensions corresponding to each of the 6 words in the input sequence. This corresponds to dream, big, and work, for, it. So whatever was the 3-dimensional input embedding for each vector, now they have been transformed into these context vectors. And now what we can do is we can simply extract the context vector corresponding to big, because we have been focusing on that second vector in the sequence. So this is the context vector of index 1. Of 0 means it will be of dream. So now this is the context vector, and I can simply append the context vector into my inputs so that I can plot it in the same 3D plot to see how much the context vector is different from the actual vector for big, right? So now I have 6 plus 1, 7 vectors which I'll be plotting, and I'm just showing you the plot here. So see, this big is the green color vector is the original embedding vector embedding of big. But then this context vector, let me also annotate that this context vector is actually context vector for big. So I'll just write that here. Context vector underscore for underscore big, something like this will be better. And let me plot the 3D plot once again. Yeah. Oh, let me run once again because it appended twice. That's why. Yeah. Now hopefully it should be fine. Yeah. So see, now consider this brown vector, this guy, and the green vector. Green vector was the original vector embedding for the word big. Now the context vector, which is much more rich in context, is this brown vector. And now that vector has the information that this big vector is not alone. The other vectors are around it. Now this vector is much more useful than directly using the input embedding for big. And like this, we can plot for every single context vectors, right? So this is the self-attention in a simplified manner. Here we did not use any trainable weights, meaning we did not transform the input embedding into corresponding context vectors using trainable weights. We transformed it using this rule by taking dot product. But in the next lecture, we will see how attention mechanism is implemented actually in models like GPT with trainable weights. And at that time, we'll be discussing about key, query, and value matrices. And you will have a even better understanding about self-attention mechanism at that point. And subsequently, we will be discussing about causal attention, meaning masked attention, as well as multi-head attention. And with that, the attention section of this series will be complete. And then we will have a better picture about the entire large language model architecture. And at that point, we can be satisfied in saying that we understand the LLM architecture properly at this point. And now we are good to look at large language model, similar architecture, but for vision, which is vision transformer. So I hope you understand the trajectory of this series, and I hope you are enjoying it. Please pause and rewatch the video wherever you feel like you want to have more clarity. Watch the same lecture multiple times, take detailed lecture notes. You will that way learn much better and faster, and you will retain everything better. And I will see you in the next lecture. Take care until then. Bye. Hi, welcome back to a new lecture from Transformers for Vision series. In today's lecture, we will be diving deep into the self-attention mechanism. But unlike last lecture where we implemented a simplified version of self-attention mechanism by just taking the dot product between the vectors, this time we'll be implementing self-attention with trainable weights. And when I say trainable weights, I specifically mean the weight matrices associated with key, query, and value. So these are terms which you will find in the context of large language models. So I hope to give you a good amount of intuition about what is key, what is query, what is value, etc. The self-attention mechanism that is used in LLMs like GPT is also called as scaled dot product attention. So by the end of today's lecture, you should also understand what is the intuition behind this equation which was mentioned in the Attention is All You Need paper. Right now, it may look a bit intimidating to you, but don't worry. By the end of the lecture, I guarantee that you will have a fairly good understanding what exactly this equation is trying to tell from an intuition perspective. So with that, let's get into the lecture. So first, let's take a step back and try to understand what all we have been discussing in this course so far. In the lecture before, we discussed about simplified self-attention, where we constructed attention scores by using dot product between the vector embeddings. And even before that, we started our discussion by going through badano attention, which was introduced in 2014. So as we know, badano attention was used primarily in the encoder-decoder architecture in neural machine translation, where every single hidden state in the decoder had access to every single hidden state in the encoder. So these H1, H2, H3 are hidden states in the encoder, and all these states were accessible in the decoder, which was not the case before badano attention. And because of this, instead of relying on one single context vector which comes out of the encoder, you can rely on every single hidden states, and you can construct relative importance that the decoder should pay to each of these hidden states. That way you are taking off the pressure that you were putting on the final context vector. If you don't remember the encoder-decoder architecture from recurrent neural networks, don't worry, it's not of relevance for today's lecture, but I just wanted to give a brief recap. If you really want to understand how badano attention came into picture in 2014 in the context of neural machine translation, you can go back to the lecture in which we discussed about how RNNs started with encoder-decoder architecture and then eventually attention mechanism came into picture. Now, in self-attention, however, what we were trying to do was something different. We had one input sequence, and let's say this is our input sequence, dream big and work for it. We wanted to construct context vectors corresponding to every tokens in the input sequence. For simplicity, we are now thinking that each token is one word, although in reality, in models like GPT, it uses byte pair encoding. So one word is not necessarily one token. There could be characters and subwords. But here for simplicity, what we want to do is in this sequence, you have 1, 2, 3, 4, 5, 6. So there are 6 tokens. And for every single token, we want to produce a corresponding context vector. If this was a neural machine translation task in the encoder-decoder architecture of NMT, we would have just produced one context vector at the end of the sequence at the output of encoder, and we were hoping that that context vector will embed whole information present in the sequence. But with the advent of self-attention mechanism, we don't have to do that anymore. We can calculate how much each word in the sequence should pay attention to or should attend to every word in the same sequence. So that's the reason why the name self-attention came into existence. So in today's lecture, we'll be considering these tokens as 3-dimensional vectors so that we can easily plot like this. In the previous lecture where we implemented a self-attention in a simplified fashion, we had input embeddings like this: dream, big, and work for it. So dream, this is the original input embedding for dream. This is the embedding for big, and work for it. Now to calculate how much attention dream should pay to big, or how much, let's say, work should pay to big, what we did was we took a dot product between these two vectors, and based on the magnitude of those dot products, we constructed attention scores. So if there are 6 words, and if we consider big as the query meaning the token that we are currently looking at, we can construct six attention scores: one between big and dream, one between big and itself, one between big and, then big and work, big and for, and then big and it. Now these attention scores are not normalized. So what we discussed in the earlier lecture was that we normalize these attention scores such that they add up to 1. So we were using Softmax function for normalizing such that the 6 attention scores corresponding to any query. So in this case, if we consider our query being big, there will be 6 attention scores corresponding to every single key. So let's say this is 0.1, 0.2, 0.2, 0.1, 0.3. So that will be 4 plus 1, 5, 6, 7, 8, 9. And then this will be 0.1. Now, if you add up these numbers, there are 6 numbers. And if you add up these, it will be 1. So 0.1 plus 0.2 plus 0.2 is 0.5. 0.6, 0.7, 0.78, 0.8, 0.9, and then 1. So you can view this as percentages. Our sentence is dream big and work for it. Now what this means is dream should pay 10% attention to big. I mean, big should pay 10% attention to dream. Big should pay 10%, 20% attention to itself because this is 0.2. Big should pay 20% attention to and, etc. So by having these normalized attention scores, we can have intuition on how much percentage attention each query is paying to every single key in the same sequence. So this is how normalization of the attention scores lead to something called as attention weights. So these numbers, which resulted from Softmax calculation, are called attention weights. Now to construct the context vector, what we did was we multiplied the original input vectors. So dream had an original input vector, which was this guy. Big had a vector for dream big and work for it. So each input vector, so if I denote these vectors like this, you can scale these vectors using these attention weights. So you multiply the vector with the corresponding attention weight and then you add them up. That is how you get the context vector for, let's say, the word big. Similarly, if you take the row from the attention matrix, which are the attention weights corresponding to any particular query, you can take attention weighted sum of the input vectors to get the context vector. So now if we plot the context vector here, this was the context vector for the token big, which we got at the end of the previous lecture. But you must have noticed one thing. We know that in large language models, training the model is a big deal. But here in this attention calculation, in the self-attention calculation, there is no training involved. There are no weights that are trainable. The dot product is simply taken between the vectors which we already have. So after tokenization, we have the vectors corresponding to tokens. And then there is no more trainable weights involved. We are simply taking dot product to get the attention scores. Then we are normalizing it using Softmax to get attention weights. Then we are taking weighted attention of keys corresponding to any given query to get the context vector for that particular query. So this is what we were doing in the last lecture. If you want to really spend some time on simplified self-attention, and if you are watching this lecture for the first time in the series, please go back to the previous lecture just to spend some time on simplified self-attention so that you can get much better intuition on why we are interested in constructing a context vector. In very simple terms, context vector is very important because it has much better meaning embedded in it. So it's much more enriched. So the context vector for big is much more useful to us, or is much more useful to the large language model than just the input embedding for big. Because the context vector for big is also taking into consideration the fact that there are other words in the sequence. There are these remaining 5 words also in the sequence. So this is why context vector is much more information rich or context rich. Now, if you just look at this diagram, this is again just the summarization of simplified self-attention. We had the input embeddings corresponding to every single word or every single token. So we had 6 tokens. So these were the 6 input embeddings, or basically the 6 3-dimensional vectors. Then if we consider big as the query, which is the second token. So we are looking at how much attention should big pay to dream, how much should big pay to itself, how much should big pay to and, etc. We took dot product between big and dream. So it will be just one number, scalar. So these dot products denoted by omega 21. Omega 21 means the attention between dream and big. Omega 22 means attention between key number 2 and query number 2. Omega 23 is attention between key number 3 and query number 2. Like that. So we got these attention scores, which are denoted by omega. And then we got attention weights, which are denoted by alpha. And these attention weights should sum up to 1. And then we use these attention weights such that we took a weighted sum. So alpha 21 was multiplied by the input embedding alpha 22 was multiplied by the input embedding for the second query, alpha 23 with the third one, for the second token, alpha 23 with the third token, alpha 24 with the fourth token embedding, and then we add all of that up. So it's as if you are adding all these 6 vectors, but we are not simply adding it, we are adding it by multiplying with a scaling factor. Scaling factor is these attention weights. So this is what we did in summary. Now just look at what all things did we use. We simply used a dot product. Dot product does not involve any weights, right? We are using already existing numbers. So in today's lecture, we are going to introduce weight matrices, which will allow a neural network to train, and then these weight matrices will become better and better, such that when you are taking a dot product, after performing some sort of transformation to your input embeddings, you will have a better context vector available to you. So the end goal is to have an even better context vector. We already got a context vector for the word big, for the word dream, etc. in the last lecture, but we want to get an even better context vector. And these trainable weight matrices are so crucial in large language models, because these weight matrices are those that help us produce these context-rich vectors. And these weight matrices are known by the name query matrix, key matrix, and value matrix. So query, key, and value are terms which you might have heard of in the context of LLMs, but you probably don't have a great intuition about this. So don't worry, we will be paying enough attention to the logic of why these matrices were introduced and what exactly do they do to the input embeddings and how exactly it results in a much better context vector. So now with this much information, let's try to actually get into the lecture, where we are now going to see how can we transform the input embeddings before we take the dot product, so that we have some better attention weights, and then how can we use that attention weights to create a better context vector. Now you might have a question, what is wrong with the idea of dot product itself? Isn't it logically correct to take dot product? Yes, that idea is fundamentally correct, because if two vectors are in general pointing in similar directions, it means semantically they are related to each other more than, let's say, two vectors that are orthogonal to each other, because we know that the vectors are pointing into certain directions in this multi-dimensional space or three-dimensional space in our example, such that the direction of pointing has some significance. And the magnitude of these vectors are not all the same, they are different. The magnitude depends on how much information these vectors can give us. So for words like is, the, a, etc., which are very frequently occurring words in sentences, which does not give us any specific information, the magnitude of the vectors corresponding to these tokens will be very small. Whereas if we consider, let's say, words like quantum, these are not words that typically occur in our sentences. So the token corresponding to the word quantum will definitely have a bigger magnitude. The vector will have a higher magnitude. But the direction has definitely semantic significance. So fundamentally, the idea behind taking dot product is still valid. Why? Because if two vectors are generally pointing in the same direction, then maybe they should pay better attention to each other. And the best way to indicate this is by taking a dot product, because dot product of between two vectors that are pointing in the same direction will be a bigger number. Dot product between two vectors that are perfectly orthogonal to each other will be 0, because the dot product will be vector A times vector B times cosine of angle between them, and cosine of 90 degree is 0. So this idea makes sense. But the problem here is in the fact that we are taking the direct dot product of the input embeddings. That is where the issue is. So now what we are trying to do in today's lecture is we have to do something to the input embedding to transform it before taking the dot product. So read the sentence. We want to take the dot product. However, instead of directly taking the dot product of the input embeddings, we take the dot product of some transformed versions of the input embeddings. And how do we transform? This is exactly where the trainable parameters come into picture. So we transform these input embeddings using three matrices. So we usually denote those matrices using the terms WK. So weight matrix corresponding to key, weight matrix corresponding to query, and weight matrix corresponding to value. So these matrices define how we have to transform the input embeddings before we can take a dot product. Now, what is the meaning of this key, query, and value matrices? We'll get to understand that in the course of today's lecture. But here is a numerical example which might help you better understand what is the problem with just the vanilla dot product. Let's say you have this sentence: the dog chased the ball, but it couldn't catch it. Now here, this it word should pay more attention to what? This it refers to ball. So here, this it means dog. Couldn't catch, it means that the dog couldn't catch the ball, right? So this it is ideally more connected to ball than to the dog. Now let's say we want to construct attention scores between dog and it and ball and it. And let's say in the three-dimensional space, these are our vectors. So dog is 0.9, 0.1, 0.1. Ball is 0.1, 0.9, 0.1. And it is 0.5, 0.51. Now the dot product between dog and it will be 0.9 times 0.5 plus 0.1 times 0.5 plus 0.1 times 0.1, which results in 0.51. And same dot product results when you take the dot between ball and it. Same thing. So although the input embeddings are different, so these are three different input embeddings. When you take the dot product, the attention scores between dog and it and ball and it are exactly the same. So somehow taking the simple dot product from your basic input embeddings are not working here, right? So this is just a numerical example which is oversimplified, but it drives home the point that you should not be taking the direct dot product between the input embeddings if you want to avoid situations like this. So this is where the solution was introduced, was you transform the input embedding. So you transform queries using Q, the WQ matrix. You transform keys using a matrix called WK. So these are weight, W for weights. So this is the weight matrix corresponding to key. This is the weight matrix corresponding to query. And these are learned matrices. Why do we call it as learned matrices? Because the numbers inside these learned matrices will change as we train the large language model. Now let's say after training my large language model, I got this weight matrix WQ, and then this weight matrix for key WK. Now what happens if I transform my dog vector using WK? How do we transform first of all? So here the dog vector had a dimension of 1 by 3. The weight matrix has dimension 3 by 3. So the dog vector multiplied by weight matrix will give us again 1 by 3 matrix multiplied by 3 by 3 matrix will result in a 1 by 3 matrix. So this is now having the same dimensionality as that of the original dog vector, but it has transformed in values. So when we multiply the key weight matrix with the original input embedding for dog, we get 0.9, 0.2, 0.1. And when we use the key weight matrix with ball, we get these numbers. Now, the query that we are looking at is it, because we want to see how much attention it has to pay to dog and how much attention it has to pay to ball. So now query is it, which means it is transformed using WQ. And WQ is this matrix. So if you multiply this matrix with the original input embedding for it, which was 0.5, 0.5, 0.1, you get something like 0.5, 0.5, 0.1, because here you might notice this is just an identity matrix. Now, if we can try to calculate the attention score, if you take the dot product between the transformed it vector and the transformed dog vector, you get the number 0.56 if you take dot product between these two vectors. And similarly, if you take a dot product between the transformed it vector and transformed ball vector, you get the attention score or dot product 0.96. Now you see this attention score is capturing the fact better that it should pay better attention to ball than to dog, right? So how did this happen? Because we transformed the original dog vector, original ball vector, and original it vector using key matrices or query matrix, depending on which one is the query. So this gives you an intuition that indeed this transformation is useful, because if we do the transformation in the right way, our attention scores can be much more meaningful. Now, this is what we are going to discuss in today's lecture, but please remember this part of this figure. We are trying to solve the problem of context vector not being able to capture the dependencies in the sequence that well if we directly use the input embeddings for the dot product. So that problem we want to solve. So before the dot product, we want to transform the input embeddings. Now, by paying attention, what we mean is we are able to selectively access parts of the input sequence. So what do I mean by that? Here it is selectively accessing ball more. How? Because the attention score is 0.96 than the word dog, because attention score between it and dog is 0.56 after transforming, right? So paying attention is simply a fancy way to say you are attributing more importance, or the current query is attributing more importance to this particular key than other key. All right. So far so good. Now let's try to understand how exactly are we going to transform our input sequence using these matrices. What are the dimensions of these matrices? Then what are the outputs we get? And then what do we do with these outputs to finally get our context vector? So our end goal is to get a very good context vector. Okay. Now we are going to look at two example sentences. The first example sentence we'll focus on while understanding the theory of the query key and value. And then we'll take another example sentence while implementing the same in code. So the second half of today's lecture is entirely dedicated to us implementing the whole self-attention with trainable weights in code. Don't worry if the code looks intimidating. I'll walk you through step by step. So first, let's see what happens to our input embeddings. So this is our input embedding. The sentence that we are considering right now is the dog chased the ball. Now this sentence is split into 5 words. So we are considering each word to be one token. So we have 5 tokens. The dog chased the ball. So that is this first dimension over here, 5. Now each token is embedded in a 3-dimensional space. So the total number of, if this were to be represented as a matrix, it will be of dimension 5 by 3. 5 denotes the total number of tokens. 3 denotes the dimension of each token. Now, what we are going to do is we are going to now transform each and every one single of these input token into another space, a space that is having different dimensions. So the other space to which we are going to transform this using our trainable weight matrices may have a different dimension. So currently in this example, we are going to consider that space to have a dimension of 2. So instead of 3-dimensional space, now we are going to transform these 5 input tokens into a 2-dimensional space, right? So we have input tokens of size, we have 5 input tokens, each of them of size 3 dimension. And this is being now transformed into a 2-dimensional space. But we have 5 tokens, which means what we will end up is something like 5 by 2. So we introduce 3 matrices, one called query matrix, one called key matrix, and one called value matrix. These matrices perform the transformation of these input tokens into the 2-dimensional space. So if you multiply this matrix dimension is easy to understand. So this Q matrix, WQ matrix has a dimension of 3 by 2. So if you multiply a 5 by 3 matrix with a 3 by 2 matrix, you will get a 5 by 2 matrix. What is this? These are the transformed embeddings of every single input token in the query space. Query space has a dimension of 2. So these are the 5 transformed embeddings of every single input query. Dimension of each query now became 2 instead of 3. Similarly, the key matrix also has the weight matrix corresponding to key also has a dimension of 3 by 2. So if you multiply 5 by 3 matrix with 3 by 2 matrix, you get a 5 by 2 matrix. So now this is the key space, which is also of 2 dimensions. And every single key is now a 2-dimensional vector. So there are totally 5 vectors. So this dimension is 5. Same thing happens for value. Now key and query are easy to understand because we have discussed so far what is a key. So if we are considering how much attention should dog pay to all the words in the same sequence, then dog should maybe pay 10% attention to the, 20% attention to itself, 30% attention to chased, some X% attention to the, and some percentage attention to ball. So here dog is the query, and all the words in the same sequence are the keys, right? So we know what query and key is, but we don't know what value is yet. So we'll come to that, but I hope you understand now what are these transformed queries and transformed keys. It's simply some transformations happening to the input embeddings such that the dimensionality reduces from 3 to 2. Now what we can do is, let's look at this in terms of some numbers, okay? So that you can better appreciate what's happening here. So your input is 3 dimensions. So you have 1, 2, 3 dimensions. So 3 numbers to denote every vector. So this is the vector for this is the vector for dog. Like that, you have 5 vectors. So 5 by 3. Now let's say we have a trainable weight matrix corresponding to query. So WQ. And it's of dimension 3 by 2. So these are the 6 numbers corresponding to your trainable weight matrix for Q. Similarly, you have 2 more trainable weight matrices, trainable weight matrix for key, trainable weight matrix for value. Then you multiply this 5 by 3 matrix with a 3 by 2 matrix. So this X is the input vector, X times WQ. So this is not multiplied by symbol. This is just X. Okay. So X times WQ will result in the query matrix. Query matrix is nothing but the 2-dimensional representation of your input queries. So this is the 2-dimensional input, 2-dimensional representation corresponding to this is corresponding to dog, chased, then the ball. So earlier it was a 3-dimensional representation. Now it became a 2-dimensional representation. Same thing happens for key. But these numbers will be different. So the key matrix will be different from query matrix because the weights, the matrices that transform the input embeddings into Q and key are different. So these WQ and WK are 2 different matrices, which means the key corresponding to dog, chased, the ball, the key values will be different from your query values. See, 0.86, 1.22, here it is 1.07, 0.82. Now earlier, in simplified self-attention, what did we do? If we wanted to calculate how much attention dog should pay to what we did was, the query we multiplied with key. So if we want to know now how much attention dog should pay to we take this number 1.00, 0.07, 0.70. So this is the query vector corresponding to dog. We did a dot product between this and the key vector corresponding to So that was 1.07, 0.82. So when you do dot product, this times this plus this times this, you will get one single number, correct? So what you can do is, for dog, you can calculate attention it has to pay to attention it has to pay to dog, attention it has to pay to chased, attention it has to pay to the ball, etc. Similarly, for every single key, you can calculate an attention score corresponding to every single, for every single query, you can calculate an attention score corresponding to every single key. Which means, at the end of the day, if you have 5 vectors in your input, you will have 5 by 5, 25 attention scores as the final output. And how do you get 25 attention scores from this 5 by 2 matrix, which is key matrix? query matrix and 5 by 2 matrix, which is key, you can simply do Q multiplied by query transpose. And when you do that, when you do Q multiplied by query transpose, the result is you are multiplying a 5 by 2 matrix with a 2 by 5 matrix because you are taking transpose of key, which is 5 by 5. So that is what you will get. So here, this is the 5 by 2 matrix corresponding to query. This is the 2 by 5 matrix, which is the transpose of key. You multiply these two to get the 5 by 5 matrix, which is now the attention scores. These are not the attention weights. These are the attention scores. Now, you might notice one thing with these attention scores. Now, these are the dog chased the ball. So now, if dog is our current query, these are the attention scores that dog should pay to each and every word in the sequence. So dog should pay 1.57 attention to the, 1.71 attention to dog itself, 1.89 attention to chased, 1.26 attention to the, and 1.97 attention to ball. But these are attention scores. So these numbers do not add up to 1. But if these 5 numbers were adding up to 1, it was easy for us to say dog must pay 20% attention to this particular token or 10% attention to this token. So it's more interpretable. And if these numbers are very nicely between 0 and 1, it's also really good for training, because for training stability of neural networks, it's better to have normalized numbers. So what we have to do is we have to convert these attention scores into attention weights. So what we do is, firstly, let's pick up the attention score for just ball. So what are the attention scores corresponding to ball? We should have 5 numbers. So just to go back to our earlier diagram, the conceptual diagram. So we were here, we had input sequence using query, key and weight trainable matrices. We converted this into query space. So all the 5 input embeddings were converted into query space, which had only 2 dimensions. We also created all the input tokens were converted into key space with 2 dimensions and also value space. So far we haven't discussed about value yet, but we'll come to that, right? But for this conversion, what did we do? Simply, we multiplied the input sequence with WQ, WK, WV. So that resulted in query vector, key vector and value vector for dream. Same for big, same for and, work for it. So this is a different sequence. The sequence that we are currently discussing is the dog chase the ball. But for any sequence, this is essentially how it works. You take the tokens in the sequence, you multiply individual tokens with W matrices. So if you multiply the input token with the WQ, you will get Q of 1. Of 1 means of the first input token, X of 1. Similarly, if you multiply X of 5, which is the 5th item in the input sequence, with WQ, you get Q of 5, which is the 5th query vector. Then what we have to do is we constructed attention scores. So to construct attention scores, we did not use value vector at all. So value vector we are still not looking at. So just ignore this part for a moment. What we did was we simply took a dot product between query vector and key vector. So if we want to calculate the attention between, let's say, query, which is big. So in this sentence, so this is a different sequence, but same example. If the sequence is dream big and work for it, which is the same sequence that we are going to use in our example code, dream big and work for it. Here, if let's say our query is big, we just want to calculate how much attention big should pay to dream and work for it, as well as to itself, to big itself. Then we want to do the dot product between Q of 2 and K of 1. Q of 2 is the query in the second item, which is query corresponding to X of 2. K of 1 is key corresponding to the first item in the sequence, which is key corresponding to dream. And then we get the attention score. So this is the attention that big has to pay to dream. Similarly, this is the attention big has to pay to 4. To get the attention, we are simply taking the dot product between query and key. Okay. Now, so far so good, but these are attention scores. So these omegas do not add up to 1. And we saw that kind of in this example. So here, these numbers do not add up to 1. Now, if we take attention scores for ball, these are the attention scores corresponding to ball. So now we are back to our original sentence, which is the dog chased the ball. Now for this sequence, if you add up the numbers, it's not adding up to 1. So what we do is, here is where we introduce the idea of scaling and softmax. So scaling is done for a very particular reason, which I will discuss in a moment. But by scaling, what I mean is these numbers are divided by square root of d, where d is the dimension of the key space. So please note our input dimension or input embedding space in our example had a dimension of 3. It was a 3-dimensional space. But the key space or query space or value space, the dimension is 2. So we are dividing these numbers by square root of 2. So when you divide by these numbers, you get now the scaled attention scores. So these are scaled attention scores. Now these attention scores again do not add up to 1 because we are yet to convert it into softmax probability distribution. So we convert it into softmax probability distribution using this formula, e raised to xi divided by sigma e raised to xi. So when you do that, you get your attention weights. So now these attention weights are numbers which will add up to 1. So this is how you go from these numbers. So these are attention scores. You go from attention score to scaled attention score. And then you go from scaled attention score to attention weights. And these attention weights are now numbers that will add up to 1. Now you can say, so here ball is my query. Okay, because we are now just focusing on what happens to this one row corresponding to ball is the query. Now these scale attention weights tell us ball should pay 17% attention to the first token. First token is the. It should pay 19% attention to second token. It is dog, right? So it was the dog chased the ball. So ball as a query should pay 17% attention to the, it should pay 19% to dog, it should pay 23% attention to chased, 13% attention to this second the, and 29% attention to itself. And when you add this 29 plus 13, 42, 52, 62, 65, 75, 84, and then 94, 101. So I think it's 101 because we have rounded off certain numbers. So this is how you construct attention weights. Now so far it's good, right? So now let's go back to our original diagram. We are not still discussing about value, but we'll come to that in a moment. But let's just go back. So you got attention scores, and attention scores were the result of the dot product between Q and key transpose. Q was 5 by 2 because you had 5 vectors. The dog chased the ball. 2 because the query space has a dimension of 2. Key space has a dimension of 2. Value space has a dimension of 2. Key transpose will be 2 by 5, right? And then when you multiply these two matrices, you get 5 by 5. Now these are attention scores. These are the attention scores for the query the. These are the scores for dog chased the ball. All right. Now these attention scores, if you consider query for ball is simply, ball is first of all a 1 by 2 vector now in the query space. But key matrix is 2 by 5, right? So key matrix here, key transpose matrix was 2 by 5. And query for ball was this guy. So if you simply multiply just this vector, so if you only consider that vector, it will be a 1 by 2 vector. A 1 by 2 vector, when you multiply by a 2 by 5 vector, you will get a 1 by 5 vector. And that will be this last row. So that will be the attention scores for the not key equal to ball, but query equal to ball. So you can even individually pick up vectors from this and multiply with the transpose of key to get the corresponding attention score. Now, once you get attention scores, they are not attention weights. You convert the attention score. So this is not key query. These attention scores are scaled by 1 by square root of d. D of what? D is the dimension of the key space, 1 by square root of dk. In our case, it's 1 by square root of 2. The reason why we are doing this is because we want the variance to be 1. I will explain this in a short moment. Why exactly does 1 by square root of d scaling works, or why is it not 1 by d, or why is it not some other number? We'll explain. I'll discuss that in a moment. But after this scaling is done, the numbers in this vector will reduce, right? Because now you are dividing by some number that is greater than 1. And then you take softmax operation. So after you take the softmax operation, you get attention scores for the query ball. Now these are attention weights, not attention scores, because they sum up to 1. Now attention weights are what we need to construct the final context vector corresponding to ball. Now it's a good time to take a look at what is value. In the simplified self-attention we implemented in the previous lecture, do you remember what we had done? What we had done was, we said the context vector equal to attention weighted sum of the input vectors. Sum of input vectors, right? So if we were considering the context vector corresponding to one particular query, we looked at all the attention weights between that input query and all the keys, and then we got the attention weights. So first we got the attention scores, then we normalized it to get attention weights, and we simply multiplied the input vectors with the corresponding attention weights and then added them up. So we were as if we were doing some vector addition, and this vector addition resulted in a new vector, and that vector was the context vector. And this we could do for every single vector in the input sequence. This is what we did in the simplified self-attention. Here also we are going to do attention weighted sum of some vectors. However, we are not going to be using attention weighted sum of the input vectors, but we are going to be doing attention weighted sum of transformed input vectors. What do I mean by attention weighted sum of transformed input vectors? What I mean by that is, we won't be using input vectors directly. We will be using input vectors that have been transformed into the value space. So the transformed input vector in the current example that we are considering will not have 3 dimensions. It will have only 2 dimensions. And we take the attention weighted sum of this 2-dimensional vectors in the value space to get the final context vector. So context vector will also have only 2 dimensions. In GPT, after the vector comes out of the multi-head attention, its dimensionality is retained. Dimensionality does not reduce. Here actually the dimensionality is reducing from 3 to 2. But don't worry, this is just an example, right? In reality, most large language models will not change the dimensionality of the input embedding as it passes through the multi-head attention. Now, let's discuss a little bit why square root of d. Why exactly did we divide the numbers by 1 by square root of d? So there are 2 reasons for this. First one is softmax. When we take softmax of some big numbers or scale numbers, it can become very steep. Let me first demonstrate to you that in code, what I mean by that. And then afterwards, I can show you the rest of the code. So first let's discuss what happens when you scale some numbers. So let's consider these set of 5 numbers. Okay. So let's say I have a tensor or vector with 5 numbers. And if I simply take the softmax, I get the result is this. It becomes a probability distribution, and sum total of these numbers are 1. And it will also, the numbers will also be between 0 and 1. Now let's say I multiply all these numbers by 8. So basically I am multiplying it by a scaling factor. When I multiply this by a scaling factor, look at what happened to my softmax. My softmax distribution now, again, it will sum up to 1, but it is now so much sharp because these numbers are now so small. The fifth number is now much bigger. 80% is the fifth number, but these numbers became so small. On the other hand, the softmax before scaling was a bit more, even distribution. So during the training of large language models, we don't want the final dot product output to be, such a peaky kind of numbers. We don't want such peaky numbers. We want numbers that look more like this. So to prevent softmax from giving us outputs like this, we have to scale the numbers appropriately. So if the original set of numbers were these numbers multiplied by 8, we had to divide those numbers by 1 by 8 to get good set of softmax numbers, distribution numbers like this. So only then we can say that, okay, this much 14% attention is paid to this, 20% attention to this, etc., etc. We don't want the entire attention to be just paid to one token. We don't want extremely peaky distribution of the softmax. So that is one reason. Second reason is that we want to make the variance of the dot product of query multiplied by key transpose somewhat stable. I'll show you this with a simple example. So here in this code, what I'm doing is I'm generating 1000 set of random query and key matrices. So q equal to np.random.randn will generate from a normal distribution. It will pick n number of random numbers corresponding to whatever dimension we feed. So if we say I need a 5-dimensional query matrix, this will generate 5-dimensional query vector, which are random numbers. And then I will do that 1000 times. And then what we are printing here is, we are printing the variance of the resulting dot product. Dot product of what? Dot product between query and transpose of key. So if I have a query vector of, let's say, 5 dimensions, and I have a key vector of again 5 dimensions, I take the query multiplied by transpose of key. So that will be simply one number because dot product between two vectors will be one scalar. So if I'm conducting 1000 experiments, I will have 1000 dot products, right? And this itself we can do for two different dimensions, for a dimension of 5-dimensional query and 20-dimensional query. Okay, so let's keep this as 20. This is 20. Okay, so now let's run the code and see what happens. Okay, so just see this. The variance of my dot products, if the dimension is 5, is around 4.56. So it's on the order of 5. Variance of the dot product for a 20-dimensional space is on the order of 20. Right? So here you can see that as the dimensionality of my key query value space increases, the variance of my q dot key transpose, the variance of my attention scores are now increasing. I don't want this because this will result in unstable training. Because what if my dimensionality of the key query value space is 128, or if it's on the order of 100, what will happen? I can simply change these numbers to 100. So 100. So now the dimensionality is 100. See, my variance before scaling now became on the order of 100. So as the dimensionality increases, the attention scores, which is the dot product between query and key, becomes so much it will experience so much variation, which is not good for the LLM training. So what I want is, I want some stability. I don't want these numbers to experience so much highly scalable variance with respect to my dimension of the key query value space. So if you divide by square root of d, so here, for example, just see this line, scaled dot product equal to the actual dot product between query and key divided by NP. NP is numpy dot square root of whatever is the dimension. So 1 by square root of d. When you do that, look at the scaled numbers. So variance after scaling for 5 dimensions, it's close to 1. Variance after scaling for 100 dimensions, it's also close to 1. Now, what if I had not put 1 by square root of d? What if I just put 1 by d? What will happen to the variance in that case? See, when I divide by 1 by d, the variance is again not scaling approximately close to 1. See, now as you increase the number of dimensions, your variance is decreasing. So the variance for your 5-dimensional query space was 0.18. Variance for 100-dimensional query space was 0.01. This is also not good. You want stability while training, and the stability should not be affected by your choice of number of dimensions in your key query value space. So that is the reason why you divide by square root of d, because when you divide by square root of d, your variance is also scaling by square root of d. So the scaling happening in the variance will get cancelled out because you have a square root of d division happening. So this is why we are dividing exactly by square root of d before we pass the attention weights into Softmax function. Now, just to recap what all we discussed, we had input vectors, and we discussed that simple dot product was what was done. Before, in simplified self-attention, we took simple dot product, but we saw the issue with respect to simple dot product for calculating attention scores, because simple dot product sometimes may not give us good attention scores, which will help us eventually to get good context vectors. So simple dot product was not enough. So we decided we will not be taking simple dot product. We will be rather taking dot product of something else. And what is that? We will be taking dot product of transformed input vectors. So we defined two transformations, one transformation for queries and one transformation for keys. For that, we defined the query matrix WQ and key matrix WK. Our input was 5 by 3 in the example that we took, because we had 5 words in the sequence and the vector dimension was 3. It was in a 3-dimensional space. But this WQ was 3 by 2 dimension, WK was 3 by 2 dimension. So the resulting query matrix and resulting key matrix was of dimension 5 by 2. So what happened was my 5 by 3 input sequence got transformed into 2 separate set of sequences. One sequence corresponding to query in a 2-dimensional space, another set of sequence in the key space, which is also 2-dimensional. Then what we said was, instead of taking softmax of the query.key transpose, so query.key transpose is the dot product, we take the scaled dot product. So we do the dot product, but then whatever we get, which are called the attention scores, we scale it by dividing by square root of the dimensionality of the key space. And then we take softmax of this. So softmax of q dot k transpose divided by square root of dimensionality of the key space. And what does this give us? This gives us attention weights. And if you go to the paper, that is exactly what you have in the bracket, in the softmax here. So softmax of q times key transpose divided by square root of the dimensionality of the key space. Now comes the value. So I hope you are now able to make better sense of the equation presented in the attention is all you need paper. Now what do we do with this attention weights? In our vanilla dot product, so let me just delete this thing. In our simplified self-attention, we use these simple dot products as the attention weights, as the attention scores. Then we used softmax to convert that into the attention weights. And then we use these attention weights to multiply the attention weight with the input embedding. So this input embedding was directly used so that we constructed an attention weighted input embedding to create the context vector for any given query, right? However, that is not what we are going to do here. We have the attention weights, and instead of multiplying these attention weights with the input embedding X, so if we were not having the value matrix, what we would have done was softmax of q dot key transpose divided by square root of dimensionality of the key space multiplied by X, where X is the input embedding. This is what we would have done. Something like this. Not exactly this, something like this. But in the paper, you don't see, you are not directly multiplying with X. You are not directly multiplying with the input embedding. You are multiplying with the transformed input embedding, so that you can, use trainable weights to change the values of the input embedding to be more suitable to produce a better context vector. So here, instead of multiplying it directly with the input embedding, you are multiplying it with the value vectors. So that is why here you have V. Now, how is value calculated? If we go back to our diagram, value is calculated over here. Value is also a 5 by 2 matrix. Why? Because you have here 5 input tokens, 2-dimensional space. Value space is also 2-dimensional. So you multiply 5 by 3 input matrix with the 3 by 2 transformation matrix. So now this is the trainable matrix for values. So 5 by 3 multiplied by 3 by 2 results in 5 by 2. This is value. Now this 5 by 2 is used to be multiplied with the attention weights. By the way, attention weights was of what dimension? Softmax of query dot key transpose divided by square root of dk. What was the dimensionality of this? We had 5 numbers in the input, which means we have 5 queries and 5 keys, right? So this had a dimensionality of 5 by 5. Now this, when we multiply with a 5 by 2, V, so this is now dimensionality of V, this is the dimensionality of this equation, we will get 5 by 2 dimensional context vectors. 5 by 2 dimensional context vectors meaning there are 5 vectors, each vector has a dimension of 2. How many vectors did we have in our input sequence? We had 5 vectors. And our goal was to produce context vectors for every single vector in the input sequence. We wanted to construct context vectors corresponding to every single vector in the input sequence. Input sequence was of a dimensionality 3 because it was in a 3-dimensional space, but then we decided to transform it into a 2-dimensional space using key, query, and value weight matrices, which are trainable matrices. So at the end of the day, we are expecting 5 context vectors corresponding to each input token, but the dimensionality of this, the new space will be 2-dimensional, which is why it turns out to be 5 by 2. So now let's go back to the numbers that we had to see how this looks like. So the numbers that we were looking at was this, right? So we had scale attention scores, and then we got the attention weights. Now these attention weights are the attention weights for ball. But now what we want to calculate is, we want to calculate the context vector corresponding to ball. Context vector will be a 2-dimensional vector. How do we get the 2-dimensional vector? This 1 by 5 matrix will be multiplied by, so these are the attention weights. We multiply this by what? We multiply this by value matrix. Value matrix is 5 by 2. And where is that? Value matrix is over here. This 5 by 2 matrix. So let me go back here. So the context vector is normalized attention weights. Not just normalized, you scaled the attention scores by square root of D. Then you took the softmax. So this became attention weights. Now you have how many attention weights? Attention weights are 5 by 5. If you look at just the attention weights corresponding to one query, it is simply 1 by 5. So here the query is bald, so it is simply 1 by 5. Value matrix, you have 5 value vectors, and each vector has a dimension of 2. So value matrix was of dimension 5 by 2. So 1 by 5 multiplied by 5 by 2 will be 1 by 2. So these are the attention weights for ball. So this is how much attention ball should pay to the, to dog, chased, the, and ball itself. And this is the value matrix. So this is the value vector corresponding to the value vector corresponding to a dog chased the ball, and 1 by 5 multiplied by 5 by 2 will be 1 by 2. So now this is the context vector for ball. The initial vector of ball was this. The input embedding of ball was this 1.2, 1.7, 1.5. So it was a three-dimensional vector, and it had some information present in it, but it had no context because this was purely the semantic meaning associated with ball. It did not carry the information or the fact that dog chased the etc. Those words are also present in the sequence. That information was not present in the input sequence. But now, finally, when this guy, this 1.2, 1.7, 0.5, by the time it gets transformed through the query key value matrices and through attention weights, and finally when it turns into a context vector, you have these numbers 1.41, 0.91. Like that, I have context vector for dog chased the, and finally ball. So there will be 1 by 2 for the, 1 by 2 for chased, 1 by 2 for dog, and 1 by 2 for the initial the, which means the final matrix that results will be a 5 by 2 matrix. And it would look like 5 by 2 matrix, where the first row corresponds to the context vector for the dog chased the ball. And what was the initial token embedding? It was this. It was a 5 by 3 matrix. Initial embedding of the 5 tokens were each 3-dimensional. Then there were 5 such tokens. So each of them looked like this. And then finally they got transformed into a 5 by 2 set of, 5 set of 2-dimensional context vectors. So this is exactly what we do with the value matrix. So we use value matrix like this. Let's go down. So these are now the attention weights. So attention weights are multiplied with my value matrix. There are inside the value matrix, there are 5 value vectors, each value vector corresponding to each token. Each token has a dimensionality of 2. So 5 by 5 matrix multiplied by 5 by 2 matrix results in 5 by 2 matrix. Now these are the context vectors corresponding to my 5 input tokens. Each input token was of 3 dimensions, but now it became 2-dimensional. Now this context vector is now much more useful because it's much more rich in context or in meaning. Now let's do one thing. Let's implement all of this in code, right? And then we will come back and discuss a few more things. But just before proceeding ahead, so if our attention weights are like this, so ball should pay 10% attention to the, 30% to dog, 30 to dog chased the ball, then we multiply that by v to get the final context vector, right? So we will discuss this diagram in a little bit, but let's first go to code and try to implement this whole thing one by one. So this is my new input sequence. Dream big and work for it. So there are 6 numbers in my sequence, but my input dimensionality I'm still keeping as 3 dimensions. So it's easy to plot. So I'm using PyTorch so that we can construct these tensors. So this is corresponding the input embedding of dream for big and work for it, right? So these are the words. Let's just run this so that it's initialized. Now, if I want to get the vector corresponding to, let's say, the second word in the sequence, which is big, I just need to say inputs of 1 because Python indexing starts from 0. So inputs of 1 is the vector corresponding to the second token. So if we say print x underscore 2, we can see that vector. So 0.75, 0.2, 0.55, which is exactly this guy, right? So the shape of these vectors also we can print d underscore in. So the dimensionality of the input sequence is 3 and dimensionality of the output sequence, which we are defining to be 2. And what does it mean by dimensionality of output sequence? I just simply mean dimensionality of the context vectors which results from the key query value operations. So dimensionality at the output is 2. So this is my input vector corresponding to big, which has 3 dimensions. And now we are trying to convert this into a 2-dimensional context vector. Okay, so first, let's start by randomly initializing the weight, the key query and value weight matrices. So here torch.rand will create a random number matrix of the dimension d in comma d out, which will be 3 by 2. And this will construct 3 matrices: query matrix, key matrix, and value. Here the seed 1, 2, 3 is provided for code repeatability, so that although it's a random number generator, we are seeding the random number generator with an input seed, so that same random numbers will be generated irrespective of who is running the code. If you don't provide this, each time it will produce different random numbers. So if I run this, it would have produced now the WQ, WK, and WV matrices. Now we can print a sample matrix here. So if we print W query, the query matrix is 3 by 2. Why 3 by 2? Because my input numbers are 5 by 3. I have 6 by 3. I have 6 words in the sequence, and each word is 3-dimensional. So now I have 6 words. In my previous example, there were only 5 words. So 6 by 3 is the input. 3 by 2 is the WQ, which means the output will be 6 by 2. Because I'm converting 6 input tokens in a 3-dimensional space to 6 vectors in the query space with 2 dimensions. Similarly, W key will also be 3 by 2 and W value will be 3 by 2. And these are random numbers generated from the random number generator. Now, if I want to pick the converted query for the second item in the input sequence. What is the second item in the input sequence? It is big. So I want to see how this big is transformed in the query space. So what happens to this big in the query space? It will of course become a 2-dimensional vector. That much is clear. Now what would that 2-dimensional vector look like? To know what it will look like, all I need to do is I do x underscore 2 multiplied by the query weight matrix. So this will be the query corresponding to the second token. This will be the key corresponding to second token, which is x underscore 2. By the way, x underscore 2 is this. We had already defined it here. X underscore 2 is the first row in the input sequence, which is the input vector corresponding to big. And x underscore multiplied by w value. So this at signifies matrix multiplication in Python. So x underscore 2 multiplied by w value will give us the value vector. So now this is the query vector corresponding to big, and we can also print the key vector corresponding to big. This is a key vector corresponding to big, and this is the value vector corresponding to big. Every single one of them will be of 2 dimensions. So this is the key vector for big. This is the query vector. Sorry, this is the query vector for big, key vector for big, and value vector for big. So this is how the 3-dimensional big vector is converted into 2-dimensional vectors in the key, query, and value space. Now let's calculate the entire QKV matrix, not just one vector. Like that, we should have 6 vectors because we have 6 input words in the input sequence. So keys are nothing but, so instead of just picking one of the items from the input, instead of picking just one row from the input, take the entire input matrix. Entire input matrix was 6 by 3 dimensions. W key was of 3 by 2 dimensions. So key will be of 6 by 2 dimension, value will be 6 by 2, query will be 6 by 2. So here when we print the shape, you can see that the shape is 6 by 2. We can also print the actual numbers. So print keys, then print queries, and print values. These will be 6 by 2 dimensions. So this is now the key matrix, query matrix, and value matrix. So if I just focus on query, this is the query vector corresponding to dream, big, and work, and work for it or something, right? Sorry, this is dream. Dream, big and work for it. That was our sequence. So now these are the 6 vectors in the query space corresponding to 6 vectors in the input sequence. Now let's pick just one query and one key and see what is the attention score between them. Not attention weight, just the attention score. Now please remember, what is the attention score? Attention score is nothing but dot product between query and key, right? So if we take one particular key and one particular value, one particular query. So one particular query that we are taking here is query underscore 2. Query underscore 2 is this guy. Query underscore 2 is query corresponding to the input word big. Then key underscore 2 is key corresponding to the input word big. So keys of 1 means key corresponding to big. Keys of 0 would have been key corresponding to dream, dream big and work for it, right? So keys of 3 means dream big and work. So it will be corresponding to work. So here we want to see the attention score between big and itself. If you want the attention score between big and itself meaning between big and big. Big is the query, big is the key also. It will be keys of 1, and attention score between second query and second key. So that is why it's called attention score underscore 22. It is 0.6990. So in the attention score matrix, this item should be where? This should be along the diagonal. Why? Because our attention score matrix will look like this. Dream, big, and work for it. Then same thing goes here. Dream, big, and work for it. Now if my query is big, and if I'm trying to calculate the attention score between big as the query and big as the key, it will be here. This is the position, right? So in my final attention score matrix, which will be a 6 by 6 matrix, the position will be second row and second column. So we'll see whether the second row, second column items value is, whether it's 0.6990 or not. That we will check. Now we can also calculate attention score between big and every single token or every single key. That will be the query, which is big, multiplied by the entire key matrix. So entire key matrix is keys, and then you are taking transpose of that is the matrix multiplication. So here we are just taking the key vector corresponding to big, and you are multiplying it with the, query vector corresponding to big, and you are multiplying that with the key matrix to get the attention score. So now these are the attention scores, which denotes the attention big has to pay with dream, big, and work for it. Now, obviously, these attention scores will not add up to 1 because we have not, first of all, normalized. We have not scaled it. We have not passed this through Softmax. So these will not add up to 1. Now, if I want to see the whole attention score, I can simply run this. So attention scores are nothing but query multiplied by key transpose. Query is a 6 by 2 matrix. Key is also a 6 by 2 matrix. When you transpose it, it will become 2 by 6. So queries multiplied by key transpose will be 6 by 6. And let's just check the second row and second column, which will be this item. See, this is the attention that big as a query pays to itself, right? And we calculated it here. This was 0.6990, and here indeed you can see that it's 0.6990. So this is now the attention scores for big. This is the attention scores for dream. So dream, big, and work for it. So if I suddenly ask you, how much attention should it pay to dream? It is the last item in the sequence, which means you will go to the last row. And how much attention should it pay to dream? And dream is the first item, which means this is the attention score that you have to look at. So dream will be looking at it will be looking at dream with an attention score of 0.6680, which means it is attending to it. It's giving that much importance. Now these numbers are okay in terms of importance, but it's not giving us an interpretable picture. For that, we have to scale it down by square root of d and take softmax. So we first divide these numbers by square root of d, And let's see when we divide just these numbers by square root of d, and here d is 2. Two-dimensional space is what we are considering in our key query value space. So we'll divide by square root of 2, which is 1.414. So when you divide, instead of now these numbers, so let's do one thing. I will just copy paste this here. So print both attention scores and attention weights. So the first set of numbers are attention scores corresponding to big. These are now attention weights corresponding to big. And here you can see that we have divided by the square root of the dimensionality of the key space. And we have also taken Softmax from the PyTorch library. So these are now the normalized, or these are the attention weights. And this will sum up to 15 plus 15, 30. This is 40 plus 8, 48 plus 48 point something. 58, 65, 75, 81. 91, 98, and some residue, some remaining numbers will add up to 100. We already discussed why we are dividing by square root of d for two reasons. One is softmax. We don't want the softmax numbers to peak. And second is we want the variance of the dot product between query and key transpose, which is basically the attention scores. We want the variance of those numbers to be close to 1. So that's the reason why we are dividing by square root of d. Now that we have the attention weights, we just have the attention weights for big. We don't have the attention weights for all tokens yet. For that, we have to do what? Instead of query underscore 2 multiplied by keys dot transpose, and instead of just normalizing attention weights for just the second item, we have to do that for all items. So instead of attention scores underscore 2, I should do something like this. Attention scores equal to query multiplied by keys dot transpose, and then here I should use attention scores and divide by square root of dimension and call this as attention weights, and then print attention weights. This I can delete. If I do something like this is queries, then I should have attention weights. So let's run this. Now these are the 6 by 6 attention weights, and each row will individually sum up to 1. So how do we ensure that each row is actually summing up to 1, not each column? By giving this parameter. So dimension equal to -1 ensures that equal to -1 means you will look at the last dimension of whatever tensor you have. So here you have a 2-dimensional matrix. So last dimension is column. First dimension is row. Second dimension is column, which means last dimension is column. So you will apply the softmax such that each row will sum up to 1. So now the sum of these 6 numbers will be 1. Sum of these 6 numbers will be 1. However, the sum of the first column will not be 1. That you can try yourself. This is 15, right? 15 multiplied by 6, or you can pick anyone. Yeah, see this 17. These are all 17. 17 multiplied by 6 is what? 17 times 2 is 34, 51. This is definitely greater than 100. So these are the attention weights. So I have the code once again written here for attention weights. This we have already discussed. So attention weights. Let's come back to the attention weights, entire attention weight matrix a little bit later. Let's first focus on the attention weights for the second item, which is big. So attention weights 2, query underscore 2. Okay, so this is what we wanted. So now we have the attention weights corresponding to big. And now let's calculate the context vector corresponding to big. So context vector is nothing but attention weighted values. In the simplified self-attention, it was attention weighted input vectors. But here we don't use input vectors directly. We use transformed input vectors. So it is attention weighted values. So attention weighted values are this. So these are the attention weights for the second item, which is big, multiplied by the value matrix to get the context vector corresponding to big. So now the context vector corresponding to big is this, which is in the 2-dimensional space because our key query value space is 2-dimensional. So now our input vector, which was big, which initially had these numbers, where is big? Big was these 3 numbers, 0.75, 0.2, 0.55, got transformed into a context vector, which has much more information about what other words are next to it. like in this format, right? So this is what we can do. And if I want the context vector for all the input numbers, what I can do is attention underscore weights. I can just bring this code from here. So attention weights equal to softmax of attention scores divided by square root of d. So d multiplied star 0.5 means it's square root, d raised to 0.5. And then attention weights are these, and I don't want to print this. So if I do this, I got 6 by 6. And then here context vector, the entire context vector will be context underscore vector equal to attention underscore weights multiplied by values matrix. So values matrix was 6 by 2. Attention weights is 6 by 6. So 6 by 6 matrix multiplied by 6 by 2 matrix resulting 6 by 2 matrix. And I can print just the context vector. So this should be what? I should have 6 vectors of each dimensions 2. It should be 6 by 2. So if I print this, this is 6 by 2. This is the context vector for dream, big, and work for it. So at the starting, we had 6 input vectors, each 3 dimensions. Now we have 6 context vectors, each 2 dimensions. We can also convert this whole operation into a cleaner Python class. So in Python class, we can simply say class self-attention. So this self-attention v1 is just one Python class that we have defined. I'll show you one more variant of the same Python class. So we initialize the random weight matrices for query, key, and value. So this nn.parameter is one way to do that, but in another Python class, we are using nn.linear. So for neural network training, to initialize these numbers in a much more optimized way, which also includes bias. So usually when we are multiplying with weight matrix, we just don't have weights, right? We also add bias. So usually in neural network, we have weights parameters which multiplies with the input, but then we add that with bias, right? So here we also introduce bias. But I don't want to spend too much time on this. All I want to show you is that whatever we have done above can now be summarized into maybe like 10-15 lines of code. So we initialize the random weights for query, key, and value. Then key is equal to input multiplied by w key, query equal to input multiplied by w query, value equal to input multiplied by w value. So self.w value is the way classes reference to that particular instance of this variable. And all we need to do now is, if we define a class like this, and if we want to run this operation again and again and again, we just need to instantiate the class by creating an object. So that's the reason why in Python, many libraries define functions inside classes, so that you can define instances of those classes as objects and use it as many number of times. Then attention scores are query multiplied by key transpose. Attention weights, for attention weights, what you do is attention scores are divided by square root of d, and then you take softmax. And then attention weights are used to multiply with the value matrix to get the context vector. That's it. You get the context vector now. So I hope this part is very, very clear. You should definitely try running some similar version of this code yourself. Now, although the weights are trainable, we are not going to train it right now, because then we'll have to define the entire large language model architecture and define backpropagation and everything. But just understand that the random numbers that we initialized in the weight matrices for query, key, and value, those will not be random after training. Those numbers will evolve to produce better and better context vectors. Now, let's go back to the nodes. So how is input embedding now converted into context vector? So let's say these are our input embeddings, these vectors. This is the input embedding for the. So now we are back to our other sentence. The dog chased the ball. Okay. The dog chased the ball. Okay. And now let's say I want to calculate the context vector corresponding to ball. So now ball is my query. So first what I will do is I will calculate attention weights, and I will multiply. You can imagine these vectors being multiplied by your corresponding attention weight. So the will be multiplied by the attention weight between the and ball. Dog will be multiplied by the attention weight between dog and ball. Chase will be multiplied by the attention weight between chase and ball. So if the attention weights are like this, 0.1, 0.3, 0.3, 0.1, 0.2, these numbers add up to 1, 0.6, 0.7, 0.8, 0.9, 1.0. So this is now the attention weights corresponding to ball. So how much attention ball should pay to each vector, right? So you can imagine it to be something like this. In the simplified self-attention, what we did was we multiplied the initial context vectors with these numbers. Initial context vector was multiplied by 0.1, initial context vector was multiplied by 0.3, and this is the context vector for the is multiplied by 0.1, dog is multiplied by 0.3, which means the length of the dog will be reduced to 30%. Chased will be multiplied by 0.3, which means length of that vector will be reduced to 30%. This will be reduced to 10%. This will be reduced to 20%. And then you will get these attention weighted or attention multiplied vectors, these 6 vectors or 5 vectors rather. Then you add all of them to get the final context vector. So this is what we did in the simplified self-attention. In the current self-attention, which is self-attention with trainable weights, most of the things remain the same, except the only difference is now this is not the input embedding anymore. This is the value vector for the. This is the value vector for dog. This is the value vector for chased. This is the value vector for the, and this is the value vector for ball. Then these numbers 0.1, 0.3, 0.3, 0.1, 0.1, 0.2 are the resulting attention weights which came from the dot product between query and transpose of key. Then we did square root of dk and we did softmax. So these attention weights are the result of this mathematical operation. Then what we do is these value vectors are scaled using these attention weights, and then you sum up those weighted vectors. So then again you sum up those weighted vectors to create the context vector for the ball. So basically whatever you get from this, you multiply that with your value vector. So this is now a matrix. This is not a single vector anymore in this equation. So that is what you have in the attention is all you need paper. Now if you go back to that equation, right? How do you read this formula? What does this mean? Attention of query, key and value. What this means is if you have an input sequence, how much attention should each token pay to all the tokens in the input sequence when you convert those tokens into query, key and value space? That is the question that we are asking here. So tokens are not anymore in the input embedding space of 3 dimensions in our example. It is in 2 dimensions because the query, key and value space are each in 2 dimensions. So how much attention should each token pay to rest of the tokens in the input sequence? The answer to that is the amount of attention that we should pay should be such that you are calculating context vectors. So every single vector in the input sequence is converted into a context vector using this formula. So this is the formula for getting the context vector. And how is that done? Context vector is created from value vectors. Are value vectors directly used for getting the context vector? No. Value vectors are scaled and added to get the context vector. And how is the scaling done? Scaling is done using attention weights. How are the attention weights created? Attention weights are created by taking query.key transpose, and to get more stable variance you divide by square root of the dimension of the key space, and then you take softmax so that you have weights summing up to 1 for every single token. So those weights for every single query you will have, let's say you have 5 queries, meaning 5 input tokens. you will have, for every query, you will have 5 attention weights. So you sum up the values, which are again 2-dimensional vectors. You will have 5 2-dimensional vectors. You sum up those 2-dimensional vectors according to corresponding attention weights. So you multiply attention weight with one query vector, you multiply attention weight with the next attention weight with the corresponding query vector, and then you add up those vectors to get the resulting context vector of your input sequence. So if we were to write in terms of dimensionality, the dog chased the ball. So this is an input sequence with 5 words. The dog chased the ball. Each word is represented by a 3-dimensional vector. Then this is multiplied by WQ, which is 3 by 2, to get a 5 by 2 matrix, which is the Q matrix. This is multiplied by WK, which is a 3 by 2 matrix to get a 5 by 2 matrix, which is the key. This is also multiplied by W value, which is 3 by 2 to get 5 by 2. These are 5 value vectors. So these are 5 Q vectors, 5 key vectors, and 5 value vectors. Then you take the dot product of these two such that Q dot key transpose will give you attention scores. So you will have a 5 by 5 matrix, 25 attention scores. Then you divide these attention scores by square root of D, and then you pass it through Softmax to get attention weights. So this will again be a matrix of dimension 5 by 5. Then what do you do with these attention weights? Do you multiply that directly with the input embedding? No. You use that with the value. So your value is now 5 by 2 and your attention weights are 5 by 5. You multiply these two matrices to result in a 5 by 2 matrix. Now what is this matrix? These are 5 context vectors corresponding to your 5 input tokens. So you had input tokens for 5, but they were in a 3-dimensional space. Now all of them or each of them are converted into corresponding context vector. Now the context vector, each of them has a dimension of 2. This is what happens in the self-attention using trainable weights. So I hope from here on, whenever you look at this equation, softmax of Q dot key transpose divided by square root of D multiplied by V, I hope you will never be scared anymore. Instead, you will think about it from a intuition point of view. So why did we introduce query key and value? Because directly multiplying input embedding, directly taking the dot product between input embedding was not good, because it can result in, as you saw in the example of the dog, it should have paid more attention to ball than dog. But because you were taking direct dot product between vectors, your context vector was not very good, or attention scores were not very good. But so to improve your attention scores or improve the attention weights, you converted or you transformed the input embeddings or input vectors into another dimensional space, which is the query key value space. And then using that space, you construct the attention weights using Q and K. And then those attention weights are multiplied after scaling down with square root of D and after converting to softmax, that you multiply with value. So this is why it's called scaled dot product attention. So where is dot product coming? Dot product is coming in Q dot K transpose. Where is scaling coming? Scaling is coming in square root of D. And where is attention coming? Basically, these are the attention weights. And these attention weights are multiplied with value to get the context vectors. And finally, before we wrap up the lecture, why these names, query key and value? What are the origins? Query is like something you are looking for, meaning if your sentence is dream big and work for it, and if big is the query, you are looking for what should big do, right? So big is your query. Then key is all the inputs in your sequence. So basically, how much should this particular query pay attention to all the different items you have available in your data set. So you have all the input sequences in your data set, and key will help you identify which one should pay most attention to query. Should dream pay most attention to big? Should work pay more attention to big, etc.? And then value is the actual information itself, which you are trying to retrieve. What do we mean by that? The value matrix was the actual transform matrix of your input embedding, right? So you are trying to retrieve information from the value space, from the value matrix, such that you are taking a attention weighted sum of that. So value, so let's just go through this one. Query is the current token, current word or token that has a question about its context. So if my sentence is dream big and work for it, and if I'm trying to understand how much attention to big should big pay to each of the words in the sequence, I am having a question about the context of big, which means query is big. It is asking, what should I pay attention to? Should I pay attention to dream? Should I pay attention to work, etc.? Key is basically saying, I don't know finally what the context vector is, but I can tell you how much attention, or I can tell you I can tell you what the big is related to. So if key is dream, then I can say, and if the value between them is 0.2, then it's saying big should pay 20% attention to dream. If key is and if the number is 0.3, then it says big should pay 30% attention to and, etc. And then value is, here is the meaning of the content you will get if you attend to me. So basically value is is in a new transform space. So if you have 5, if here you have 1, 2, 3, 6 tokens in a 2-dimensional space. So you have now a value space in which each of the input embeddings are converted into this value space. So value space basically embeds the actual information that is there in your input sequence. And then that value space can be used to construct the final context vector. Now, so far, what we have discussed in this series is badano attention we have discussed, simplified self-attention using just basic dot product we have discussed, and in the current lecture, we also discuss the self-attention with trainable weights. But still we are having to go one more step to reach the attention mechanism used in GPT-2 or 3 or other models, which is masked self-attention or causal attention. So in the next lecture, we'll be discussing masked self-attention. But I hope you understand the intuition behind query, key, and value. And I would say you already have 90% of what is required to understand masked self-attention. So the next lecture you will find relatively simple if you have understood the current lecture. One thing I would like to say is there is a lot of technical things that we discussed in the current lecture, and this has been also quite a long lecture. So if you have reached till this point, you have had so much patience and you have had so much interest to understand this topic. So I recommend you go through this material again and again, as many times as needed. Take proper notes and try to implement the same in code. The code is not at all difficult. You might have seen it. It's very beginner level code, basically. We did not do any deep learning to implement it in deep learning. Although we said these are trainable weights, we actually did not train them. So the code was pretty simple. Concepts are actually fairly intuitive. It's just that you have to spend a little bit more time, right? So I highly recommend you pause wherever you wanted to pause and rewatch sections which requires clarity. But more importantly, try to zoom out sometimes and try to understand the big picture. We discussed about tokenization. We discussed about importance of how tokens should pay attention to each other. And then now we are understanding through today's self-attention that tokens cannot be directly used in the dot product. Tokens need to be transformed before we do anything with the dot product. But the idea of dot product still remains. Dot product is still a valid operation because it tells you how close to each other these vectors are, or semantically how close to each other the vectors are. So I hope you understand the intuition behind these things. Thank you so much for listening. I'll meet you again in the next lecture. Take care until then. Bye. Hi. Welcome back to a new lecture from Transformers for Vision series. Today we'll be discussing about multi-head attention. I will give you a brief recap of our journey so far at the beginning, and then we will see how much we know, and you will truly realize that multi-head attention is in fact very simple because we have already discussed causal attention in the last lecture. So there are two approaches for implementing multi-head attention that we are discussing in this series. In the current lecture, we'll be discussing the approach using concatenating the context vector matrices that we get out of each attention head. And then after that, in the next lecture, we can discuss a bit more unified approach, which is adopted by modern large language models. If you don't know what is attention, self-attention, causal attention, etc., I highly recommend you to watch the lectures that are immediately before this one, so that you will have better context. And especially if you have fairly good idea about the causal attention that we discussed in the last lecture, you will find today's lecture very easy. With that, let us get into the lecture. So first, let's have a brief recap of what all did we learn so far in this understanding of transformer architecture. We first looked at the transformer architecture itself as a whole. So here in the last part of this, I have a figure. So we looked at the transformer architecture as a whole, and then we discussed it in three parts: input, transformer, block, and output. But there we did not go into details of the multi-head attention. So we kept multi-head attention alone separate, but we looked at the rest of the architecture. And then we started to discuss about attention. So first we started with badano attention. In the context of neural machine translation. After this, we discussed about self-attention. And when we first implemented a simplified self-attention. So here we did not use any trainable weights. We simply said the attention score between two input embeddings or two vectors is simply the dot product between them. And once we have the attention scores corresponding to one query, we can normalize those attention scores to get attention weights. So this is what we did in simplified self-attention. But in the lecture following, we discussed self-attention with trainable weights. And here for the first time, we introduced the weight matrix for WQ for query, WK for key, and WV for value. And here we discussed that instead of directly taking the dot product between the two input embeddings, what we do is we transform those input embeddings into query key value spaces. Then we take the dot product of the transformed input embedding in query space and transformed input embedding in key space. So we got query.key transpose, q.k transpose. And then we said we will scale this by the square root of dimensionality of the key space, square root of dk. And then we said we will take softmax of this resulting attention weights. So what we get out of this is the attention weights. So we'll take softmax of this. And after taking softmax, actually before this, it will be attention scores, and softmax will give us attention weights. And once we have attention weights matrix, we can multiply it with the value matrix. So this is basically the input embeddings converted into value matrix. So this was the final context vector matrix that we can get out of the attention with trainable weights. So this was what we discussed 2 lectures ago. And then after that, we discussed causal self-attention or masked self-attention. So this is what we discussed in the lecture before. So in causal self-attention or causal attention, what we discussed were the following. First, we have input embedding. So here we have 1, 2, 3, 4, 5. We have 5 input vectors in 3 dimensions. So total, this matrix will be a 5 by 3 dimensional matrix. And then we want to transform each of these vectors into the query space, key space, and value space. So query space dimensionality is 2 according to our assumption. So we said we will use query key value spaces of dimensionality 2 instead of 3. So to convert 5 vectors each of dimensions 3 into 5 vectors each of dimension 2, we used a transformation matrix of dimension 3 by 2. So 5 by 3 multiplied by 3 by 2 will be a 5 by 2 matrix. So this transformation matrix was the query weight matrix, which is a trainable matrix. Like this, we'll have another trainable matrix to convert the same input embeddings into keys and same input embeddings into values. So these three are the trainable matrices which perform the transformation of input into query, key, and values. Now, once we have these three, first what we do is we calculate the attention weights. So first we try to get the attention scores. You take the dot product between query and key. So to get the dot product, you multiply Q with the transpose of key. So this is 5, 2 because you have 5 input embeddings, and in the query space, each of them is 2-dimensional. So it's 5, 2. The transpose of key is 2 by 5. And then the result of this matrix operation will be, matrix multiplication will be a 5 by 5 matrix. And this is the attention scores. And then we said to create masked attention, where we want to mask the future keys. Basically, query should not pay attention to keys that are supposed to come in the future. We want to mask the upper triangle. So all these values, we wanted to have it to be 0. For that, what should we do? We should have those numbers as negative infinity when we are applying softmax operation, because softmax operation is e raised to x divided by sigma e raised to x. So e raised to minus infinity is 0. So if we had minus infinity before we applied softmax, then those numbers will become 0 after application of softmax. So what we did was, the attention scores that we got, we converted the upper triangle into negative infinity numbers. Then we scaled the dot product. So this is the dot product, Q dot key transpose, Q dot or queries multiplied by key. And then we scale it. Basically, this scaling is done to reduce the variance or keep the variance of the resulting dot product numbers equal to 1. So we saw that the variance scales with square root of d. So if you divide by square root of d, where d is the dimensionality, in this case, the dimensionality is 2, the dimensionality of the query key value space. So since the variance of the resulting attention scores, which are these numbers inside this, is proportional to square root of d, if you divide the resulting matrix by square root of d, you can keep the variance close to 1. So this resulting thing is called scaled dot product, because we are scaling by 1 by square root of d. And the scaled dot product, we were normalizing using softmax. So softmax is applied row wise so that each row will sum up to 1. So this was the masked self-attention, because you are basically applying a mask. Negative infinity is the upper triangle. So this mask will produce a final output of zeros in the upper triangle. And then each of those rows should sum up to 1, because these are normalized attention weights. So the first item will simply be 1, because dream as a query has only one key to focus, which is dream itself. Dream cannot see big, because in this sentence, big comes after dream, and you are preventing the tokens or preventing queries from accessing the future keys. Big has access to only dream and big. So the sum of these two should be 1, sum of these 3 should be 1. So every row should sum up to 1. Then at the end of the last lecture, we discussed about a dropout mask, which drops out these attention weights randomly at a certain probability. So if the probability is such that if we are dropping out at 0.5, let's say half of these items are masked, then we said the remaining numbers in this will be scaled by a factor of 1 by 1 minus p. So p is 0.5. So in this case, 1 by 1 minus p will be 1 by 1 minus 0.5 is equal to 2. The reason why this scaling is done is because when you are dropping out half of your items to produce your final output, you only have half items available on an average. So if you want to produce output of similar magnitude with just half the available weights, you have to scale those weights by a factor of 2 because half items are missing. So you scale the remaining ones by 2. So because of that, in the final output, actually, this will be 2 instead of 1. This will be 2.0. This AND should be, so here the AND was the third item in the, or second item in AND was 0.2. So after application of mask, this 0.2 will become 0.4. Similarly, after application of mask, you have in the fourth row, second and fourth item gone, which means this and this is gone. So these two items will be scaled up by a factor of 2. Then here, second and fourth item is gone, which means this and this is gone. So remaining items are scaled up by 2. So this and this will be scaled up by 2. Then in the final row, this and this are gone according to the mask of the final row. So then remaining items will be scaled up by 2. So that is the final output that you get from a dropout mask. So this dropout mask was implemented to prevent overfitting. Now, in the result, we will not have these numbers. We will actually have numbers that are scaled up by 2. Okay. So now the goal of attention was the following, right? The reason why we introduced attention was because we wanted to have context vectors corresponding to every single input token. Because context vectors are much more information rich, input token just takes the semantic meaning. So if we have tokens for dog and cat, maybe they will point into a semantic space that correspond to animals. If we have apple and orange, those vectors will point to a semantic space corresponding to fruits. But if these words are already part of a sentence, then maybe the context in which these words are present are different. So maybe we should modify it a little bit to take care of the context. So this is why we were trying to create attention weights, so that using the attention weights, we can convert the input embeddings into context vectors. So we want one context vector per input token. Now with this much background information, let's see what is multi-head attention. So multi-head attention, as the name suggests, it has multiple attention heads that operate independently. So far in our discussion, we just had one query vector, one query matrix, trainable matrix WQ, one key matrix, and one value matrix. And these matrices were used to transform the input embeddings to query key and value. In multi-head attention, we will have separate WQ, WK, and WV corresponding to each attention head, and they will be stacked in parallel. So I have made a figure that explains the following. So I don't want you to focus on the right hand side yet. So I'm going to draw a rectangle so that this part is kind of masked. So just ignore this part. Just focus on the left hand side. You have your input embeddings. So this is one vector of 3 dimension. Like that, you will have, let's say, 6 vectors in the input. So those are 6 input tokens. Then instead of now having one query weight matrix, which creates one set of queries, here you have 2 query matrices. This is the first query matrix and this is the second query matrix, and these operate in parallel to produce 2 queries, 2 different sets of query matrices. Now, if I had 5 inputs, meaning I had 5 tokens and each with dimension 3, and if the dimensionality of my query key value space is 2, then this Q1 will be of dimension, what will it be? It should be 5 by 2. Q2 should also be 5 by 2 because each of them are processing the inputs separately. The dimensionality of the query space is 2, which means Q1 should have 5 input vectors converted into queries. Q2 should also have the same, and the dimensionality should be 2. So 5 by 2, 5 by 2. Same thing applies for keys. So there are two key matrices, which are learnable weights, which produces two keys, K1, K2. Similarly, there are two value matrices, weight matrices that are trainable, producing two value matrices as a result. So how is this Q1 produced? Q1 is simply X multiplied by WQ1. Q2 is simply X multiplied by WQ2. So basically input vector multiplied by the weight matrix. So weight matrix performs transformation of the input. Key is X multiplied by WK1. The second key is X multiplied by WK2, and similarly for value. So this part is simple. And now let's look at the right hand side part. So normally what would we do next? We would simply take the dot product between Q and K to produce attention scores. Then attention scores are scaled, then they are masked, and then they are normalized using Softmax to produce the attention weights. And then after that, we apply dropout, right? These are the steps with respect to what happens to Q and K. And then once we have the final causal attention with dropout, you can multiply the result with values to get the context vector. So here also, it's exactly the same. Now I'm going to remove this, this white rectangle. So now we will have two matrices with attention scores, one corresponding to this query matrix, another corresponding to this query matrix. So this is now Q1 multiplied by, Q1 taken dot product with K1. So Q1 dot K1 transpose. And this is Q2 dot K2 transpose. So we are taking again the dot product between query and key, but such that Q1 is taken the dot product with K1, Q2 with K2, and whatever is the result of this dot product, it will be a matrix of what dimension? 5 by 5. I have drawn here as 3 by 3 just to save some space. But if our query space is having 5 tokens converted into 2-dimensional vectors, key will also be 5 tokens converted to 2-dimensional vectors. Like that, you have K1 and K2. So Q1 multiplied by K1 transpose will be 5 by 2 multiplied by 2 by 5 transpose, or 5 by 2 multiplied by 2 by 5. That will be 5 by 5. So the first set of attention scores will be corresponding to this will be 5 by 5 dimensionality. The second set of attention scores will be corresponding to the second attention head, second layer in the attention head. Again, that will be 5 by 5. And then what we do is we mask the attention scores such that the upper rectangle are all negative infinity. We also scale down with 1 by square root of d, which is 1 by square root of 2 in this case, because dimensionality of the query key space is 2. Then once we have the attention weights after we take softmax, so softmax of the masked scale attention scores. After we have the attention weights, we perform dropout so that randomly some weights are dropped out. Then we have, this is the final attention after applying the mask and after applying dropout. And then this we have to multiply with value, right? So we multiply the first, this one with value 1, V1. Let me just draw it. This is multiplied with V1, and the one below, which is the second layer of the output, is multiplied with V2. Now V1 will be 5 by 2. V2 will be 5 by 2. This will be 5 by 5. And this will also be 5 by 5. So when we multiply 5 by 5 and 5 by 2, the resulting one would be 5 by 2. So we will have now two context vector matrices. It's not context vector. So if I write it as context vector, it is wrong, but these are context vectors. So this S is important. Why? Because if I had 5 inputs, like this, if I had 5 input vectors, right, then each context vector matrix will have 5 vectors like this. So 2-dimensional vectors, but there will be 5 of them. Like that, there will be 5 of them. And why is the dimensionality 2? Because we created this context vectors using query key and value whose dimensionality was 2. The input embedding dimensionality was 3, but the query key value space had a dimensionality of 2. And why do we have two context vector matrices? Because we had multi-head attention here with two attention heads. So one context vector matrix, the first one is created by the first attention head consisting of WK1 weight matrix, which produced K1 as the keys, WQ1 query matrix, which produced Q1 as queries, and similarly WV1 weight matrix producing V1 as values. Like that, you have two layers stacked parallelly, and these layers operate simultaneously but also separately. So you have two context vector matrices, and then what you do is you concatenate them to just produce one context vector matrix. So why do we call it as context vector matrix? Because you simply won't have just one vector like this, you will have 5 vectors. In our example, assuming we have 5 input tokens, we will have 5 context vectors. And what will be the final dimensionality of each of these context vectors? It will be 4, because you are concatenating two two-dimensional context vectors. Now let me draw this once to make everything clear. The dog, or something like this, let's say dream big and work for it. So how many tokens are there? There are total 6 tokens, and let's say each token is represented by a 3-dimensional vector. This will be a vector of dimension 6 by 3, a matrix of dimension 6 by 3. Then in multi-head attention, we have WQ1, WQ2, WK1, WK2, then WV1, WV2. Then this matrix passes through both of them to produce 2 queries, Q1 and Q2. The dimensionality of the query space is 2. So this will be 6 by 2. This will also be 6 by 2. If you want to produce 6 by 2 from 6 by 3, this should be 3 by 2. This should be 3 by 2. So this is WQ1. This is WQ2. This is Q1, Q2. Okay. Similarly, you will have keys and values. So there will be K1, K2 and K1, both of them will be 6 by 2, 6 by 2. Then you will have V1 or V2 and V1, which will be again 6 by 2, 6 by 2. Now, query and key, we take the dot product. And after we take the dot product, we will have two 6 by 6 matrices. So this will be 6 by 6. This will be 6 by 6. Why do we have 2 layers? Because here we are saying we have 2 attention heads in the multi-head attention. Remember, in GPT-2, they had 12 attention heads. In GPT-2 small, in GPT-3, they had 96 attention heads. Okay. And then we perform scaling, softmax, masking, and finally dropout to get the final attention weights. And again, the dimensionality will be 6 by 6 and 6 by 6. Now we have to multiply this with the value matrix. So value matrix is 6 by 2. This is 6 by 6. So when you multiply 6 by 6 with 6 by 2, resultant will be 6 by 2. So we'll have 2 of them. 6 by 2 and 6 by 2. What is this? These are context vector matrices before we do the concatenation. And then we concatenate it. So here, each of them will be of 2 dimension, but like that, there will be 6 vectors, 3, 4, 5, 6, like that. Okay. And then we concatenate it in such a way that, so this part alone, maybe I can draw slightly better. That way I can show you the concatenation operation. So all right, so this is the first context vector matrix of dimension 6 by 2. I will give it a different color. And now this is the second one. This one can have another color. So you have two 6x2 matrices that are context vector matrices, correct? And then you concatenate them such that you are doing it row wise. So how does that look like? That will look like this. It will look like this. So first matrix should come first. So here I should probably bring this to the back layer to not confuse you. Yeah. So now if you concatenate, it will look like just one matrix of dimensionality, what? 6x4. So what happened is we had 6 input vectors of each 3 dimensions, and it got converted into 6 context vectors. So these are now context vectors of dimension 4, because each vector is now represented by 4 dimensions. So this is what happens in multi-head attention. So that is why, and where is the concatenation operation coming here? Here, the outputs you get from each heads of the multiple heads in the multi-head attention, you concatenate it. So now you can think of it like this. You can qualitatively say that each attention head is taking care of half of the dimensionality of final context vector. So final context vector has dimensionality 4. The first multi-head attention took care of the first 2 dimensions. Second head in the multi-head attention took care of the third and fourth dimension, the green ones. So you can think of it like that. But the actual reason why we have multiple attention heads is so that each attention head, because they have trainable parameters, it can train itself to learn different types of features in the input, so that the final context vector that comes out of this concatenation operation will be much more richer than if you had just one attention head with just 3 trainable weights like WQ, WK, and WV. So that is what is happening. So here, this one again shows the dimensionality. So if dream big and work for it is your input of 6x3, let's say you have multi-head attention of 2 heads. The first one will produce, the first output will be 2 context vector matrices, the each of dimension 6x2. Then they will be concatenated to produce 1 context vector matrix of dimension 6x4. Now, what if we had, instead of 2 heads, what if we had, let's say, 3 heads? And let's say the dimensionality of each of the query key value space was 2. Then this output will be 6x2 only. This is not going to change. But instead of 2 context vector matrices, we'll have 3 context vector matrices. And each of them will be concatenated. So 6x2 will become what? Will it become 6x4? No, it will become 6x6. Because now you have 3 things to concatenate. And what about if my dimensionality of the query key value space was 3? So let's say Q, K, V dimensionality was 3. Number of attention heads equal to 4. And input dimensionality equal to, let's say, 4. And number of tokens equal to 6. What will be the final context matrix looking like, context vector matrix looking like, the final one after concatenation? So tokens, you have 6 tokens, input dimensionality is 4. So you have a 6x4 matrix. Now the query key value space individually, they have 3 dimensions. So this 6x4 will be converted to 6x3 for query, 6x3 for key, 6x3 for value. Now these are 6 tokens in 3-dimensional space. Using this, the attention weights that will be produced will be 6x6. And then this attention weights, after applying the mask and after applying dropout, will be multiplied with the value matrix. So 6x3 and 6x6 will be multiplied such that the resulting dimensionality will be 6x3. Now, this is the resulting dimensionality of the context vector matrix from 1 attention head. Like that, how many attention heads do you have? You have 4 attention heads. which means when you concatenate, your final dimensionality will be here. In each attention head, the dimensionality of each vector is 3. You have 6 vectors, each vector has a dimensionality of 3. But like that, you have 4 attention heads. So if you concatenate, finally, you are concatenating along the row. This will become 6 by 12. So this is how it works. So these were random numbers I just picked. This is not how actual GPT numbers look like, but just to show you how to calculate, right? So this is what we finally have. Okay, so now in GPT-2, we had 12 transformer blocks in series. So this is the transformer block diagram, and this diagram we had looked at in the lecture where we tracked the journey of a token. So this transformer block is just one picture, but like this, there were 12 of them in series. And within each transformer block, GPT-2 had 12 attention heads in parallel. So the multi-head attention had 12 heads. But that is within one transformer block. Like that, there are 12 transformer blocks in series. And in GPT-3, they had 96 transformer blocks in series. And inside each transformer block, they had 96 attention heads in parallel. But that's within one transformer block. Like that, there are 96 transformer blocks themselves. So this is how the multi-head attention works. Now what we can do is we can try to implement this in Python code in the simplified fashion. And in the next lecture, we will see how do we apply the multi-head attention in a much more matrix multiplication friendly way. So these are the vectors that we are considering at the input. Dream big and work for it in 3 dimensions. Each of the row will be one vector. So you have 3 columns because you have. And this nn.linear basically defines the matrix multiplication using which we transform our input. It also allows us to add the bias if we need. So we thus define W query, key, and value. Then we have dropout. So nn.dropout function helps us easily define the dropout mask. And this tri-U is the upper triangular matrix, which makes sure that we are applying the mask such that upper triangle items are initially negative infinity, and then we apply softmax. Then in one forward pass, what we are doing is we are calculating key. Key is W key of X. So what here is happening is into this nn.linear function, we are passing X is the input. And that inputs get transformed using a matrix whose dimensionality will be dn multiplied by dout. So dn will be 3, dout will be 2. So 3 by 2, as we saw earlier. Same thing happens to produce queries and to produce values. Now here, B is a new dimension that we are introducing, which is batch size. Usually we will have batch as a parameter, but other than that, number of tokens is 6. Here batch dimension is 1, batch size is 1. Number of tokens is 6 because we have 6 words. din is 3. Then attention score is nothing but the dot product between queries and keys. So queries multiplied by transpose of keys. So can you guess why we do transpose of 1, 2? The reason is we are the first dimension or 0th index dimension is the batch. So the dimensions that we want to exchange is the dimension where number of tokens and the input dimensions are coming, which is the first and second dimension. 0th dimension is the batch. So since 0th dimension is the batch, that we don't involve in transpose. We transpose this dimension and this dimension, which is dimension number 1 and dimension number 2. So queries multiplied by the transpose of keys. So this at is the Python symbol for matrix multiplication. Then attention scores, we convert to attention weights. So first we have mask. In that mask, we are defining minus of torch dot infinity, which are minus infinity values. And these minus infinity will be there introduced in places where we have upper triangle. Then attention weight is nothing but softmax of the scaled masked attention scores. So this is now the masked attention score. Upper triangle will be negative infinity divided by keys dot shape of -1 raised to 0.5. So keys dot shape of -1 is the last dimension of the keys matrix. So keys matrix dimension was 3 by 2. The last dimension is the number of columns, which is 2. So -1 means we will pick the shape of the last dimension. So keys dot shape of -1 will basically be equal to 2. And 2 raised to 0.5, which is square root of 2. So we are taking square root of 2. And then softmax is applied along dimension equal to -1, which is softmax is applied such that the columns will be preserved along the rows the softmax will be applied. Then attention weights, final attention weights will be these attention weights plus dropout applied on top of it. So after dropout is applied at a certain probability, you will have masked certain weights being masked, and remaining weights will be scaled up by a factor of 1 by 1 minus p, where p is the probability with which you are masking. And then final context vector is nothing but your attention weights multiplied by values matrix. So attention weights in this case will be, you have how many tokens? 6 tokens. So attention weight should be 6 by 6. Values will be 6 by 2 because you have 6 tokens and 2 as the dimensionality. And then you will have the final context vector. So this is how we perform the calculation. Now let's run this just to make sure that we have all the class defined. And then dimension at the input is inputs dot shape of -1. Again, this will pick the number of columns in the input. Number of columns in the inputs is 3. Number of rows is 6 because we have 6 tokens, each tokens of 3 dimension. So din will turn out to be 3. We can just print din. So din should be 3 and dout is 2. So that's what we are printing. And then we define batch. So batch is such that torch.stack of inputs comma inputs dimensionality equal to 0. So here you can see that you have inputs stacked 2 times to produce a batch size of 2, but they are the same inputs. Ideally, we will have different inputs, but here we have stacked the inputs 2 times to produce a batch whose size is 2. If we had this repeating 3 times, we will have a batch size of 3. See, first dimension is batch, second dimension is number of tokens in each batch, third dimension is the dimensionality of the each token. Okay. So here we can actually go with one batch also, no problem. So if we just have inputs comma, then it's just one batch. So one batch, 6 tokens, 3 as the dimensionality. Now what we do is we define this class. This is the new class that we are defining called multi-head attention wrapper. Basically, this is a wrapper which is around the previous causal attention class that we have defined. So into the causal attention, we are passing input dimension, output dimension, context length. Context length is what? 6. Dropout, we will say false. So I will show you where this is being passed. So first we say MHA, multi-head attention, equal to, it's an object, which is an instance of this multi-head attention wrapper class, into which we are passing D in, D out, context length, 0 for dropout. So nothing is being dropped out. Number of attention heads equal to 6. Okay. And then that is being passed in over here. Query key value bias is false. And then these passed values are also passed into the causal attention class. And one thing you might notice here is this for loop is because we are processing these attention heads. Although in reality it happens in parallel, we are defining a for loop so that attention head number 1 processes its input first. Attention head number 2 processes its inputs next. And then those outputs you get from attention head number 1 and number 2, you finally concatenate. So here we are doing it in series, but this is not a very efficient way to do it. You will see that in the next lecture. But you can concatenate the outputs that you get from both of these attention heads. So here you say this is the concatenation operation. So final thing that you get as a return is for each attention head, the output you will be concatenating. So you are calling head of X, and the output is whatever is returned is this guy, context vector. So like that, you will be 2 context vector matrices because you have 2 attention heads. So let's just run this and run this. So here we just want to print the final context vector. So final context vector is this 6 by 4 because you have concatenated the context vectors from both attention heads. So this is now the final context vector. And I also want to show you what if my batch size was 2. If my batch size was 2, so now it's batch size 2. Same inputs we are repeating. Ideally, it will be different. And you will have 2 such context vectors corresponding to each batch. The numbers are the same, but you see, this is the first set of context vectors. Okay, let's look at the dimensionality. First of all, batch size is 2. So this is the first batch. And this is the second batch. Second batch of what? Second batch of context vectors. How many context vectors in each batch? 6 context vectors in each batch. What is the dimensionality of each context vector? 4 is the dimensionality of each context vector. What was the dimensionality of the input vector? 2 was the dimensionality of input vector. How many input vectors were there in each batch? There were 6 input vectors in each batch. So input dimensionality counting batch size was 2, 6, 2 over here. 2, 6, 3. Yeah, input dimensionality was 3. And then, so that was 2, 6, 3. And here context vector dimensionality is 4. Why is it 4? Because you have 2 heads in the multi-head attention. What if we had, let's say 4 heads? What would have been my final output? If we had 4 heads, each head is outputting a dimension of 2. Like that, you have 4 heads. So your final dimensionality for each context vector would have been 8. So let's try that. So number of heads equal to 4. Then you see 8. Why? 1, 2, 3, 4, 5, 6, 7, 8. So each context vector is of dimensionality 8. So this is the first batch. This is the second batch. You have 6 vectors in each batch. Each row of this one batch is one vector. So this is one vector. This is second vector, third context vector, like that. And each context vector has a dimensionality of 8 because you have 4 attention heads. Each attention head is producing a context vector of dimension 2. Then when you concatenate them, you get a dimensionality of 8. So this is how multi-head attention works. In the next lecture, we will see in detail how multi-head attention is actually implemented in practice, because this for loop is not good because now you are implementing each attention head in series, while in reality it has to happen in parallel. Only then LLMs can utilize GPU processing to improve the speed of training. Right here, what if we had 40 attention heads? The code will significantly slow down for sure because of the for loop. I mean, this is still fine, but if I had, let's say, 400 attention heads, I don't want to print the context vector. I just want to print the shape. So now it's taking a little bit. It took a few more seconds. If this was 4,000, it will take more time. See, it's taking few more seconds. And as this dimensionality increases, I mean, number of heads is anyway not 4,000 in any model. It's only 96, but then you have many of them to process in series. But in general, you will notice the effect of things slowing down because you are running a for loop. The best way to know the track this is you simply keep a timer before and after execution, and this timer will tell you how much time it took for you to run. In the next lecture, we will see how can we do this without using this for loop, just by using simple matrix multiplication. So I hope you understand the idea of multi-head attention. In multi-head attention, you have multiple attention heads happening, processing the input independently. Then finally, you have outputs, which are multiple context vector matrices. Then those matrices concatenate along the row to produce context vectors of that concatenated dimension. So if you had 2 attention heads, and if each attention head is producing context vector of dimension 2, your final dimension of each context vector will be 4. So, and why do we have multiple attention heads? Why not one attention head? Because if we have multiple attention heads, each attention head is now having 3 trainable weights. And these trainable weights are so valuable because it can learn patterns in the data, and each attention head will take care of different aspects of the relationships between the tokens in the data. It's very hard to exactly say what is the role of each attention head, but the fact that you have different attention heads trying to learn patterns from your data, it makes the learning process much more efficient and the final context vector after combination much more richer. So I hope this you enjoyed this lecture. Please try implementing this yourself. It's very easy to implement. If at any point you have any doubts or confusion, pause the lecture, watch the video again, and do take very good notes. Also code along with this, or after you finish the lecture, at least you try to define the code and write this yourself. The detailed mathematical implementation and code implementation of multi-head attention we will see in the next lecture. So take care. See you soon. Bye. Hi, welcome back to a new lecture from Transformers for Vision series. In today's lecture, we'll try to understand causal attention mechanism, which is the actual attention mechanism implemented in models like GPT. We will not be implementing multi-head attention yet, which we are reserving for the next lecture, but today we will see how the masked self-attention, also known as causal attention, works. So with that, let's get into the lecture. In fact, today's lecture you will find much easier compared to the previous lecture because the concept is pretty simple. However, if you don't remember how the self-attention itself works, I will give you a brief recap in the beginning. So before we go into the nuts and bolts of causal attention mechanism itself, let's try to have a quick recap over what the idea of attention mechanism itself was. So the idea was we wanted to produce a context vector corresponding to every single input embedding. So input embedding is a vector which corresponds to every token, and corresponding to every single input embedding, we want to produce a context vector. And why is context vector so important? Because it is much more richer in information. So input embedding is just the direct conversion of a token into a vector, whereas context vector also has the information about the tokens next to the token which you are looking at. So if you are considering the sentence, the cat sat on the mat, if you simply convert the token cat into an input embedding, it may look like this, but the cat is not a token that is standing there alone, right? Because there are other tokens next to cat, the, sat, on, the, mat, all of them are next to the cat. So how do we embed this context into the cat's input embedding vector? That is by converting it into a context vector. So this context vector production corresponding to every single token. So the should be converted to one context vector, cat should be converted to one context vector, sat another one, on another, the and mat. So if there are totally 1, 2, 3, 4, 5, 6 tokens, in our output, we need 6 context vectors. Now, just to recap, the words are not equal to tokens. It's an oversimplification that I'm taking here for the convenience of conveying the idea. The actual tokens in GPT can be words, subwords, characters, etc. So we discussed the byte pair encoding in one of the previous lectures. But for simplicity, we will assume one token is equal to one word. Now these 6 context vectors are much better or much richer in information compared to the 6 input embeddings, right? So this was the idea behind attention mechanism. How can we create context vector using attention mechanism? So 2 lectures before, we had implemented a simplified version of self-attention in which we said we will just take the dot product between 2 vectors. So if I have a vector like this for cat, and if I have a vector like this for the, so let's say this is corresponding to cat and this is corresponding to the, if I take dot product between them, it's 90 degrees. So the dot product between 2 orthogonal vectors is 0, which means cat need not pay too much attention to the, but here cat should pay a lot of attention probably to sat and also to mat because cat is sitting on the mat. So maybe the vectors corresponding to cat and mat might look like this. So mat might be something that looks like this. So we said, since these input embeddings are vectors pointing into semantic areas of multi-dimensional space, if you simply take the dot product between those vectors, the vectors that are pointing generally in the same direction will have a bigger dot product. Vectors that are orthogonally pointing to completely different directions in the semantic space will have a very small dot product. And we took this dot product as a proxy for attention score. And then we said, okay, attention score need to be normalized to get attention weights. So that is what we did in the simplified self-attention lecture. But then we discussed this has a problem. The problem is, consider this sentence. The dog chased the ball, but it could not catch it. If you consider the last word it, what does this it mean? This it refers to ball or dog. Here it simply means ball. So the token it should pay more attention to ball than it should pay to dog. Now let's say the token embeddings in 3 dimensions. So we are simplifying it again. We are considering the token embedding space to be 3-dimensional space. In that space, let's say dog is this vector 0.9, 0.1, 0.1, and this is ball, and this is it. And clearly they are pointing in different directions. But now if you take the dot product between it and ball, you get a dot product like 0.1, 0.51. If you take a dot product between it and dog, again you get 0.51. So simply taking a dot product is sometimes not enough to capture the attention. Why? Because here the attention scores are exactly the same between it and ball and it and dog. Ideally, what I wanted was attention score between it and ball should have been bigger, higher than it and dog, right? But that's not the case here. That's because we are directly using the input embeddings in the dot product. So this brought us to our idea, which we discussed in the last lecture, that instead of using the embeddings directly, we still need to use dot product, because the core idea of dot product is still valid. Because if you take dot products between 2 vectors, and if those vectors are pointing in similar direction of the semantic space, then it's a valid idea, because if the dot product is big, that means those vectors are pointing in the same direction, which means they should probably pay more attention to each other. So that idea is valid, but the problem here is we are directly taking the dot product of the input embedding. So what we discussed in the last lecture was, instead of using the input embedding directly, use transformed input embedding and use some matrices to perform this transformation. So these matrices had some names. So we introduced 3 matrices: query matrix WQ, key matrix WK, and value matrix WV. Now in this example, what we are showing is the query currently is it, because we are looking at how much attention should it pay to dog and ball. So it being a query, it is transformed using the query matrix. And this is a weight matrix. It's a trainable matrix. So in the last lecture, we implemented self-attention using trainable weights. But before that, we had implemented self-attention in a simplified manner without trainable weights. And now if you convert it into a transformed query space using the WQ matrix, you get this vector 0.5, 0.5, 0.1. It's the same as the previous it vector, because in this simple example, I have used an identity matrix as the WQ matrix. Now this WK matrix is used to transform my tokens into the key space. And key space is also 3-dimensional here in this example. And I transform dog by multiplying it with WK. I transform ball by multiplying it with WK as well. And now these are the transformed vectors of dog and ball in the key space. Now I can calculate attention score between transformed it, which is this vector, and transformed dog, which is this vector, resulting in 0.56 as the attention score. I can also calculate attention score between transformed it and transform ball by taking the dot product between this vector and this vector, resulting in 0.96. So you see, conceptually, I hope you understand now how a transformation can actually make your attention score much more meaningful or much more useful, because here now it is paying more attention to ball than to dog, because attention score is clearly showing that. So this is the reason why we introduced the concept of transformations. So embeddings are transformed into query key value space. Now to generalize this idea, we took an example. So let's say the sentence is the dog chased the ball. And let's say we are representing each vector in the input embedding in a three-dimensional space. So this three-dimensional vector corresponds to to dog chased the ball. So this is a 5x3 matrix because you have 5 tokens and each token is 3 dimensions. Then we transform this 5x3 matrix, or we transform these 3-dimensional vectors into 2-dimensional vectors. So in the example that we took in the last lecture, we said that the query key value space will be 2-dimensional, although in reality it will be different. In GPT, by the end of the multi-head attentions, the dimensionality does not change, but here we assume it to be changing just for giving a better example. So here the 3-dimensional vector, which is the corresponding to that particular token, got transformed to a 2-dimensional vector in the query space. It also got transformed into a 2-dimensional vector in key space and in the value space. So what performed this transformation? This weight matrix. This is a transformation matrix with trainable weights. So we discussed, since the input is 5x3, the weight matrix is 3x2. So final transformation will be 5x2 because you have 5 tokens. Each token is now converted into 2-dimensional vectors. Like that, every token is transformed into the query space, key space, and value space. Now what do? We look at query and key. We take a dot product between query and key like this. So query is now a 5x2 matrix, 5 tokens, each of 2 dimensions. And we take the dot product with the transpose of the key. And this is how the dot product works. So when we take the query matrix and multiply it with the transpose of key, we get a 5x5 matrix because query is 5x2, key is 5x2, key transpose is 2x5, and resultant matrix is 5x5. And this was the attention scores matrix. These attention scores were, so it was like this: the dog chased the ball. So now this, if the is the query, this is the, whatever number is here in this cell of the matrix is the attention score between the and the. This is between the and dog. Third one is between the and chased, the and ball. Similarly, this is dog and the, dog and dog, dog and chased, dog and the, dog and ball. Like that, we have attention scores. But an important point which we iterated multiple times earlier was attention scores are not the same as attention weights. Attention weights are different. Now, one thing is, if I just wanted the attention score corresponding to one token, like what is the attention score just corresponding to ball? All I need to take is this particular row, the last row of this attention score matrix, right? So these are the attention scores corresponding to ball. How can I get this? This is now, this one row is 1x5. How do I get 1x5? I just take the query corresponding to ball, which is 1x2, multiply it with the transpose of key, which is 2x5. So if I multiply a 1x2 vector with a 2x5 matrix, I get 1x5 vector back. And I mean 1x5 vector back meaning I get 1x5 vector as an output. And that is the attention scores corresponding to the query ball. But this attention score has to be now converted into attention weights because attention scores are not normalized. If you look at the attention scores, here I am not displaying it. If you sum up the attention scores along the row, it will not sum up to 1. But we have to make it sum up to 1 so that we can make meaningful statements like ball should pay 20% attention to dog. It should pay 30% attention to, let's say, chased, something like that. So what we did was we first scaled the attention scores by using this 1 by square root of d, where d is the dimensionality of the key space. And we also discussed why exactly are we doing this. This is done so that the variance of the dot product between query and key, so q dot key transpose, will have some variance in the attention scores. That variance can be brought to 1 because that variance itself scales with square root of d, which we saw with an example in the previous lecture. So if you divide these attention scores by square root of d, we can bring the variance back to roughly 1. So we will have very good normalized set of numbers, which will stabilize our large language model training. And then, so this is now scaled dot product. Why do we call it scale dot product? Because we take the dot product of between query and key transpose, and whatever we get, which are called as attention scores, are now scaled by multiplying with 1 by square root of d. And then we take softmax along every single row. And when we take softmax along every single row, that row will sum up to 1, and individual items in that row will be basically like a probability distribution. There will be numbers between 0 and 1. Now these are now called the attention weights. So now if we consider one particular row, let's say the last row corresponding to ball, the numbers here may look something like this. So let's say 0.2, 0.4, 0.6, and then something like this. So this will add up to 1. And every number will be positive. It will be between 0 and 1, as if it's a probability distribution. So this is now called as attention weights. And then we said, okay, now we have the attention weights, but what's our final goal? Our final goal is to convert input embeddings into context vectors. So to convert attention weights into context vectors, or to use attention weights to create context vectors, what we did was we took the attention weights. So this is now the attention weights. This is not the input embedding. It's 5 by 5. This is attention weights. We multiply it with the value matrix. Value matrix was also the conversion of input embeddings in 3 dimensions into 2 dimensions using the value matrix. So here there will be, of course, 5 tokens, but each token will be of 2 dimensions. And therefore the matrix dimension will be 5 by 2. Attention weights are now 5 by 5 because you have 5 queries and 5 keys. So if you multiply 5 by 5 matrix with a 5 by 2 matrix, you get a 5 by 2 matrix. And now these are the context vectors. So this is the context vector corresponding to the dog chased the ball. And here the context vector is 2-dimensional because your key query value space was 2-dimensional. If it was 3-dimensional, context vector also would have been 3-dimensional. So this is in a nutshell what we discussed in the previous lecture, right? And we implemented this mathematically. So what we did earlier was we had this particular sentence, dream big and work for it. So it was totally 6 tokens, and each of those tokens were 3-dimensional. And then we implemented a Python class for performing this self-attention using trainable weights. So we have now 6 tokens, each in 3 dimensions. We want to get 6 context vectors out of this, right? So we define this self-attention class. So in the class, we initialized 3 matrices, which are random numbers initially. So weight matrix for query, weight matrix for key, weight matrix for value. And then we said the keys are equal to w underscore key of x. What does this mean? It means this input x, which is the input embedding, will be multiplied with the corresponding w key matrix. Here you will be multiplying with the corresponding w query matrix. So here we used nn.linear to kind of denote the matrix multiplication as a neural network forward pass. Same for values. So now keys, queries, and values are the transformed input embeddings in the key query value space. Then we said the attention score is the dot product between query and key. So queries multiplied by, so this is the symbol for matrix multiplication in Python. Queries multiplied by key transpose. Keys.t is key transpose. That is the attention score. Now to convert the attention scores to attention weights, we first normalize by square root of d. So square root of d is basically square root of dimensionality of the key space. So keys dot shape of -1 is basically the dimensionality of the keys matrix, and shape of -1 means you are looking at the number of columns, right? -1 is the last dimension of the matrix. So first dimension is row, second dimension or last dimension is column. So dimensionality of the column of the keys matrix is nothing but the dimensionality of the key space. So now this will be 2 in our example. and then multiplied 2 times means it's taking raised to, so this raised to 0.5, right? So you are taking dimensionality of the key space raised to 1 by 5, 1 by 2. So this will be square root of d, which is square root of 2, because we are passing the output dimensionality to be 2. We can pass 3 or whatever, but here we are using 2. And thus we get attention weights. And we do softmax before that. And softmax is done through each row. So that is why we mention here dimension equal to -1, such that every row is converted, every row is normalized. So if you sum up along one row, you will get sum equal to 1. So this is what we were doing, okay? And then finally, the context vector was nothing but attention weights multiplied by values matrix. So this is again matrix multiplication, same thing which we discussed. And then we said the input dimensionality is nothing but number of columns in my input vector, input matrix. So input matrix is this inputs, number of columns is 3. So inputs dot shape of 1, or I can also say inputs dot shape of -1. -1 is the last dimension. Both are fine. D out equal to 2 because the dimensionality of my key query value space is 2. I'm seeding a random number into my PyTorch. So if I run with this and then I instantiate my class. So my class name is self-attention v2. I instantiate the class. So this is now the object corresponding to class self-attention underscore v2. I instantiate the class by passing input dimension and output dimension. So this is the dimension of the input embedding. This will be the final dimension of my context vector. So I'm passing those two as the parameters. And then the SA underscore v2 of inputs will be my whatever I get as return out of my class. So the return is context vector. So now if I print this, if I run this, whatever is printed is whatever is being returned from the class or whatever is returned in the object, which is the context vector. So now I have 6 context vectors, each with 2 dimensions. So there are 6 rows and 2 columns, right? So now these are the 6 context vectors corresponding to my 6 inputs. This much is clear, right? So let's just print the final attention weights that we had. The final attention weights are stored here, attention underscore weights, which we can access by saying SA. So first, attention weights are what? Attention weights are normalized attention scores, and attention score is what? It is a product of matrix multiplication between query and key transpose. And query we can access from the object, key we can access from the object. So query is SA underscore v2, which is the object corresponding to my self-attention class, dot w underscore query. So w underscore query will be this, and we are passing x, which is the input matrix, into it. So x is this inputs. So inputs we are passing, and then we will get the query. Similarly, we will get the key. Query multiplied by transpose of key is the attention score. Then attention scores normalized by square root of d and taken softmax is the attention weights. And then we can print the attention weight here. So this is printing the attention weights, and these are the attention weights that resulted in the final context vector, because we use this attention weight to multiply with the value matrix to get the context vector. So this much is clear. But this was the basic self-attention with trainable weights, right? We did not have any causal attention or mass self-attention here. Now we come to our main thing, which is causal attention or mass attention. What exactly is this, and what are we going to do here? So the basic idea here is that think about how ChatGPT or large language model works. It predicts the next token, and then that next token is appended to the input. Then you have a context window with that new token also added to it. And then you try to predict the next token, and this is how it goes. Which means if you have, let's say, if you are trying to predict the context vector corresponding to a particular token. So let's say you are trying to predict the context vector corresponding to the token big. Big is the second token in this sequence, which means big ideally should not have access to and, work, for, and it, because they are future tokens in the sequence. In the sequence, big should have only access to itself, and it should have access to dream. Similarly, dream should have only access to itself. It should not have access to any of the future tokens, because that's the way in which we want the ChatGPT or we want large language model to work, right? future tokens should not influence the context vector. Only the current token and the past tokens should have some influence on the context vector, because by the time you reach big in your context, you have only dream. Similarly, by the time when you reach work, you have work and big and dream. So what you have to do is, for every query, it should have access to only certain keys that are at its own token level, or the ones in the past, not the ones in the future, which means dream should not have access to big and work for and it, right? So somehow this we have to mask, this we have to mask, dream, this should not be there, this should not be there, this should not be there. Dream should only attend to dream. So there should be an attention score between dream and dream, but the rest of the score should be nothing, 0. Similarly, big should have attention score with dream and big, but it should not have attention scores over here, right? And then and will have attention scores between and dream, and big, and. So these will be 0. So by the end, what we want is something like this, and this is called as masked attention, where I want everything above this diagonal to be masked. And you might know the concept of upper triangular matrix and lower triangular matrix. And if you look at this, this is like a lower triangular matrix, because only this lower triangle is now available in the matrix. Rest of the values should be 0. So basically what we are trying to do is, for every query, so here and is a query, future keys are marked. So for and as the query, key corresponding to work, key corresponding to for, and key corresponding to it are all future, in the future, because it's a sequence of words. It's a sentence. So dream, big, and work for it means and should not have access to work for and it, which means and should not attend to work for and it. The attention should be fully paid between dream, big, and. So this is called as masked self-attention. So we mask the attention weights above the diagonal, and then whatever is remaining. So once we mask this in each row, now look at in the first row what is remaining. You have this one remaining. Second row, you have this remaining, and you normalize the remaining item. So this alpha 1, 1, which is the attention weight between dream and dream, it should become 1, because sum total after normalization should become 1, correct? Then big has 2 attention weights between big and dream, between big and big. So alpha 2, 1, alpha 2, 2. So sum total of these two should be 1. So how can we do that? What we can do that is, whatever is the remaining numbers. So if there are 4 numbers remaining in the row after masking, take the sum of those 4 numbers and then divide every single one of the number by that sum. That way, the sum total of those numbers will be equal to 1, right? So what we do is, in causal attention, we normalize the non-masked attention weights. We normalize such that each row sum up to 1. And why is this called causal attention? It's because the output at any given point of time. So a series of data you can think of also like something that progresses with time. So output at any given point of time depends only on, right? It depends only on everything that happened in the past. So the past causes the future to happen. Future is the effect. So future tokens or future keys are not accessible to the current queries. That is basically what causal attention is. And this is also called as masked self-attention. Where we are masking the future keys. Now, how do we, if we were to apply this, what do we do? So first we get the attention weights. So here we had a 6 by 6 matrix with attention weights. All numbers were there. Then zero out all the elements above the diagonal. So everything in the above this diagonal, the upper triangle will be basically zeros. And then whatever is resulting, normalize it row wise, right? So this is what we are going to do. So let's see how to implement this in code. So firstly, we already saw the production of attention weights using our self-attention Python class. So these are the attention weights that we have now. And if you look at each row, they will sum up to 1. 15.82 plus 17.29 plus 14 point plus 17 point. So if you sum up these 6 numbers, they will sum up to 100% or 1. Now what we want is, we want to construct something like a lower triangular matrix where all the elements above that diagonal are zeros, right? So in PyTorch, actually we can construct triangular. So torch.tri L is the lower triangular matrix where the size of this whole matrix is basically 6, 6. So context length is 6. And how do I get the context length? Context length is nothing but how many tokens do I have right now in my, here we are considering that context window is equal to 6. So context length that I have right now is 6 because I have 6 words, dream big and work for it. So dream big and work for it. And context size is what? Will it be the row size or column size? It will be the number of rows because the number of columns here is the dimensionality of the input embedding. So dimensionality of the input embedding is not what we want. We want the number of tokens here. So the number of tokens is basically number of rows. So number of rows will be equal to, where is our, number of rows equal to the shape of 0, attention scores dot shape of 0, or it can be inputs dot shape of 0 also. Both are fine. Inputs dot shape of 0 is 6, or attention scores dot shape of 0 or attention scores dot shape of 1, both are 6. Then we say the simple mask that we are going to use to produce the masked self-attention is a matrix that looks like bunch of ones. And then we apply this mask onto our attention scores. So these are our attention scores. So now if you multiply element wise, so here we are doing a simple multiplication between or element wise multiplication between this matrix, this mask simple matrix, and the attention weights matrix. And then we will have all the elements where it is getting multiplied by 0 to become 0. So all these upper triangular ones are now 0. All these lower triangular ones are retained as such, right? So now we have the attention weights after applying the mask. But is this enough? This is not enough because now we have to normalize this row wise. So how do we do that? We first calculate the sum. So row sum equal to mask simple is this matrix name. So mask simple dot sum of dimension equal to 1. So dimension equal to 1 means you will be taking the sum along the rows. So you are finding the row sum, whereas if we put dimension equal to 0, you will find column sum here. And then we say we divide this guy, this whole matrix called mask simple, simply by the sum of each row. So each row here is divided by the sum of that row. So that is what is done here. So mask simple has 6 rows and 6 columns. Row sums have 6 rows and 1 column. If you add this code print rows.sum of shape, row sums.shape, you will see 6 rows and 1 column. And then here we are basically dividing every row by its corresponding sum. And then finally we have now the normalized masked self-attention. So after normalization, this 0.152 will get divided by 0.152 because in this row, rest of the elements are 0. This 0.1590 will get divided by 0.1590 plus 0.1739 because in this row there are only 2 elements, 0.1590 and 0.1739. You sum that up and that sum, whatever it is, is dividing the 0.1590 and 0.1739 such that sum total of those two will be 1. So here the sum total of this row is 1. Here the sum total of this row is 1. But there are only these 2 elements. So 0.47 and 0.53 like that. Okay. The last row will be unaffected. Why? Because in the last row, the sum of this is already 1. So you have these many elements. And if you add up this, it's 1. Because after masking, nothing has been dropped out. After masking, all the 6 elements are still there. So this was anyway attention weights, which were summing up to 1. So if you now divide each of these numbers by 1, you will have that same number back. So last row is unaffected. Okay. So now this is the attention weights that you have after normalization. So far so good, right? So you now think you have understood causal or masked self-attention, but there is actually a problem. Why did we introduce masked self-attention in the first place? We introduced this because we did not want the queries to kind of have a look into the future. We did not want and to attend to work for and it. We did not want work to attend to for and it, right? So this was our idea. But let's take a step back and let's see, how did we get these attention weights in the first place? How did we get attention weights? If we go back, to get attention weights, first we had query key and value matrices constructed, right? So this is query key and value. And then query multiplied by key transpose was the dot product between query and key. And this dot product resulted in attention scores. This is fine. Attention scores is fine. So attention score gives us how much each token is attending to every token. And then what we did was we constructed the scaled dot product. So in the scaled dot product, every number in this attention score was divided by square root of the dimensionality of the key space. So now we have scaled dot product. And now pay close attention. The scale dot product, how did we convert it into attention weights? We converted it into attention weights by taking softmax in every single row. Okay. So now we have attention weights. Now, is there any point in masking this? So this is what we did, right? In mask self-attention, we said, okay, we'll mask these guys. But look at what softmax has already done here. Softmax has already summed up like this: sigma e raised to xi, where xi is, so this is x1, x2, x3, x4, x5. So the denominator of softmax was sigma e raised to xi, numerator was e raised to xi. So each number in this attention weight was basically e raised to xi divided by sigma e raised to xi. And to calculate the sigma e raised to xi, you are already looking at the future, because now you are taking all these scaled dot product scores, which means by the time you reach attention weights, you have already had a look into the future. How? In the form of this sigma e raised to xi. So masking here is not going to completely eliminate your queries from having a look into the future. You have to do it even before you take the softmax. In the softmax summation, these guys should not have an influence in this row. Similarly, in the softmax summation, these guys should not have an influence in the second row. Similarly here, or rather these guys. Yes, these guys. Similarly, in the softmax summation, these two guys should not have an influence in the third row. And so for softmax summation meaning softmax summation in the denominator. So you are dividing e raised to xi by sigma e raised to xi. So that sigma e raised to xi should not consider all the items in the row. It should only consider items till the current token. Future keys should not be considered. How can we do that? So what we can do is, and before even that, this is termed as data leakage, because we were hoping this attention mask or masked self-attention to do something for us so that your future is not leaking into the past. But it has already happened when we took softmax. So this data leakage happens because we have not done something at the place where we are actually doing the softmax. So what can we do here? What is done is something very clever. We introduce this negative infinity term. So when we construct attention scores by taking the dot product between query and key, so q multiplied by key transpose, we get the attention scores. And here, what we can do is we can assign all the upper diagonal, upper triangular elements to be minus infinity. So this minus infinity, even if you divide by square root of d, it will remain as minus infinity. You can even assign it here. Basically this here, even if you don't assign minus infinity here, by the time you take the scale dot product, you assign all the upper diagonal, upper triangular elements to be minus infinity. And now look at what happens when you take softmax. So let's say I have these numbers 2, 3, 5, something like this. Let's say these are my numbers. And if I take softmax, 2 will become e raised to 2 divided by e raised to 2 plus e raised to 3 plus e raised to 5, right? 3 will become e raised to 3 divided by e raised to 2 plus e raised to 3 plus e raised to 5. and then 5 will become e raised to 5 divided by e raised to 2 plus e raised to 3 plus e raised to 5. This is what will happen. Now imagine I want to mask these two guys. So then this will become 2 comma minus infinity comma minus infinity. So now what will happen to 2? 2 will become e raised to 2 divided by e raised to 2 plus e raised to minus infinity plus e raised to minus infinity. What is e raised to minus infinity? E raised to minus infinity is 1 by e raised to infinity, which is 0. It's a very small number. So this will become what? E raised to 2 by e raised to 2 plus 0, which will be 1. And what will become to this guy? This guy will be e raised to minus infinity divided by e raised to 2. What is this? 0. This guy will also become 0. So what happens now is, after taking softmax by assigning this to minus infinity, so 2 comma 3 comma 5, this is 3. 2 comma 3 comma 5 will become 2 comma minus infinity comma minus infinity. And now this will become, after taking softmax, this will become 1 comma 0 comma 0. Now this is the case when I wanted to mask these two. What if I only wanted to mask the third one? Let's say 2 comma 3 comma 5. Then I will put the last item to be minus infinity. So 2 comma 3 comma minus infinity. And then when I take softmax, last item will become 0. First item will become e raised to 2 divided by e raised to 2 plus e raised to 3. Second item will become e raised to 3 by e raised to 2 plus e raised to 3. So this is how converting the items that we want to mask as minus infinity before we take softmax will help us convert those things into 0 after the softmax is implemented. So now after we implement the softmax, these things would have become 0 and the remaining items will automatically add up to 1. Because after taking softmax, here you might have noticed, after taking softmax of this, we don't need any more normalization. After taking softmax, this will automatically become 0, 0. And after taking softmax, this guy 2, 3 minus infinity will become a probability distribution such that the sum of these two or these three numbers are 1. Because if you add these three numbers up, you have e raised to 2 by e raised to 2 plus e raised to 3, then plus e raised to 3 by that, so that I can add in the numerator itself, plus 0. This is 1. So now softmax operation automatically converts this attention weights into a masked attention weight such that the remaining elements row wise will add up to 1. That's what happened. So this is what we can do to mathematically implement the masked self-attention without having data leakage, right? Now the only place where query and key are interacting to see the future is here, because here the query is getting multiplied with key. So of course, when we construct attention score, every key is interacting with, so this is the first query is interacting with first key, first query is interacting with second key, first query is interacting with third key, fourth key, and fifth key. Similarly, second query is interacting with second key, with first key, with second key, third key, fourth key, fifth key, and so on, right? So this is now the only place where query is getting a look into the future. But by the time you reach here, that is gone, because you are masking your attention scores by using minus infinity, and then softmax convert those minus infinities into zeros. Now let's see how to implement this in code. Okay, so now first let's have a look at the attention scores, because attention score is what we want. We don't want attention weights right away. We want to convert attention scores such that the upper triangles are negative infinity. So these are the attention scores, 6 by 6 matrix. Every single row will not add up to 1. Only attention weights add up to 1. Attention scores will not add up to 1, right? Only after normalizing the weights, this will become weights, and only that will add up to 1. So now what we want is, we want to convert these numbers to minus infinity in the first row. Similarly, in the second row, third, fourth, fifth, and sixth items need to be converted to minus infinity, right? This is what we want to do. So first what we define is, we define this upper triangular matrix where wherever we want minus infinity, those numbers are now 1. Remaining ones are 0. And then what we do is, we use the mask such that wherever the mask is 1, we convert those numbers to minus infinity. So minus torch dot infinity is basically minus infinity. And look at what this mask.boolean does. Mask.boolean returns true whenever it is 1, otherwise it will be false. And the mask is applied to this attention scores such that wherever you have 1s in the mask, you have minus infinity. Wherever you have 0s in the mask, nothing is done. The mask is not applied. So now what you have is the same attention scores you have, except the upper triangular elements are now minus infinity. So minus inf is the way Python denotes minus infinity. Now we can apply softmax row wise. So softmax is nothing but softmax of mask divided by keys.shape. So here we would have already divided by square root of d. So attention scores that we have, let's have a look. So attention scores were queries multiplied by, actually square root of d division has not happened here, but we can introduce that if we want here. So we could say attention underscore scores equal to attention underscore scores divided by, and the dimension was 2, right? So 2 raised to 0.5. So if we wanted, we could do that. And then what we have is the resulting thing is, well, let me just put this in bracket just to ensure that the calculation is done correctly. So now these are my new attention scores. So attention scores are divided by square root of 2. And actually 2 is nothing but dimension out. So d underscore out is also fine. Oh, let me run this once again because I just multiplied it multiple times. Okay. So yeah, so now these are my masked attention scores. Then I apply softmax, and after applying softmax, I have now each row converted into probability scores such that the upper triangular ones are still 0. Right? So here, actually here there is already the division by square root of square root of d out. So here I can just remove it. So let me just run this once again. So this is the attention scores. Yeah, so now I have the attention scores. Then attention scores are masked. The mask before taking softmax is divided by the square root of d. And then we take softmax, then each row will become such that numbers are in a probability distribution. All right. So now these are the attention masked self-attention scores. Okay. So we are so good. I hope now you understand how we implement masked self-attention, which is what is actually done in GPT. In GPT, we don't directly use the attention weights. We mask the ones in the future. Now there is one more thing which is actually implemented in large language models like GPT, which is causal attention, but with dropout. So dropout is an idea which we have discussed in detail in one of the earlier lectures where we were going through the journey of a token. And dropout is used for making sure that lazy neurons are actually contributing or they are actually learning from the data. So in this example, let's say in this layer, in the second layer, this neuron is doing most of the work, meaning the weights in these two neurons are, let's say, very small. What that means is whatever comes out of this layer is mostly influenced by this neuron. Similarly, in this layer, let's say this is the neuron that is doing most of the heavy lifting, which means this neuron, even if it was absent, right, it would not make any difference to the output. So these are called lazy neurons, which are not contributing to your learning process. Or conversely, these are the neurons that are learning too much or kind of like helping you overfit on your data. So what you do in dropout is in each layer of the neural network, you randomly drop or you randomly switch off some neurons. So here, let's say you switch off this neuron and this neuron. So I have deliberately taken the non-lazy neurons to be switched off here, but it's done probabilistically, not like manually. So you will say with a probability of 0.5, each neuron will be switched off, which means statistically half of the neurons will be switched off, half will not be. But then what happens is now these two lazy neurons are now part of the forward propagation. The one that was doing the heavy lifting was not part of it anymore, which means these neurons the weights of these neurons will have to be adjusted during the backpropagation such that the loss is minimized. Otherwise, if the forward propagation entirely relies on this neuron, loss will be anyway minimum. Then the weights in these neurons are not going to get modified anyway. But by introducing dropout, you force these lazy neurons also to take part in the learning process, right? So this was the idea of dropout. Now, similarly, in attention score, let's say some tokens have too much dependency with each other. So let's say if I go back to our example, if the dog chased the ball, let's say the ball is too strongly dependent on chased, or let's say the ball is too strongly dependent or too much attending to dog, there could be high token to token or inter-token dependency. That is not good. So what we can do is we can introduce something similar to the idea of dropout using dropout mask. So let's say I got the masked attention after taking my Softmax. Now my masked attention will look something like this. The first row sums up to 1, second row sums up to 1, 0.8 plus 0.2, this sums up to 1, this sums up to 1, right? Now this is my masked attention. Now what I do is I define a dropout mask where if my probability P is equal to 0.5, half of the items in this 6x6 matrix will be masked. So in each row, there is a likelihood that half of these attention scores might be masked and remaining half might be present. So now if I introduce this dropout mask into this masked attention matrix, this is how the resultant one will look like. Resultant one meaning the values I have again normalized. So if I had masked, let's say, if this mask was introduced in the second row, all items are now gone. So see, in the second row now there are no attention scores left because 4 of them were already masked in the masked self-attention. Now 2 more are gone because you have the dropout mask. So 4 plus 2, 6, all 6 are gone. Similarly, in the third row, you had only 3 attention scores remaining after the masking process. From those 3, you lose 2 because this is the third row. And the first and third item are now masked. Only second item remains. So only second item remains. And obviously after normalization, that second item will become 1.0. But there is one more thing here to notice. In dropout, let's say I am masking half of the attention scores. Then the remaining half of the attention scores have to do the work, which means I have only half parameters available to produce an output of similar magnitude as early. Which means whatever is produced out of this, I have to scale up by a factor of 1 by 1 minus P. So if probability of masking was or dropping out was 0.8, it means only 20% is remaining, which means 1 by 5th are remaining. So whatever output I get from a mask or out of an attention score, which has only 1 by 5 values available, I'll have to scale them up by a factor of 5. And how do you get that? By scaling up by a factor of 1 by 1 minus P. So here, when we scale up by 1 by 1 minus P, if P equal to 0.5, each numbers will be scaled up such that this will become 2, this will become 2, this will become 0.8, this will become 1.2, this will become 0.4 like that. So those numbers will be multiplied by 2. So this is how dropout is done. And I'll tell you the logic of why this multiplication factor has to be introduced. Let's go back to dropout. Let's say I have this as the input, x equal to 1, 1, 1, 1. Okay. And let's say my weights are also 1, 1, 1, 1. So if I now do x multiplied by weights, I will get 1 times 1 plus 1 times 1 plus this plus this. So that'll be 4. Now let's say the value that I was supposed to predict was 5. But the prediction happened to be 4. So the loss will be like 1. So difference between prediction and reality, right? Now let's say I introduce dropout such that 2 of the P equal to 0.5, which means half of the weights will be masked. So let's say this is gone, this is gone. Now what will be my output? This one has nothing to multiply with it. This one also has nothing to multiply with it. So now my output will be 1 times 1 plus 1 times 1, which will be 2. And now if you look at the loss, your loss is now 3 because what you are supposed to predict was 5, but what you are predicting is 2. But this loss did not happen because your weights were bad. This loss happened because you have dropped out half of the weights, which means remaining half of the weights I have to scale up by a factor of 1 by 1 minus p. So what is 1 by 1 minus p? 1 by 1 minus p is 1 by 1 minus 0.5 equal to 1 by 0.5 equal to 2. So this I have to scale up by 2. This I have to scale up by 2, which means 2 times 1 plus 2 times 1 equal to 4. So now I am back to similar output as before. So this is exactly or similar order of magnitude as before, right? So this is what I have to, we have to do while doing dropout. So now let's see how this dropout can be implemented in code. It's again fairly easy. So first we define a matrix which are ones. So ones meaning it's a 6 by 6 matrix. Instead of 6 by 6, I can simply say I want to make to be more generalizable. I can say I want a matrix which are of context length. So my context length is 6. So here I will say context length, comma, context length. Output is not going to change, but it will be more generalizable, the code. And then I have to drop out with, let's say, 50% probability. So here again, since I'm using probability, it's random. So I provide a seed to my random number generator. And then I drop out with a probability of 0.5. And if I apply this dropout to this mask, you see half of them are now gone. So there were 36 here and almost half of them are gone. Remaining ones will be doubled. They will become 2. Now what I do is the weights, what will happen to the weights after applying the dropout mask? What will happen is when I apply the dropout mask to these attention scores, so here is how we are dropping out according to the mask. So attention underscore weights were these numbers, right? And then we are applying the dropout mask, which looks like this. So it will simply become whichever value was 1 and wherever there is 2.0, that will become 1 times 2.0. And the third row, let's focus on the third row. Third row, all of them are, these first 4 items are 2. So in the attention weights, the first 4 items are like this. So this will become 0.66, this will become 0.72, this will become 0.60. Let's see if that is the case. 0.66, 0.772, 0.73, and then this is 0.60, right? So this is how the mask is applied. Now this is now my final attention weights after applying dropout mask. So if we go back and write what all things we did, right? So that we know what we are doing. We had input tokens. We had 5 input tokens. Each of them were 3 dimensions. So we had a 5 by 3 matrix. Now these input tokens we converted to query, key and value using WQ, WK and WV. The dimensionality of the query key value space was 2, which means Q was 5 by 2, query was key was 5 by 2, value was 5 by 2, and the matrix WK, WQ and WV was 3 by 2. Now once you have these 3 things, you calculate the dot product by taking Q dot key transpose. If you take Q dot key transpose, what do you get? You get attention scores. And these attention scores will be 6 by 6 because in our input there were 6 tokens. And what we do is we perform masking of the upper triangle by putting those elements as minus infinity. And then we have to convert the attention scores into attention weights. So what do we do? These attention scores with upper triangular elements to be minus infinity, we scale down. So this is now the scale dot product. We scale it down by multiplying each number by 1 by square root of d, where d is the dimensionality of the key space, which is equal to 1 by square root of 2 in our example. Now you get scaled dot product between query and key. And then the next step is you take softmax. And we saw that when we take softmax, if minus infinity is involved in that particular series, those numbers will become 0. Rest of the numbers will be such that they will add up to 1. So now after applying softmax, what we will get is again a 6 by 6 matrix where the upper triangular elements will be zeros and these numbers row wise will add up to 1. Like that, there will be 6 rows. Last row will be unaffected. Now, after doing this, so these were the attention weights, right? So these are not attention scores, these are attention weights. Now, these attention weights, we did one more thing. We applied dropout mask. So in dropout mask, what we did was, let's say we are dropping out with a probability of 0.5. Half of these weights will be masked and remaining half will be scaled up by a factor of 1 by 1 minus p, such that the overall magnitude of your operation is not affected because of the fact that half of your numbers are now gone. So at the end of this, you now get the causal or masked self-attention that is used in GPT. So this is what we implemented today in summary. Now, is this fully what is done in GPT? Not yet. One concept we are yet to discuss is multi-head attention. In GPT, there are multiple attention heads in parallel, and each attention head takes care of certain number of dimensions from your input dimension, and then finally you concatenate such that the output that comes out is having same dimensionality as that of the input tokens. Here you could see that the dimensionality has changed, but in GPT, usually final dimensionality is preserved. If there is 768 dimensions in the input, it will be preserved at the output of the multi-head attention also. So in the next lecture, what we are going to look at is multi-head self-attention, but it will be now very easy for you because you have already covered, I would say, 95% of what you have to know with respect to self-attention. So if we take a step back and see what all things we have done so far, we started by discussing about recurrent neural networks in the context of neural machine translation, NMT. And we saw that recurrent neural network with the encoder-decoder architecture was not good because it was producing one context vector as the output. So encoder was producing one context vector and decoder was entirely relying on that one context vector to kind of decode the meaning of whatever is there in the encoder. So that was not good. So relying on just one context vector was not good. And that is when badano attention came into picture. This was in 2014. In badano attention in 2014, the decoder could access hidden states in the encoder, and then those states could be multiplied by attention scores or attention weights. So basically, you could pay attention. So if you are using it for neural machine translation from English to French, every single token that is coming out of the decoder could pay attention to every single hidden state in the encoder. Now, this was in 2014 and it was generalized in 2017 when self-attention was introduced. This was in the Attention is All You Need paper, the famous paper. Now, the way we learned about self-attention is we initially implemented a simplified self-attention without trainable weights, where we said, okay, we have input embeddings. We take dot product between these input embeddings, and we will take the dot product as the attention scores, and then we'll normalize those attention scores to get the attention weights, right? That was the simplified self-attention. So we first implemented simplified self-attention. Then we said simplified self-attention is not really good. It's good to understand the concept, but it's not really good because you are taking direct dot product between the input embeddings. What you should have actually done is convert the input embedding into some other space using trainable matrices and take the dot product between those two. So that is why the input embedding X was converted to query, key, and value. Now to construct attention score, we took the dot product between query and key, q dot k transpose. This was attention score. And then now we learned about masked attention. So we mask the upper triangle with minus infinity. We then take 1 by square root of d, and then we take softmax to get the, and then we do dropout to get the final attention weights. Now, once we have the attention weights, I don't know what to call that. Maybe I can just call it as attention weights. Once we have this, how do we calculate the context vector? Context vector is finally what we want. We use this value. So attention weights multiplied by value is equal to context vector. So this is the summary of what we have done so far. I hope it has been a very long journey, but I hope you are now having a very good understanding of what exactly is context vector, what exactly is the attention mechanism. In the next lecture, we will try to understand properly what is multi-head attention, and by then your understanding of the crux of the neural network, of the transformer architecture will be full. This lecture was also pretty dense in concepts, but I would say easier compared to the previous lecture. But still, if you have some doubts or questions, feel free to pause, take notes, and watch again. That way you can understand it much better. I hope you are feeling very good satisfaction in your journey of understanding the transformer, and we are yet to move to vision transformer, like which we will soon do. So once you understand the transformer architecture in the context of language, you can also understand the transformer architecture in the context of vision. So your journey when it comes to vision transformer will be very smooth and very enjoyable. So I hope to see you again in the next lecture. Take care. See you then. Bye. Hi. Welcome back to a new lecture from Transformers for Vision. In this lecture, we'll be doing a very specific thing, which is hand calculating how exactly did GPT-3 get 175 billion parameters. This exercise will give us a fairly good intuition about the architecture of the LLM itself, and we will also have a fairly good idea how these parameters are distributed inside that architecture. How many are there in the input part of the neural network, how many are there in the transformer layer, and how many are there in the output part. If you don't know the architecture of a large language model, I highly recommend you to go through at least one video that explains the architecture in detail, because here I will not be going into all the details of the transformer architecture because that will make the lecture very long. Instead, I will assume that you have some basic knowledge about the large language model architecture, you have some basic knowledge about the transformer block, etc. And then from there, I will walk you through step by step on how exactly to calculate these parameters. And don't worry if you have forgotten how exactly the architecture of an LLM looks like. I will give you a brief recap so that you can refresh. Now, you might be wondering, how is GPT-3 architecture relevant for vision-based tasks? The reason why I am explaining this to you is so that you can carry forward the same intuition that you get from this lecture also to the cases where you talk about or you learn about vision transformers. So that's the reason why I introduced this lecture. So let's first look at the architecture of the LLM itself. So this is the overall rough architecture. Don't worry by seeing multiple blocks. I will divide it into meaningful chunks. So the first block, so here you can see 1, 2, 3. We can look at the entire LLM architecture in 3 blocks. First block is the part that deals with input. So you give an input or a prompt, and some things happen to this input where it is tokenized, and a position embedding is also done. So I will explain what these means, but just keep it in your mind. Then you have transformer block where you have 2 layer normalizations, these 2 blue blocks. You have dropout happening at 2 locations. You have a feed forward neural network, and you have the main guy, which is the multi-head attention. So this transformer block will be repeating 96 times in series in the GPT-3 architecture. That is one thing. This is one place where you will hear the number 96. Another place where you will hear the number 96 is in the number of heads inside this multi-head attention, which is 96 heads in parallel. So these two 96 are 2 different numbers, so please don't confuse between them. Then the last block is the output block, where the final prediction of the next word happens in the large language model, which has a normalization layer and an output layer. Now what we want to calculate is how are these 175 billion parameters distributed in these blocks individually and also into these individual modules. How many billion parameters are there in each of these? Let's try to calculate. So we will start very systematically, let us look at the input part. A GPT-3 with 175 billion architecture models, 175 billion parameters have the following architecture. It has 96 layers. What does this mean? It has 96 transformer blocks in series. The token, which could be a word, which could be a subword, are represented using vectors of 12,288 dimensions. So each token is represented by a vector of these many dimensions. And within each transformer layer, you have a bunch of things. And one of the most important things is the multi-head attention. So each multi-head attention has 96 heads. So 96 heads make up one multi-head attention inside one transformer block. And inside these multi-head attentions, each of them take care of 1/96th of the dimension of your input token, which means 12,288 divided by 96 equal to 128. So the tokens are represented not in a 12,288 dimensional space inside these attention heads, but rather it is represented in a 128 dimensional space inside the attention heads, individual attention heads. And then they are concatenated back to create the 12,288 dimensional token back. Similarly, you have a feed-forward neural network over here. This feed-forward neural network, what it does is it projects the token, the transform token of 12,288 dimensions into a space with 4 times more size. So whatever is the input dimension, in this case it's 12,288, you multiply that by 4. So you are projecting it into that dimensional space, and then you project it back. So that is what is happening in the feed-forward neural network. I will explain the exact number of parameters when we calculate it. I'm not talking about the parameters yet. I'm just giving you the architecture related numbers, and then we can calculate the parameters later. Then you have a dictionary with a vocabulary size of 50,257, which means that many unique tokens exist in your vocabulary. And each token is represented by a 12,288 dimensional vector, please note. And context length, the number of tokens which you can feed to the GPT-3 architecture is 20,048. 2048, my bad. So this is the general GPT-3 175 billion architecture. Now, based on this information, let's try to calculate the number of parameters, and finally, all of that should add up to 175 billion. Let's start with the vocabulary. So, as I mentioned, the input token is a vector of 12,288 dimensions. So, this is dimension 1, dimension 2, etc. up to 12,288. So, this is the input token. This is one token. The vocabulary consists of 50,257 such tokens. And there are numbers inside each of these, right? Each of these are numbers that are trained so that you can have a good representation of each tokens. So let's say one word is a token, then the word cat, maybe this is the token corresponding to the word cat. This is the token corresponding to the word, let's say zebra. There are subwords also. I'm just simplifying it here. So how many parameters are there in this vocabulary? You will have 50,257 multiplied by 12288. Those many parameters will be there. And what is this number? Let's calculate using calculator. 50,257 multiplied by 12288. This is 617.55 million. So this will be 617.55 million. So these many parameters are there in our input embeddings because the vocabulary size is this much. Now, how many tokens are there in our context window? Our context window size, as I mentioned, is not the entire vocabulary. It's only 2048 tokens. And each token, of course, it is 12,288 dimensional vector. which means the total number of parameters, trainable parameters, to construct a position embedding, because what you would be doing is you won't be taking the token value directly and using it. You take the token value from the dictionary, yes, but on top of it, you add a position embedding. Why is position embedding important? Let's say the dog chased another dog. So here the dog word or token is appearing twice, but this is appearing in the position number 2 and this is appearing in the position number 5. So there should be some difference in the way this dog is represented and this is represented, and that's why you have to add some information about the position to your input embedding. And how many such position embedding vectors do you need? You will need as many as there are number of tokens in your context window. So context window is 2048. So you will need that many position embedding vectors. So what would this be? The number of parameters 12288 multiplied by 2048. And this is equal to, okay, before we use calculator, let's roughly calculate how much this should be. So 2048 tokens in the context window, but roughly 50,000 tokens in the vocabulary, which means you have 1 by 25th number of tokens in your context window. And what would that mean? The number of parameters will be 1 by 25th of this, which should be roughly 25 million, right? 25 multiplied by 25 is 625. So roughly we should have 25 million parameters here. So this number, let's calculate exactly to see what it is. So 12288 times 2048 equal to 251,65824. So this is 25.1 or 25.2 million if I round off to only one decimal point. These many parameters. So in the embedding part, in the input embedding part, totally how many parameters do we have? Due to vocabulary, you have 617.55 million. And due to position embedding, you have 25.2 million. So if you add these two, roughly this should come to 17 plus 25 is 42. So this should be 642.75 million, roughly. Roughly these many parameters should be there where in our part 1 of the transformer architecture, which is part 1. Part 1 is this 642.7 million parameters in this part. And compare this to 175 billion. This is 0.64 billion, right? So it's very small compared to our total number of parameters that we are expecting. Now let's go to the second part, which is the transformer block itself. As I mentioned, there are 96 such blocks. I'm just drawing one block here. And there are few places where parameters can be expected. There will be some parameters in each of these layer normalization. There will be, of course, some parameters in the multi-head attention. Dropout does not introduce parameters because you are simply randomly not using certain neurons. So it won't introduce additional parameters. But there will be additional parameters in the feed-forward neural network. And this will repeat 96 times. So if we do the calculation for one transformer block, whatever numbers we get, we simply multiply it by 96 to get the final total number of parameters due to the transformer blocks. And later we can calculate the output block, the number of parameters in the output block separately, right? So now, what should we look at first? Let's look at multi-head attention. So in multi-head attention, what's happening is the following. We have the embedding. So this is the vector in which position embedding is added. So the dimension is still 12288. And what happens is we pass this to each of the 96 attention heads in the multi-head attention. So this 96 is different, right? This 96 is within an individual transformer layer. And what would be the dimension of this token inside those attention heads? It will be 1 by 96th of 12288. 12288. 1 by 96th of 12288 is 128. So the dimensionality of our token inside this individual heads of the multi-head attention is 128. So how do you transform something with 12288 dimensions to something with just 128 dimension? Here you have the query vector key vector and value vector. And to perform this transformation, you will have bunch of weights for query, bunch of weights for key, and bunch of weights for value. So let's calculate that. So number of weights for key will be weights for, let's say, or rather query will be 12288 multiplied by 128. But there could be bias also, which you can add here. So bias is added at the nodes at the output. So how many such bias parameters can you add? Because you have 128 as the dimension here, you can have 128 bias values. So this plus 128. So this will be biases in the queue plus weights. And same thing repeats for key. So key also is exactly the same. You have 12288 times 128 plus 128. This is the bias. And value is also the same. 12288 times 128 plus 128. And what would this number be? So let's calculate. 12288 times 128 is equal to something. Then you add 128 to this. Doesn't change much. Then you multiply this by 3 because I have key, query, and value. So this will be 4.72 million, right? So this number turns out to be 4.72 million. Let me just draw it. 4.72 million. Where is this 4.72 million coming? It is coming in one of these attention heads, or 4.718 million. That was the number that we got. Like this, there are 96 attention heads in one transformer layer. So total number of parameters here would be 96 multiplied by 4.72 million. So let's do that. So this multiplied by 96 equal to 453 million. So the total number of trainable parameters inside these this whole attention, multi-head attention, is what? 453 million. 453 million. Okay. So let's just write it down. Let's go back to our figure and just write down that multi-head attention. Yeah, one more thing is there. Before we add this 453 million, we have one more transformation. So what happens is you get 1 by 96th of the dimension from each attention head, and then you concatenate each of those outputs to get back the 12,288 dimensional transformed input token. But then you perform one more transformation of this final concatenated token through an output matrix. Output meaning just the output from the multi-head attention, not the final output of the LLM. So here dimensionality does not change. Dimensionality will remain to be 12288. So which means the transformation that you are doing is through a matrix of dimension one of number of parameters 12288 multiplied by 12288. You can imagine it to be like a simple neural network with fully connected connections. But then there could be bias parameters that is added at the nodes in the output. So there are 12288 number of nodes. So you can add that also here. So this plus 12288, and this will be 12288 times 12288. This is equal to something. Then that plus 12288 equal to 151 million parameters. So this is equal to 151 million parameters, where in this output transformation matrix. So you have to add this 151 million to 453 million. So 151 plus 453 equal to 604 million. So finally, inside our multi-head attention, we will have multi-head attention plus counting the output transformation, we will have 604 million parameters. So we can note this down over here, 604 million parameters. We are still far, like a long distance. Oh, I'm sorry. This, let me just make sure that, yeah, it's correct. 604 million. Yeah. We are still far away from the 175 billion, but we will soon get there. Now let's look at the layer normalization. Both of them are identical. So we just need to do calculation for one of them and that same number will apply. The number of tokens will be the same for both. So in layer normalization, what happens is you have input token. I mean, after transformation, it still retains this dimensionality. What you do is there are individual values inside each of these dimensions. They are normalized by subtracting the mean of all these values and dividing by the standard deviation of all these values. So you want mean to be close to 0. I mean, the mean of the distribution to be close to 0, standard deviation of the distribution to be close to 1. And then each of those are scaled by a scaling factor, and you add a little bit of bias to each of these numbers separately. So the total number of trainable parameters are how many ever number of betas and how many ever number of gammas are there. So the number of betas will be equal to number of dimensions of this, which is 1, 2, 2, 8, 8. Number of gamma parameters will also be the same, which means the total number of trainable parameters in each layer normalization is 1, 2, 2, 8, 8 times 2, which will be 1, 2, 2, 8, 8 times 2 equal to 24576. In millions, we can express this as 0.024 million. That many parameters in each of these layer normalization. So let's go back and draw. So this will have 0.024 million. This will also have 0.024 million. Okay. So these three are done. Now what else? Now we have feed forward neural network. So what feed forward neural network does is its input dimension is again the transform token, which is of 1, 2, 2, 8, 8 dimension. Its output is same. So this feed forward neural network does not change the final dimensionality, but what it does is it projects this incoming vector into a higher dimensional space of 4x the number of dimensions, and then it projects it back. So here there is a transformation happening from this dimension to 4x whatever this number is, and that would require certain number of weights. The number of weights will be 1, 2, 2, 8, 8 times 4 times 1, 2, 2, 8, 8. So this will be the number of weights, but you can have bias also for each of these. So the total number of bias parameters will be this number. So this plus 4 times 1, 2, 2, 8, 8. So let's calculate this what it is. 1, 2, 2, 8, 8 times 4 times 1, 2, 2, 8, 8. This is equal to some number plus 4 times 1, 2, 2, 8, 8. I think I might have messed up the brackets. Let me do this once more. Okay, 1, 2, 2, 8, 8 times 4 times 1, 2, 2, 8, 8 equal to, so this is 603.97 million. So this will be 603.97 million plus whatever is 4 times 1, 2, 2, 8, 8 equal to 90. So this is 0.909 million, right? 0.909 million. So this will be around 604 plus 1, roughly 605 million parameters, something like that. 909, 604 plus 0.9. So like something like 604.9 million, something like this. So this is the first transformation from here to this. Now from here to here, you are going back in dimensionality. So what will this be? Total number of weights will be 4 times 1, 2, 2, 8, 8 times 1, 2, 2. So this 4x I have written is 4x of whatever this is. That's the number of dimensions here. And here it is 1, 2, 2, 8, 8. So that many, so your matrix that performs this transformation will have these many parameters. And then you can add bias also at the output nodes. So number of nodes equal to 1, 2, 2, 8, 8. So you simply, that many bias parameters will be there. So what would this be? This will be 4 times 1, 2, 2, 8, 8 times 1, 2, 2, 8, 8 equal to something, that plus 1, 2, 2, 8, 8 equal to 603.99, which is 604 million. So this will also be 604 million. So the sum total of this entire feed forward neural network will be 604.9 plus 604 million, which is 1208.9 million, which we can approximate to be 1209 million 1209 million. And in billion, what will this be? 1.209 billion, which is 1.21 billion roughly. So 1.21 billion parameters in this feed forward neural network. See, this is probably the biggest out of all. Now, what are the total number of parameters in one transformer block? It will be 1.21 billion plus 0.02. So this we can ignore because in billion, this will be even smaller. This is 0.024 million. So this layer normalization can be ignored to perform our approximate calculation. So you have 1.21 billion plus 604 million is 0.604 billion, which we can say 0.6, which is 1.81 billion parameters in one transformer block. 81 billion parameters. But like this, there are 96 transformer blocks in series. How will it look like? So all these things inside this gray box will repeat 96 times, like over here. So transformer block 1, transformer block 2, block 3. I mean, I'm calling it as layer 1, like this 96. So your total number of parameters due to the transformer blocks will be 1.81 billion multiplied by 96. So this times 96 equal to 173.76 billion. So this will, like this, if you multiply by 96, 173.76 billion. So now look at the distribution. Out of the 175 billion, we got almost 174 billion. And we understand that most of them are coming from the transformer block. Just 0.64 billion is coming from the input part. Now let's see how much is coming from the output. So the dimension of the token which has been transformed is still 12288 by the time it reaches this layer normalization. And what would that mean? It would mean the same thing. So earlier in the layer normalization, what did we do? We calculated the mean and standard deviation of this. We subtracted the mean so that the mean of the distribution becomes 0 and standard deviation becomes 1. So we did that. And then we multiplied with a scaling factor, which is a learnable parameter. We added a bias parameter, which is also learnable. So we will have what? 12288 number of beta parameters, 12288 number of gamma parameters. So total will be 12288 multiplied by 2. Again, 0.024 million parameters in the final feed forward layer. Where is that? This one. Sorry, final layer normalization. So this will be 0.024 million. Now what happens in the output layer? Our dimensionality of the token is still, the transform token is still 12288. Now at the output, we want something where we can say, hey, my vocabulary looks something like this. I have 50,257 tokens and I want to predict the next word or next token. So basically I want to know out of these 50,257 tokens, which one comes as the next token based on the current prompt input. So it'll be nice to have a distribution which looks like this, where I have bunch of values of total number 50,257, and maybe one value out of this is predominantly bigger. So let's say the ID of this is 2027. This ID, the 2027th token, let's say that is cat. Let's say that is this token, which means the next word which I'm supposed to predict, or the next token that I'm supposed to predict, is highly likely cat. I mean, there will be a probability distribution. So the value associated this might be 0.8. Maybe the rest of the values add up to 0.2. So that 0.8 and remaining values will add up to 1. So it's like a probability distribution. It goes through Softmax operation to have these numbers. But did you notice the input token? I mean, the token after transformation was 12288, but now it has to somehow become 50,257. Like what? Like something like this. So this 12288 has to somehow transform to this, which means another matrix ideally would be needed of dimension what? Of dimension of number of parameters 12288 multiplied by 50,257. Plus you can have bias at the output. So you can add another 50,257. But in GPT-3, so how many parameters would this have added? This would have added an additional 12288 times 50 to 57. That will be 617 million plus 50 to 57, still 617.6 million. So we would have gotten around 617 1.6 million extra parameters. But in GPT-3, they don't do this because you already have a matrix of these many parameters, which you had over here. Because your vocabulary had these many tokens and each token was 12288. So you had, if you remember, you had already bunch of parameters which took care of the vocabulary part and individual token part. So what is done in GPT-3 is these same weights are used. So you don't create new trainable weights at the output. Instead, you use the same thing which you used at the embedding. So you don't have these numbers. So this does not exist in GPT-3. So this number is 0, but you will have bias 50,257 parameters as bias, which is 0.05 million. So the total number of parameters in this is 0.05 million. So that's it. That's all the number of parameters. So your total number of parameters will now be 173.76 billion plus 0.64 billion plus these are small, like this is ignored because it's so small compared to these numbers. So this will be what? 173.76 plus 0.64. 173.76 plus 0.64 equal to 174.4, which is approximated and said to be 175 billion parameters. So this is how you get the 175 billion parameters in GPT-3. And just notice the distribution. 1.81 billion parameters are coming in individual transformer blocks. Within that, 1/3 of the tokens are coming in, 1/3 of the parameters are coming in multi-head attention part. 2/3 are coming in the feed-forward neural network. And like that, you have 96 transformer blocks, which means 174 or around 174 billion parameters come in the transformer block itself, out of which 2/3 are attributed to the feed-forward neural network. So 2/3 of 174 billion, it will be roughly slightly less than 120 billion, right? Slightly less than 120 billion out of 175 billion are belonging to this simple feed-forward neural network. Amazing, right? And 0.6 billion is in the input part, and a very, very negligible amount, 0.075 million is in the output part. It could have been 617 something million if we were having the weight matrix in the output layer, but we use the same one from the embedding. So this is how you should understand the distribution of parameters are in the GPT-3 architecture. This knowledge also translates to other models. So now you have a better understanding of how the architecture is using the parameters. Where exactly is it coming? Unlike we might think, most of the parameters are not coming in multi-head attention. 1/3, yes, 1/3 are coming in multi-head attention, but 2/3 is coming in the feed-forward neural networks. Feed-forward neural network is much simpler. You are just projecting into a 4x dimensional space. You are projecting it back. It's a very simple part, but 2/3 parameters are coming there. Amazing, right? So I hope this brings a lot of clarity. All these learnings also translate to when you try to understand vision transformers, because there also all these parts of the architecture will come into picture. So I just wanted to present you with GPT-3 because it's very famous. The model architecture is very famous, but the learnings translate to concepts in computer vision using transformers. So I hope you enjoyed this lecture. I will see you again in the next one. Take care until then. Bye.